Hello everyone, I'm Siddharthan. I hope everyone is doing fine. Today I'm creating a new playlist called as Deep Learning Projects, and in this playlist I will be uploading videos on deep learning use cases and projects where we will use neural networks, and I'll post videos on the machine learning course which we are working on already. So those videos will be posted regularly, and once in a while I'll try to make some videos on the deep learning project so that it is not monotonous for the viewers to watch, and you can also learn deep learning on the go. Okay, so that's the idea. And the first project that we are working on in this deep learning playlist is breast cancer classification with neural network. Okay, so if you're following my channel, you would have seen the project video in which we have worked on this breast cancer classification dataset, which is basically a numerical dataset, and in which we have used the logistic regression model in order to classify the data points as benign or malignant. So it is the same dataset that we will be working on. So if you haven't watched that video, you can just check this one out. And in this we will be using the neural network as I have told you. Okay, so this will be a very simple neural network that we are going to build. And if you have never worked on deep learning, if you have if you don't have any idea on how to create this neural network, so this video will be very simple for you to understand, and you can also implement this for other numerical data set as well. So this is the idea that I wanted to make this video on, so that it is easier for the viewers to make their own neural networks for different projects. And so as I've told you, we'll be working on this breast cancer data set. So all this codes, I've just made some simple data processing techniques that we already done in the previous video of breast cancer classification. I'll explain you what are all the things that we are doing here. So but we won't be including any data analysis stuff and feature engineering stuffs and all that. So we will be including only the basic things, so that we can focus mainly on building the neural network. And so if you want to get a clear understanding about this data, and if you want to know how to perform data analysis and all those things, so you can refer these videos. So the first video is basically, as I've told you, this is where we have used the machine learning model, which is basically the logistic regression model, where we use that model in order to classify the cancer. And the second video will be on the exploratory data analysis on this breast cancer data set. So I have provided the link in this collab file. And then how you can do some data visualization on this particular data set. So I have given all these three links. I'll also give the link for each of the three videos in the description of this video as well, so you can check that out. Okay, so I'll just quickly explain what are all the data processing part that we are doing before moving on to the neural network part. So first is, we are just importing the dependencies that we need. Dependencies in the sense the libraries and the functions that we will need. First, we are importing the numpy library. So numpy is very important because we may need to create some numpy arrays, we may need to perform some math on those numpy arrays and so on, and for that we are importing the numpy arrays. And then we are importing the pandas library. So the use of this pandas library is to create a data frame. So you can see, so this is how our data set basically looks like. In order to to get a better view of this data, to perform some analysis and processing, it is better to load this data to a pandas data frame. So data frames are nothing but more structured tables in which we can get a clear idea about our data set. So for that we are importing our pandas library, and then we are importing the matplotlib.pyplot. So once we train our neural network, so we will visualize how this training has been going on. So for that purpose, I'm importing this matplotlib library, and we are importing this sklearn.dataset. So this is the module. So sklearn as a module called as datasets, and this particular datasets module has some basic datasets like this breast cancer dataset, house price dataset, etc. And then we are importing the train test split function from sklearn.model selection, so that we can split our data into training data and test data. So these are all the basic libraries that we need. And once we are creating a neural network, so in that case we will be importing the TensorFlow and Keras, so that we will deal with in the later part of this video. Okay, so usually we use neural networks on image data and audio data, but there are not much tutorials available on how you can use neural networks for numerical data. So that's why I wanted to create this tutorial. And after this I'll post videos on how you can use this similar neural network for text data as well as image data as well. So that will be the upcoming videos. For now, let's focus on the numerical data set. So the first step is loading the breast cancer data from sklearn.datasets. So you can see here, so sklearn.datasets is what we are importing, and from that I'm giving this function called as load breast cancer, and I'm storing this dataset in a variable called as breast cancer data. So this is basically in the form of a library, sorry, so it is in the form of a dictionary. So I'm printing this breast cancer data set. If you see this dictionary, there is a key called as data, and this particular data contains all the feature values, and there is another element pair, which is basically the target, which is 0 or 1, where one target represents benign and the other target represents malignant. So the idea of this data set is, so if we give all these features, the model will tell us whether the particular tumor is benign or malignant. So benign tumors are localized, so these tumors doesn't travel to other parts of the body. Whereas if the tumor is malignant, so then only we call it as cancerous, because these tumors have the ability to move to the other parts of the body, and the problem gets serious. So this is what we are working on in this particular data set, where we have to predict whether a particular patient has benign tumor or malignant tumor. So that's the idea. And again, if you wanted to get a clear understanding and detailed understanding of this particular data set, please watch these 3 videos so that you understand this completely. And after that, so you can see the feature name. So these are all so this is the target name, which is malignant or benign, so 1 and 0. And we have the feature names. So if I just scroll here, so it will be given as this. Yeah, so you can see the feature names. So feature names are nothing but the names of the columns. You can see mean radius, mean texture, and so on. So these are all the values. So the data or the values that is present in this key called as data, or the values for the corresponding feature names. So we will understand how this comes and all that. And yeah, so now we are going to load this data, which we have loaded to this breast cancer data set, into a pandas data frame. And for that, I'm creating a variable called as data frame. So this will be the name of the data frame that we are creating. And here I'm using the pandas library, and I'm using the function data frame and breast cancer dot data. So when I run this, it will take all these values. So we know that this is the data set that we are working on. And when I mention breast cancer data set dot data, so all these values will be loaded from this to this. Okay, so all these values will be loaded. And after that, I'm setting columns. So columns is nothing but the feature names that we have seen. So when I give this feature name, so we get all these column names from this particular sklearn data set. So next, I'm just printing the first 5 rows of the data frame, so that we can get the sample on how this data set looks like. So we can see the columns like mean radius, mean texture, mean perimeter, and so on. So you can see the column names. And if you so if you want to check the number of columns, so you can see here, so 30 columns, 5 rows and 30 columns are there. So it basically gives us the first 5 rows, so that's why it is giving this as 5. And the total number of columns that we have is 30. So that means we have 30 features. And now we are going to add the target column to our data set. Okay, so target column is nothing but 0 and 1, which represents malignant and benign. So for that, I'm just creating a new column called as label. So you can also name this column as class, or you can name this as target, or anything you want. So in this, we are loading this target. So this target is this one. So when I run this value should be added to my data frame. So now what I'm doing is, I'm just printing the last 5 rows of the data frame. So if I scroll to the last, now I can see a new column called as label, whereas previously it doesn't contain that particular column. So we are just basically adding a new column. So the idea here is, so if you give all these features, so if you give all these features to your neural network or to your machine learning model, it should predict what is the label. So all these things becomes your X, and this final column becomes your Y. So this is the output that we are going to predict, and all the other 30 columns will be our input. Okay, so if you want to determine, or if you want to check how many rows and columns are there in your data set, you can run the function called as shape, data frame dot shape. So data frame is the name of the data frame that I've created. So you can name this as anything you want. So when I run the shape, I get that there are 569 rows and 31 columns. So 569 rows means there are 569 patients. So all these patients, the tumors of these patients will be classified as either benign or malignant, and 31 columns are there. Next, so data frame dot info. So this will basically tell you how many null values are there, and what is the data type of the columns that you have. So null value means missing values, non-null values means those values are present, right? So totally we have 569 entries, that means 569 rows. So each of this represents the column names. So 569 non-null values means 569 values are present in the mean radius column. So again, 569 values are present in the mean texture column. So all the values are present in this data set. So there are no missing values in this. So if we have some missing values, we need to process that. And all the data types are in the form of float, except the label, which is in the form of integer, which is 0 and 1. And next, you can also run this in order to check how many number of missing values are there in each column. So No, this one is similar to, so this particular value is similar to this one. The only difference is that, so this will tell you how many non-null values are there. That means how many values are present. And when you run this dataframe.snl.sum, it will tell you how many missing values are there. Okay, so 0 means there are 0 missing values in the mean, radius, and so on. So we can see all the values are 0. That means no values are missing in any column. So that's the idea. And then we are checking some statistical measures. So this is useful for us when we are doing some more data analysis on our data set. So describe will give me the descriptive statistical measures like count. So count is nothing but how many values are there in each column. So mean will give me the average value of each column. So std is the standard deviation, minimum is the minimum value of each column. So this is my 25th percentile, 50th percentile, 75th percentile. So 25th percentile means 25 percentage of the values are less than 11.7 in this mean radius column. So again, it is similar to 50th and 75th percentile, and this is the maximum value for each column. And 50th percentile is my median value. So I hope everyone is clear about these things, because like we have worked on this isnal, describe, and info on several of our projects. So I hope everyone is clear. So I'm just quickly going through all the codes. So if you don't understand this, again, you can just go to this exploratory data analysis video and breast cancer classification with logistic regression video, where I have made a very clear and detailed explanation on all these things. So the next thing will be, yeah. So next we are counting how many values are there for benign case and malignant case. For that, I'm using this value count. So this is basically to check the distribution of the target variable. So we know that there are two target variables, which is either 0 or 1. Which is the sklearn.datasets target. Okay, so we are checking how many data points have the label as 0 and how many data points has the label as 1. So we can see there are 357 data points with a label 1 and 212 values with the label 0. So the reason we are checking this is, if there is a huge imbalance in this distribution, we have to process this data. So let's say that there are 500 data points for this label 1 and only 100 data points are there for the label 0. So in that case, there is a huge imbalance. So in that case, we will perform methods like upsampling or downsampling so that the distribution is even. So this is very important when it comes to machine learning. So because like if there is imbalance, the model don't learn well, or it won't be trained well. So in this case, it is not a problem, because like the imbalance is not that much high, so we can just ignore this particular thing. So 1 means benign and 0 means malignant in this case. So this is if you wanted to know how we arrive at this particular information, so you can go to the documentation of sklearn.datasets. So this sklearn.datasets, where in that you can go through this load breast cancer. So in that the details will be given, or you can go to the UCI machine learning repository of this breast cancer dataset, where these details will be given. So understand that 1 means benign and 0 means malignant, and this is what we wanted to classify. And then we have another function called as group by. So what this group by function does is, it will group the data points into these labels, and it will give me what is the mean value for each of the labels. So just look at this one if you don't understand this. So I have label 0 and then I have label 1. For all the data points that has the label 0, the mean value for this mean radius is 17.4, and the mean or average value for all the data points with label 0 as an average value of mean texture as 21.6, and so on. So this is the mean value for the label 1. So we are grouping all the data points with label 0, and we are grouping all the data points with label 1, and when we are finding what is the average for each of the columns. So the important inference that we can get is, so we know that 0 means malignant, which is the most dangerous state, and benign is not that much dangerous. So the value are kind of more for the label 0, which is malignant. So malignant, as for malignant, most of the column values are greater when you compare it to the benign value. So you can see, so it is 17.4 here, this is like 12 something, so this is 21, this is 17, and so on. So the values are kind of more for malignant cases. So there is a clear distinction. So like this is very important for us, because it clearly tells us for malignant cases the values are kind of higher. So these features are nothing but the values that are taken from a test called as fine needle aspiration, which is basically a biopsy of the tumor. where they will collect the sample of this tumor cells from the patient, and they will run some test on some microscopes. I'm not exactly sure what is the process, but it is taken from this test, and these are all the cytological values. Cytological in the sense the measurements of the cells that they are taking for the sampling thing. So after that, so if we are doing some more data exploratory part, so we will probably use some plots and other things in order to get some more information on the data set again. So this is not a data analysis video, so this is implementing neural network. So let's not go deeper into it. So just a second. Okay, so now what we are doing here is we have to split this data into features and target. So I'm creating two variables. So one variable is x and the other variable is y. So x will contain all the columns except the label column, and this label column will go to the variable called as y. Okay, so here what I'm doing is, so I'm taking the data frame and I'm going to drop a column, and that column is label. So axis is equal to 1. So this means like whenever you want to drop a column, you will mention axis is equal to 1, and whenever you want to drop a row, you will mention axis is equal to 0. And I'm storing all the label into the variable called as y. So after running this, if I print x and y, so you can see that so this x doesn't contain the last column, which is label. So it will contain the columns from this mean radius all the way up to worst fractal dimension. So it basically contains 30 columns. So you can also see here, so these are all the 30 columns that we add initially, worst fractal dimension. So we have this label column, so that won't be present in this x. So this y will contain the label column, which is basically my target. So the reason we are doing here is, whenever we are training our machine learning model or neural network, we need to give the features and the target separately. So features are nothing but the input that we are giving to the model, and based on that input, it will predict my target. So that's the idea. And after this, we are splitting our data set into training data and test data. For that, we will use the function train test split. So we have initially imported this function from sklearn.model selection, and here we are creating four arrays: x train, x test, y train, and y test. And I'm splitting x and y, so these are all the attributes for this train test split function. So I'm going to split this x and y into x train, x test, y train, and y test. So x train is nothing but training data of all these features, and the corresponding labels will be stored in y train. And x test is the test data features, and all the labels for this test data will be stored in y test. Okay, so x train is the features of training data, and the corresponding labels in y train. X test is the test features, and y test is the labels for those test features, and so on. And the test size is equal to 0.2. That means I want 20% of the data to be my test data, and random state is equal to 2. So the reason we are using this random state is, if you are using a different random state value, your data will be splitted in a different way. So if you want your data to be splitted in the same way as my data is getting splitted, then we both have to use the same random state. So that's the idea of random state, and the only purpose is to get some reproducible results. So it is not like that much important. So it is just to get some same results whenever we run our code. So we are checking how many data points are there for the training data and test data. So x is my original data set, which contain 569 data points, and 80% of the data, which is 455, goes to my x train, and 20% of data, which is 114, goes to my x test. Okay, so we have worked on these up to these things before, and what we are going to see after this is what is new for you. Okay, so if you haven't worked on deep learning, so this is the part where we will be creating a simple neural network in order to train this neural network with this breast cancer data. Okay, so now we know that a neural network will contain several layers. So the first layer is my input layer, where I will give my features, and the final layer is my output layer, where the model will actually predict whether the target is either 0 or 1. In between, there can be multiple hidden layers. Okay, so there can be one hidden layer, there can be 10 or even 100 hidden layers in a neural network. So we need to develop this particular structure. So we need to create some layers for our input, a single layer for our output, and several layers for hidden. So input and output will be one layer, and hidden can be multiple layers. So this is what we are going to work on, and this is the most important part of this video. So for creating this neural network, we are going to use two libraries. One is TensorFlow, and the another one is Keras. Okay, so let me just make these text as bold. And now let's import the required libraries. So this will be importing TensorFlow and Keras. Okay, so I'm going to import TensorFlow as TF. So TensorFlow library is already installed in Google Colab, so I'm not installing it. So if you are working on Spider or PyCharm, you probably have to install this TensorFlow library. So using pip install or Anaconda installation, so you can use any one of those. So in Colab, it is already installed, so we don't need to worry about it. So next thing that I'm going to do is I'm going to set a seed. So tf dot random dot set seed. I'll give a value as 3. So I'll explain you why we are doing this. And then we are importing Keras. So from TensorFlow, import Keras. So let's try to understand this TensorFlow and Keras. So TensorFlow is the deep learning library developed by Google. Okay, so there are several functions, and like we can create neural networks easily by using this library called as TensorFlow. And again, there are several other libraries like PyTorch and Microsoft CNTK, which is basically cognition toolkit. So these libraries are used for creating deep neural networks and so on. And the widely used libraries for deep learning are TensorFlow and PyTorch. So if you think about this Keras is not a standalone library, so it is just a wrapper of this TensorFlow and Keras. So like when TensorFlow was released initially, it was hard to make neural networks from TensorFlow because like the coding part is bit hard. What Keras did is it used TensorFlow as its backend, and after that, the building the neural networks became easy because they have created several APIs and functions so that we can easily build our neural network. So that is the use of this Keras. So you can set your backend to TensorFlow or PyTorch in Keras. So here we will be using TensorFlow. So after a while, TensorFlow included Keras in their library itself. So that's why we are importing Keras from TensorFlow. So you can also import TensorFlow separately, and you can specify the backend as Keras. But this is more easier. Now coming to this random seed. Okay, so I have set this set seed to 3. So whenever you are training a neural network in Keras, so there are several weights and parameters that will be initialized. So each time you train your neural network, so this as it is a random way of generating the values, some of the values may be different. So the final outcome is that your accuracy value may change each time you run your neural network. So in order to avoid that, we set a random seed. So if you set this random seed, no matter how many times you run your code, you will get the same accuracy score. So that's the idea of this, setting this random seed. So this is just like, this random state to just get, reproducible results. So the main thing is we are importing TensorFlow and we are setting some random seed, and then we are importing this Keras from this TensorFlow. So you should set this random seed as soon as you are importing this TensorFlow, then only it will work. Okay. So these are all the two libraries that we need, TensorFlow and Keras. So I'll run this one. And now we are going to build our neural network. So cannot import Keras from TensorFlow. Okay, so there is some error. So this should be a small letter, so it should not be in caps. So that's the thing. Okay, so I'm importing TensorFlow and Keras. Now I'm going to build this layers: input layer, return layer, and output layer. So I'll create a command here as setting up the layers of my neural network. Okay, so for this I'll just create a variable called as model. So in this model only I will create my neural network layers, and for this I'm going to use keras.sequential. So you probably would have heard about this sequential. So this is where we will stack the layers of our neural network. So this is a very useful function that is present in this keras. So keras.sequential, I'll just create a list here. Okay, so what we are basically doing here is, so now we will be setting up the layers for our neural network. So keras dot layers. Okay, so keras dot layers dot flatten, and in this I'll mention my input shape. Okay, so or else I'll just mention the layers first. After that we can mention the number of neurons and the parameters for it. Next is keras dot layers dot dense, and finally keras dot layers dot dense. Okay, so this keras dot layers dot flatten is my first layer of network, and second I have an hidden layer which is this keras dot layers dot dense. Okay, so this D should be in caps, and keras dot layers. So the third one is my output layer. Okay, so we are creating one input layer, one hidden layer, and one output layer. Okay, so dense means all the neurons in that particular net layer is connected to all the neurons in the previous layer. So if you see this, so if you see this neuron alone, so we are getting the data from all the other neurons in the input layer. So we have three neurons in the input layer. So this neuron gives its output to this first one, and this second one also gives its input. This third neuron also gives input to the this particular neuron. So this will be carried on for all the other neurons as well. So if you think about this four neurons, all the four neurons will get the input from all the three neurons in the previous layer. So that's what dense means. And flatten. So there is an interesting thing about this flatten. So whenever we are training our machine learning model, we will feed this X train and Y train directly to our model, right? So if you think about this X train, it is in the form of a matrix, right? So this matrix contains 569 rows and 30 columns. But whenever you are training a neural network, we have to flatten this. Flatten in the sense we have to convert this into a single dimensional array. So this is very important. Okay. So each feature will go to one neuron. So if you think about this particular data set, so we have 30 features. So each feature for each feature we will give one neuron in the input layer. So there is not much function or not much work that has been done in the input layer. So this is just used to pass the value to the next hidden layer. So the number of the number of neurons in your input layer is equal to the number of features that you have in your data set. So this is like specific for numerical data set alone. For image data, this is like slightly kind of different. So we will deal that with deal that at a later time. But again, I hope that you understand the purpose of this flatten is to convert the data into a single dimensional array. And here I need to mention the input shape. So in this input shape, mention the number of columns that are there in your data. Okay, so 30 comma. So this is how you need to mention. So if there are 10 columns or 10 features in your data, then you have to mention 30. And the important thing is that this doesn't contain the output, which is my target. So this is the number of features alone. So input shape is equal to 30. So this particular flatten layer will flatten our data and it will convert it into a single dimensional array. And the next one is my hidden layer. So in this hidden layer, let's say I want 20 neurons. Okay. And the next important thing that we need to mention is the activation function. So activation is equal to ReLU. So ReLU stands for rectified linear units. And finally, my output layer. So in my output layer, I'm going to have two neurons. And here the activation function is equal to sigmoid. So sigmoid is just like the logistic regression function that we have. Okay. So in this hidden layer, I have mentioned 20 neurons. So in this image, we have four neurons in the hidden layer. So we have one hidden layer, we have four neurons. So in this case, I am mentioning 20 neurons. So you can give different number of neurons and you can check how the model is working. So in this case, I'm just giving 20 neurons and the activation function is ReLU. Whereas in the output layer, I am giving the number of neurons as 2. So this is like very specific. You should not give any other values. The reason is the number of neurons that you are giving in this output layer is equal to the number of classes that you have. So if you just go through this data, we have two classes. One class is 0 and the other class is 1, right? So the number of I'm just repeating this again. So the number of neurons in the output layer is equal to the number of classes that you have. If you have three different classes, in that case you will be creating, this number will be changed to 3. Sorry, so this will be changed to 3. If you have 10 classes, in that case we have to convert this to 10 and so on. So in this case there are two classes, hence we are creating this two. So this is like very important for us. So what happens is, let's say that this is the two neurons that we are creating. So let's say that when the output is 0, this will give us the signal as 1. So when the output is 1, this will give us the 1. So like a specific neuron will fire for each label. Okay, so I'll just take an example. So let's say that the output that our model is predicting is 0. So 0 basically means malignant, right? So if I go there, okay, so 0 means malignant. So this particular neuron, so this particular neuron will give me the output. So this will be blank. When my output is 1, that means benign, right? Then this neuron will give me the output. So that is the idea. So this is what we call as firing of neurons. And when one neuron is firing, the other neuron won't be active. So like firing in the sense the output will be 1. So that is the idea. So that's why we are creating 2 neurons in the output layer, which is equal to the number of classes that we have. So we are creating this flatten array, or this flatten layer, in order to convert our data into a single dimensional array. And then we are creating a hidden layer with 20 neurons. And finally we are creating the output layer with two neurons, as we have 2 classes. So this is my model, and I'm stacking all these layers using the sequential function from Keras. So I'll run this. The next step is we have to compile this array. Okay, so I have to put a comma here, so I missed this one. Okay, so let's run this. So this will create my create the structure for this neural network. Now we have to compile this neural network with some factors. Okay, so this is a very simple neural network, as I've told you. So this is a very simple data set. So it will, this particular network will work fine. So if your data set is complex, and in that case we probably have to add several neurons and several layers to our neural network. So if you want to add another layer, so what you will basically do is you will again add keras.layers.dense, and so I'll just copy this one. So you will just put this one. So keras.layers.dense, 20 neurons ReLU, right? So I will just add this here, and I can just change this neurons to maybe 30 or 40 or whatever it is, and I can just change this ReLU to sigmoid. So now this particular neural network has 2 hidden layers. So this is how you can add a new layers to your neural network. And again, there are several activation functions like sigmoid, rectify linear units, which is my ReLU, and there is other activation functions called as leaky ReLU and so on. So we will discuss the theoretical part and how these things work on all those things in the deep learning course. So this video is purely for implementation part. So understand that for each layer and for each neuron, we have to mention the activation ReLU. So it is not that we have activation function for the entire layer. So it is not that. So each neuron will have an activation function. Okay. So when I mention ReLU, all the 20 neurons in the hidden layer will have the activation function as ReLU. And when I mention sigmoid, all the neurons in the output layer will have the activation function as sigmoid. So that's the idea. So after this, we have to compile our neural network with factors like optimizers, loss, etc. Okay. So this part will be compiling the neural network. Okay, so for this I'm going to use model.compile. Model.compile, and this model is nothing but the keras.sequential that we have built. So in this I'm going to mention my optimizer. So first one is my optimizer. So here I'm going to use my Adam optimizer, and the loss that I'm mentioning here is sparse categorical cross entropy. Sparse categorical cross entropy. Okay, so this is the loss. And finally, I'm going to use the metrics as accuracy. Okay. So this is my accuracy. Okay, so this is compiling part. So we are setting the optimizer to Adam optimizer, loss function as sparse categorical cross entropy, and metrics as accuracy. So again, there are several optimizers and several loss functions that we have. So you can again do some research on what is meant by this Adam, what is meant by this sparse categorical cross entropy, and so on. So I'll explain all these things while we are working on our deep learning course. So please do some research on this part. I'll just give you one idea. So whenever you're using the target variable as 0, 1, 2, 3, and so on. In that case, we have to use sparse categorical cross entropy. And when you have one not encoded labels, in that case, we will use categorical cross entropy. So we won't use sparse. So one not encoding in the sense, let's say that there are three objects. Okay. So let's say that we want to build a neural network that will predict whether an image represents dog or a cat or a horse. So let's say that we are labeling this dog to 0, and we are labeling cat to 1, and we are labeling horse to 3, sorry 2. So these are all the three labels that we have: 0, 1, and 2. So whenever you are using the target variable as this kind of integer labels, so in that case you will use the sparse categorical cross entropy as your loss function. Whereas if you use one not encoding, so how one not encoding will look like is, so just create a text cell here. Okay, so if it is a dog, I will mention it as 1, 0, 0. If it is a cat, I will mention it as 0, 1, and 0. If it is a horse, I will mention it as 0, 0, and 1. So this is what is called as one not encoding. Okay, so you can see, if it is dog, the first value should be 1. If it is cat, the second value should be 1, and the other value should be 0. If it is horse, the third value should be 1. So this is what we call as one not encoding of labels. So if we have multiple labels, when there are 10 labels or 20 labels, in that case we probably will go with one not encoding. Whereas in this case we just have two labels, right? So benign and malignant, so we can just go with this numerical kind of encoding called as label encoding. So whenever you are going with this normal label encoding with the 0, 1, and 2 as your label, we will be using sparse categorical cross entropy. And when we are using this one not encoded labels, in that case we will just use this sparse categorical cross entropy. So this is like two kinds of loss functions. Similarly, there are other loss functions as well. So you can just go to the Keras documentation of this loss function, and you can do the research on it, so you will get some idea. So this is the compiling part of this model. So I'll just run this one. So we are creating input layer, output layer, and one hidden layer, and we are using the Adam optimizer and sparse categorical cross entropy as the loss function, and the metrics used is accuracy. Now we need to train our model. So this part is training the neural network. Okay, so it is just similar to machine learning. So in machine learning we use this model.fit, right? So similarly we will use this model. So model is my neural network that I am building. So model.fit, xtrain, and ytrain, and I'll set my validation split to 0.1, and epochs is equal to 10. Okay, so we are feeding my we're feeding this xtrain, ytrain, validation split, and epoch. So validation is just like the train test split we are doing on. So while the model is training, it will do the testing on this validation itself. So it is just like train test split. So we have xtrain, ytrain, validation split as 10% of the data. Epochs is equal to 10. Epochs is like how many times your model has to go through the data. So that is the epochs. So xtrain is my features, and ytrain is my labels. Okay, so which we have splitted from this xtrain, this train test split function, and so on. So when I run this, this will train my neural network, and I will see what is the loss at each epoch and what is the accuracy at each epoch. And before doing this, I'm going to create another variable called as history is equal to model.fit. The reason is, so we will be plotting the loss value and accuracy value while the training has been going on, and for that we generally use this variable name called as history. So this is just like the convention that we use while training the neural network. So I'll run this. So this model will be run for 10 times, which is the 10 epoch. So there is some error that I'm getting here. So let me just go through it. User code, unknown loss functions. Okay, so I just made a spelling mistake here. So it's sparse. Okay, so I'll set my model.sequential again. I'll compile this and let's train our model. Again, I'm getting an error. So unknown metric function called as accuracy. Okay, so I'm just making several mistakes today. So accuracy, I hope everything is fine now. Let's see. Yeah, now our model is training. So when the model is running for the first time, the loss function that we are getting is 23, which is a very huge loss function. And the accuracy on training data is 0.22. And the validation loss function is 20, and this is the validation accuracy. So we have training data loss, training data accuracy, and this is the validation loss, validation accuracy. So if you see this, we have 10 epochs, and at each epoch, the loss function is decreasing and the accuracy score is increasing, right? So we have started from 22.7 percentage accuracy to 78.73 percentage accuracy. Now, when we use a logistic regression model for this particular data set, the accuracy is kind of more than 90 percentage, whereas in this case we are getting 78 percentage accuracy only, and the validation accuracy is 86.9. So this is like pretty less for neural network model, right? The reason is we haven't standardized our data. Okay, so if you see this, the data will be in different ranges. We don't apply, we didn't apply the standard scalar function, and that is the reason why we are getting this low accuracy. And now I'm going to apply the standard scalar function to my data. Okay, so that should be done after splitting our data to training data and test data. Okay, so this is very important, so we should not do this before splitting into training data and test data. So like I've seen like few people have asked me that even if I standardize the data and even if I don't standardize the data, the accuracy is kind of similar in some machine learning models. So I've mentioned that in some cases this will be a huge difference. So in this case, now we will see that first time that if we apply this standard scalar function, the value will increase, the accuracy value will increase. So this part of the code will be to standardize the data. So we have done this before actually. Okay, so standardize the data, and for this we'll be using the function standard scalar, which is in sklearn dot pre-processing. I'm going to import standard scalar. Okay, standard scalar. Now I'm going to create a variable called a scalar, and this is where I will load the instant of the standard scalar function. And I'm creating a variable called as xtrain standard, which is equal to scalar dot fit transform. So this is very important, so I'll just explain you after doing this. So fit underscore transform xtrain, and after this we will create a new variable called as xtest standard. So this is the standardized training data and this is the standardized test data, is equal to scalar dot transform xtest. Okay, so let's try to understand what we are doing here. So we are loading the standard scalar function. Now we have to fit our data, which is our training data, to this xtrain, and then we have to transform it. Okay, so instead of like doing this, I'll just do this in this form. Okay, so it is actually the same, but you will understand this better. So xtrain standard. Okay, let me just put it together as well. So fit transform. Okay, so what basically we are doing here is once we load the standard scalar function, we have to fit this model to the standard scalar, which is named the scalar, and then we have to transform our data. So we are fitting the data to our xtrain, and then we are transforming this data and we are storing this in xtrain. And we are, based on this scaling, we have to transform our xtest data. So the main thing that you need to remember here is you should not fit your data to your test data. So that is wrong. You have to fit it to your training data alone. Okay, so we are fitting and transforming the data of the training data, and then we are using the same scalar to transform our x data. So this is how it works. Now I'll run this one. Now you can print this train standard if you want to, and you can just see how this data is looking like. So I'm just printing train standard. Okay, so there is no reason, like there is no requirement to transform y train and y test because it is already in the form of 0 and 1. So we don't have to do that on that one because it is a categorical variable. So I'll just print this train standard. Now all the values will be in the form of similar ranges, so which is what we need. So I'll just remove this one. Now in while training our model, instead of giving this X-train and Y-train, we will give this X-train standardized data. So that will give us better results. So I'll run this model is equal to keras.sequential again. So my model will be set up, and I'm compiling my model. And while fitting, instead of using this X-train, I'm going to use this X-train standard. Let's see whether there is any change in the accuracy score. So you can see the accuracy starts from 0.22, which is 22 percentage, all the way up to 78 percentage. Now we are training it with the standardized data. Now, so previously the starting accuracy was 22 percentage. Now we are getting the starting accuracy as 44 percentage, and the accuracy increases up to 95.8 percentage. So you can, if you want, you can just increase this epochs, or you can increase the number of neurons, and you can also add another layer to your neural net. So you can just basically play with. So I've just created a simple neural network with one hidden layer. So you can basically increase the neurons and increase the layers, but just make sure the model doesn't overfit. So that is a problem which we will discuss later. But yeah, so you can also set this epochs to 20, where the model will go through the data 20 different times. So here again you can see the loss function starts from 0.76, whereas previously it starts from 20. So loss function is basically what is the difference between your true value and your predicted value. So this difference should be minimum. So while training any machine learning model or deep learning model, our goal is to reduce the loss value and increase the accuracy value. So if loss value increases, the accuracy value will decrease. If the loss value decreases, accuracy value will increase. So they are like inversely proportional. So you can see the loss value kind of decreases at each epoch, and the accuracy value increases at each epoch. So this is the validation loss and the validation accuracy. So this is how you can train your neural network model. And the other standard thing that we usually do is visualize how this loss function value changes, and the accuracy value changes. So for that, we will just create some basic plots. So I'll create a text here as visualizing accuracy and loss. Okay. So PLT, which is my matplotlib library that we have imported in the first cell. So PLT dot plot history dot history. Here I have to mention accuracy. Okay, so my accuracy, and then plt.history. Let me just copy this. So we will visualize this loss and accuracy, loss accuracy, and validation accuracy. So I'll put this one. So here I'll just change this to validation accuracy. So I'll just explain you after completing this part of the code, and then we are giving a title to our plot. So let's name this plot as plt.title. Let's name this as model accuracy. Model here is the neural network accuracy. Okay, so model accuracy will be the name of the plot, and plt.y label. So the name of the y-axis will be again. So let's call this as accuracy, and plt.x label, it will be epochs. Okay, and we are going to set legend for this plot. So plt.legend, and this legend will be train val. So val basically stands for validation, and where do you want this? Location is lower right. So I'll put this as training data, and this as validation data. Okay, so I hope everything is fine. So history is nothing but, so this is where we have stored all the checkpoints of the model. So history accuracy. So let's run this. You will understand what we are doing here. So what it basically do is, it will take this model's accuracy. So this is the accuracy on the training data. This is the accuracy on the test data. So it will take each of these values, and it will try to plot it. Okay, so here we have the epochs number. So this is when the model runs for the first epoch, second epoch, third epoch, fourth epoch, and so on. So totally we had 10 epochs. So like in the first epoch, if you see, the loss value is 0.7. So if you see, sorry, we have to look at the accuracy. So accuracy is 44, almost it's 45 percentage or something like that. For first epochs, it is somewhere here. The accuracy is, accuracy is, I think we have to look here. Okay, so let me just check it for this second one. Okay, second one, the accuracy is 0.78, so it's 78 percentage. 78. So I think it's kind of different. So training and validation. So let me just recheck it. Epochs history. Okay, so the thing is, the first epoch has been numbered as 0, second epoch has been numbered as 1, so 2 and 3. So you will have epochs from 0 to 9, which counts for 10 epochs. Okay, so for the first epoch, so this is represented, this particular epoch is represented as 0, and for this the accuracy is 0.44 percentage, which is 44 percentage. So if you see here, we have the value at this point, which is 44 percentage, and this is basically the third epoch, because like 0, 1 and 2. So for this we have to look at the third epoch is about 89 percentage. So if you see here, the training data accuracy is almost here, which is equal to 89 percentage. So epoch starts from 0, 1, 2, 3 and so on. So this is the basic numbering in Python. So just, yeah. Okay, so that is the thing. So blue color line, this blue color curve tells me how my training data accuracy changes. So it changes from 44 percentage to 95 percentage, and this orange colored line tell me what is how is my validation accuracy changes, 0.71, 0.95 and so on. So this is just basically how my accuracy changes. So it starts from very low accuracy of 44 percentage, and it kind of getting, and after a point it kind of reaches a plateau, because like it reaches 91 percentage and 93 percentage in the fifth epoch itself. So in the next 10 epochs, it goes to 95 percentage. So the maximum accuracy we have is about 100 percentage, which will be in the form of 1.0. Now this is what we are creating. So when I mention this history accuracy, so this value will be taken, and when I mention validation accuracy, this one will be taken. And we are just naming the plot, which is model accuracy, and we are creating the y label as accuracy, x label as epoch. So we are just plotting for epochs and accuracy and the legend. So I just wanted to mention that this blue color curve represents the training done on the training data, and orange color is this validation data and location. So if you change this location to upper right or upper left, this location will be changed here or here based on your value. So this is the plot we are doing, and we also used to do this for the loss value as well. So I'll just copy this code, so it will remain the same. We just need to change this to loss, and this will be validation loss, and let's name this as yeah, so model loss, and this is loss value. Okay, so training data, test data. So here let me put it on upper right corner, so you will see the change in the location. Yeah, so if you see the first epoch, which is 0, the loss function value is 0.76, right? So if you see here, 0, the training data loss function is 0.7 and so on. It kind of decreases, so on. So the accuracy starts from a low point and it increases, and the accuracy kind of decreases, which we are more interested in. Okay, so the final accuracy that we are getting is for training data it's 0.15, and for validation data is 0.12, so which is at this point. Okay, so this is how we will visualize how the loss function and loss function value and accuracy value changes. So this is how we can visualize this, and now we can also do some certain things. So the next, we just have two more works to do. One is to test our neural network on the test data that we have created. So we have done all these things on the training data, but then we have to do this for this test data that we have created, which is this X test, which we have standardized to X test standard. Okay, so after that we'll be building a predictive system. So let me do those as well. So this part of the code will be to get the accuracy value, accuracy of the model on test data. Okay, for this I'm going to create two variables called as loss and accuracy. So there is a function in this keras sequential, this keras model, which is called as evaluate. So model, which is my neural network dot evaluate, Here I have to give my X test data and the corresponding labels. X test standardized. So this is just like predicting the accuracy score of the model, which we used to do for machine learning case. Okay. So what happens here is, so we will feed this X test standardized. So the neural network will predict the label for all this test data, and it will compare it with this Y test, which is my true data. Okay. So this is just like the calculating accuracy score. So we don't have to do all those things. We can just use this evaluate function. The model does it by itself. So I just repeat this. So the model will take the standardized X test data, which is my testing data. It will predict the labels, and those labels will be compared with my true labels called as Y test, and it will give me two values. One is the loss value, and the another one is the accuracy value. And let me print the accuracy value alone. Print accuracy. Okay. Okay, again I'm making a mistake. Okay, so accuracy. Let's see. So here the loss function value is about 0.16, and the accuracy is 0.938, which basically is 93.8. So we are almost getting a test data accuracy of 94%, which is very high. So if you increase the epochs or if you increase the layers, we probably get some increased accuracy. So you can check that out, but it is not like that much important for us. Now what we are going to do is the most interesting part, which is to build a predictive system based on this neural network. So this is just like, this is slightly different from how we used to do for machine learning model. So there is like few steps that we need to include. So here what I'll do is, I'll just print X test standard dot shape, and I'll print the first value of this X test standard. Print X test standard. When I mention 0, this is the first data point in this test data. Okay. So there are 114 test data points, and then we know that there are 30 columns, right? We have printed this here. So 20% of the original data, 114 goes to the test data and 30 values. The difference is that this data has been standardized here. So we have 114 data points and 30 columns, and this is my first data. So see, like this, there are 114 data points are there. Now when I use a predict function in this model, so we are just basically working on classification, right? So I'll create a variable called as ypred. And in this ypred, I'm going to use model.predict. Model.predict X test standard. So when I run this in machine learning, it will give me either 0 or 1, right? It will predict the class, whether it is, if it is benign, it will give me 1. If it is malignant, it will give me the 0. So I will get those classes alone as 0 or 1. But in this case, it is slightly different. Let's see what we are getting. So I'm going to print ypred shape dot shape. So this will basically calculate, or this will find the label for all the data points. So ypred dot shape and print ypred 0. Okay, so let's see what happens here now. So what we expect is similar to machine learning. If I run this, it will give me either 0 or 1, but it is kind of different here. So it is giving me two values for one data point. Okay, so this is the prediction. For prediction of this X test, this X test standardized 0 for the first data point, I'm not getting the label value as 0 and 1, but I'm getting some value like this. Let's try to understand what is this. So when you run this predict function, it will give me what is the probability that the label is 0, and this value represents what is the probability that the value is 1. Okay, so in other words, this is the probability of that this particular data point being 0, which is like 0.24, and this is the probability of this data point being 1. So in other terms, we can say that the model is 24% sure that this data point represents malignant data, but it is 53% sure that this particular data point is benign data. Okay, so the first value represents the probability of label 0, and the second data point represents the label 1. So this is very, very important. So it won't give you as either 0 or 1, but it will give you the probability. So we will basically choose, like if the first value is maximum, then that label will be 0. If the second label, like the second value is maximum, we will choose this one as 1. Okay, so let me just print this ypred shape. ypred shape, or okay, so I'll just print all these things. So print ypred. Okay, so here we will print the x test standard. Okay, so this is the test data, and this is the values predicted by my model, which is stored here. So model.predict extents. So this, I'm just printing my test data, which contain 114 data points. So there are like 114 data points here, and then I am printing my ypred. Let's try to understand this. So this will basically contain 114 different values, and for each value you will have two things. Okay, so we just have to compare the first one and second value. So this is for the first data point, this is for the second data point, and this is for the third data point, and so on. So similarly we have the two values for each of the data point. So if the first value is maximum, we will tell the label as 0. If the second value is maximum, we will tell the label as 1. So for this one, if you compare, the label value is maximum for this one, so we will tell this is the maximum one. For this is the maximum one, and so on. So this is, instead of giving us labels, it will give us what is the probability that this data point can be 0, and what is the probability that this label can be 1, and so on. Okay, so this is how it works, and we need to convert this to labels. So we don't want this probability value, but we want label values, and for that we will be using np.argmax. So there is a function in numpy library called as argmax, so we'll be using that. So I'll just put this thing here as model.predict gives me, so it gives the prediction probability of each class for that data point. Okay, so if I consider the first data point for this, so this is my first data point, and model tells that this, for this 4 data points, there is like 2.4, like 0.24 probability that it will be 0, and 0.53 probability that it will be 1. So it will choose the maximum one. So if the second value is maximum, it will choose as 1. In this case, second value is maximum, so we will get the label as 1. And another important thing that you need to note here is, it is not that if you add these two things you will get the value as 100. So it is not like that. Okay, so it is not like if you add these two you will get 1. So it is not like that. It is just some, you can think this about some confidence value of the model. So which value is higher, we will take that particular label. So we have to determine this. Okay, so I'll just create a text here as converting the prediction probability to class labels. Okay, so to either 0 or 1, which is like more we can understand that better, right? So I'll create a text here as ypred labels. So we are just converting these values to labels, is equal to np.argmax. So we are going to use a for loop. So np.argmax of I for I in ypred. So let's try to understand how this argmax works. So I'll just create a, so let me just put it here. Okay, so argmax function. So let's try to understand this first and then move on to that part. So I'll create a list as my list. So this list contains the values as 10, 20, and 30. Okay, and I'm going to say, let's say that I want to find the index of the maximum label. So index of maximum value, index of max value is equal to np.argmax of my list, and I'm going to print my list as well as, and I'm going to print the index of maximum value. Now let's see what is the output that we are getting. 2. So we know that the index of 10 is 0, index of 20 is 1, index of 30 is 2, right? So np.argmax will try to find what is the index of the maximum value. So in this, the maximum value is 30. and the index of this maximum value is 2, right? So that's why we have the 0, 1, 2. The maximum value is present in 30. If we say that I have 30 here, 10 year and 20 year, now the Rmax value should give me the value as 0, right? Let's see. So it is giving me the value as 0. So this is how this works. So if I say that in my list the values are 0.56 and there is another value as 0.25, so it should give me this particular value as 0, right? Let's run this. So it has given me the value as 0. So let me just reach, just put this here. So yeah, okay, I'll put this here. Now you can see. So this is how this basically works. So we will take each of these list and we will try to find whether the first value is maximum or the second value is maximum. If the first value is maximum, I want to give the label as 0. If the second value is maximum, I want to give the label as 1. So this is just very simple, very basic. So that is what we are doing here. So I'm creating this wipe-read list. So here we have just done this for one single list, whereas in this we are going to create a for loop where this for loop will iterate over all these lists. Okay, so each of this represents one test data point. So totally we have 114 data points. So all these values will be converted into 0 or 1 depending on which value is maximum. So that's why we have this for I in wipe-read. So when this for loop runs for the first time, it will take the first value and it will apply this Rmax to determine which value is maximum. For the second time the for loop runs, it will take this value and Rmax will be run and so on. So this is what is done, and all these labels will be stored in this list called as wipe-read labels, because you can see we are creating this square brackets which basically represents my list, and after this I'll print my wipe-read labels. Wipe-read labels is what we are creating here. Okay, so let's run this. So this is the value we are getting. So if you just print this, so if you just compare this wipe-read and wipe-read labels, for the first value, for this first data point, the second value is maximum, right? So the label should be 1. You can check this one. So label is 1. Again, so 1 means second value is maximum, second value maximum, 0 means first value is maximum, and so on. So this is how we can convert this prediction probability to class labels, and in machine learning our model directly give this kind of values because we have classification from model separately, but in neural networks we can do this one in order to convert our labels. So this is why the prediction, building the predictive system changes, because we have to incorporate this as well. So this part will be building the predictive system. Okay, building the predictive system, and for this we have to create the input data. Input data is equal to some tuple. So in this we need to give the feature values. So these 30 values, if you give this 30 values, you will get some result. And next thing is we have to change this to numpy array so that we can reshape this array and so on. So input data, so I have to include an underscore here, input data. Next step is change the input data, which is form of a tuple. So you can also create this as a list, so that is not a problem. So we have to change the input data to a numpy array. Okay, and input data as numpy array is equal to np.asArray, np.asArray. Okay, so as array input data. Okay, so this will change this tuple which is in this brackets to a numpy array, and after this we have to reshape the array. So reshape the numpy array as we are predicting for one data point. Okay, so the reason is while training our model we have fed it with almost 500 data points, but we have to tell that model I'm just predicting the label for only one data point. So that's why we have to reshape this data point. So it will be given as input data. So let's create this name as input data reshaped is equal to mention this array which we have converted dot reshape function. So reshape, we have to mention 1 comma minus 1. Okay, so this is the reshape that we do in order to tell the model that I am predicting the label for only one data point. And after that we have to standardize the data. So don't forget that here we have, before training the model, before training our neural network, we have standardized the data using the standard scalar function, right? So using the same scalar which we have fitted with our xtrain, we have to transform this data. Okay, so once we transform this data, input data reshaped, input data reshape, and standardizing the data, standardizing the input data. So I'll call this as input data. So if you do this without standardizing the data, it won't work. Okay, so this is like very, very important, and this order is also important. First you have to convert it to a numpy array. After that you have to reshape it. After that only you have to standardize it. So if you apply the standard scalar before this reshaping, it won't work. So scalar dot transform, here you should not fit it, you have to transform it, because like we have to fit it only with the training data. So scalar dot transform input data standard, scalar dot transform input data reshape. Okay, and finally prediction is equal to model dot predict. So please remember that this predict will give us a prediction probability and not classes as either 0 or 1. So model dot predict input data standard. So I'm putting it here, and then let's also print this one to see, print prediction, and finally prediction label. So this is in the form of a probability value. So we have to again apply this np.argmax in order to convert this probability value into class as either 0 or 1. So I'll create this as a list called np.argmax, argmax of prediction. Okay, so it is the same step that we are doing. So in this case we have done this for all the data points, but we are just doing this for only one data point. So that's why we are not including this for loop. And I'll print this as well. So let's print this prediction label as well. Okay, so that is done. So that is all we need, and then we can just include a simple if loop that we used to do. So if this prediction label, so if prediction label 0, which means the first element, so it will be basically in the form of list. So if this element is equal to 0, in that case we have to say that the breast cancer is, we can say that the tumor is malignant, whereas else means the label will be 1. So we know that 1 means it is it is benign, right? So print the tumor is benign. Okay, so we are using the trained neural network in order to, we are doing this if you want to predict the value for a new data point. Okay, so if the label is 0, then it will say that that particular tumor is malignant. If the label is 1, it will tell that it is benign. So there is like nothing to worry and so on. Okay, so now we have to put some value to this input data, and we have to predict whether it is benign or malignant. So I just take one data. Okay, so let me go to the CSV file that I have. So this is the data that is downloaded from the Kaggle. So it is the same breast cancer data set. I'll open this with Notepad. Okay, so you can see, so M means it is a malignant data point, and you can see B. So B means a benign data point. So I'm going to copy one malignant value. So if I put this, the model should say that it is a malignant tumor. So I'll copy this. Let's put that there. So this should be pasted in input data. So it should tell that it is a malignant tumor. Okay. So let's run this and see whether our model is predicting correctly. Okay, so it is saying that the tumor is malignant. So now you can see, so this prediction, so this is nothing but the prediction that we have printed here. So it is saying that it has two values, which is 0.67 and another one is 0.16. So if the first value is maximum, we have to say that the label is 0, right? So hence why it is giving 0. So this 0 is derived from this np.argmax. Okay, and as the label is 0, it will say that it is malignant. And now let's do the same for benign cases. So I'll go and randomly copy some value. So this is a benign case. You can see the B here. So I'll copy this data point, which is the 30 values. And let me put, now it has to say that the label is 1. The second value is maximum. It should say the tumor is benign, right? So I'll put this here. And let's run this. Now you can see the second value is maximum 98 and the first value is minimum, which is 42, and we are getting the label as 1 and the tumor is benign. So this is how you can build a predictive system using this neural network. So the only difference is that you have to use this np.argmax and you have to scale this before scale this after reshaping. So I hope everything is clear now. I'll just give you a quick recap of what we have done so that you just get the whole idea. So we are just importing the necessary dependencies that we need. So the libraries like NumPy, Pandas, sklearn, etc. So Matplotlib for plotting the loss function, the accuracy function, and we are loading the data from this, sklearn.datasets. So after that, we are creating a data frame where we are adding all the data from this dictionary, which like in this dictionary called as breast cancer dataset, and in that we are getting this data alone, which is the feature values. After that, we are adding the target column and we are naming the target column as label. Okay, so now if you see the last, there is a last column added called as label, which is my target column, and you can print the shape, which is 569 rows and 31 columns, and then we are checking the info as whether there are any missing values, if there are any null values, and so on. And after that, we are just printing this description. So these are just data analysis part. We are checking the distribution of the classes, how many one values are there, how many zero values are there, and then we are grouping the data points based on their labels. Next is separating the data into features and target to this X and Y. After that, we have splitted our data into training data and test data using this train test split. So 80% of the data, which is 455, goes to my X train, and 20% 114 goes to my X test. After that, we are using the standard scaler. So this is like very important in deep learning. So we have seen that if you don't standardize your data, you will get less accuracy, and if you standardize your data, you will get better and higher accuracy. So that's the idea. And here we are building a very simple neural network. So there is like a lot of things that we have to explore, and I will do that in while taking the deep learning course. You can also do some research on this. So we are importing this tensor flow, and we are setting the seed so that we get constant results every time we train our neural network. So model, we are using this keras.sequential, where we are stacking all the layers. So we have flattened layer in order to convert all the data, which is in the form of a matrix, to a single dimensional array. And after that, we are creating an input layer and output layer with two neurons. You can try this with different, so you can just give the activation as sigmoid for both the things, or you can give activation as reduce. So you can just interchange. You can do some explorations on that part, and also check what are all the different activation functions are there. So you will find all these details in Keras documentation. Just search as Keras activation function or Keras optimizer loss and so on. So we have Adam optimizer. Since we have the labels as 0 and 1, we have used a sparse categorical cross entropy. If we have one not encoded labels, in that case we have to use categorical cross entropy. And the metrics, so as we are choosing the metrics here, we are getting the accuracy. So we are getting the accuracy here. So if you choose different metrics, you will get different accuracy here, and so on. So here we are creating a variable called as history, so that it saves all the checkpoints of the training. So we are using this fit function to train our standardized training data with along with the labels, and we are setting up the validation split. So how many validation data points are there, and setting the epochs, how many times the data has to the model has to go through the data. And you can see, so at each epoch the loss is decreasing and the accuracy is increasing, which is what we need. And then we are visualizing how the accuracy and loss changes. So we have epoch 0 to 9. So 0 means the first epoch, 9 means the 10th epoch, and so on. Again, we are seeing the loss function value. So the accuracy starts from a low point and it reaches a higher value, and loss function starts from a larger value and reaches a small value. And then we are finding the accuracy on the test data as almost 94%. And the main thing is, we can see that when we use this predict function, instead of giving us the labels, it will give us the prediction probability, and we have to use this np dot argmax in order to find which is the maximum value, and we are just converting it to list. And after that, the important thing is building this predictive system where we have to take the value, we have to reshape it. After that, so first is taking the input data, converting it to numpy array, and after that reshaping this numpy array, then we have to standardize this data and then predicting whether that particular uh, the predict value, which is my probability, and in that we have to use the np.argmax function and find the label. Here we are getting the label as 1, and finally we can say that if this label is 0, we have to print it as malignant. If the label is 1, we have to print as malignant. So that is what we have done. So this is a very, very simple neural network. So there is a lot of things that we can do with this. So what you can do is, so try adding the layers, and you can also see there is a chance that this model will overfit. Overfit is the thing when your training data accuracy is high, like 95%, but your test data accuracy will be low, like 50% or 60%, and that is what is called as overfitting. So if you add more number of layers, there is a chance that your neural network may overfit. So you can explore that part, and you can also explore what are all the different optimizers and loss functions that you have. So these are all the two things that you can explore. I just wanted you to explore, and in the upcoming videos I'll post a video on how image processing works in deep learning. So how we are converting this image to numerical value. So that I'll create a separate video, and after that we will work on few image data sets, so image recognition problems using deep learning. And after that, I'll just continue with the machine learning videos. The machine learning course videos are there, and once in a while I'll upload deep learning projects like this. I hope you have understand this particular video. So like watching this video is not enough. Please try to write all these code by yourself. At least just keep this code aside, just try to write all this code by yourself. So then only you will get a clear idea, and you can just use this as a template, and you can work on different numerical projects. And so in our channel itself, I have worked on several classification problems with numerical data. So for those data sets, you can apply this neural network and see what is the result you are getting. So that will be a good exercise. So please practice all the codes. So just watching the video won't help. Okay. So I hope everyone is happy with this video, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. This is the second deep learning project video in our channel, and in this video we will be working on the MNIST handwritten digit classification using neural network. This is one of the basic and important use cases in deep learning, and this is an image recognition task, and working on this will give you an idea of how to handle image recognition projects. So let's get started. So first of all, let's try to understand what is the workflow that we have in any image recognition problems, and as well as in this MNIST handwritten classification. So first is about data collection. So first we have to get this data set. So this particular data set is available in Keras itself. So in case you are working on some other image recognition task, you can search for the data set in Kaggle. Or if you are working in a company where you have to build this deep learning system, they probably will tell you an idea of where you can get that particular data. So the first part is collecting the appropriate data for your particular use case, and the next one is to process the image data that you have. Okay, so so we have seen like what are all the different image processing that we have to do in the previous video. So we have seen that what does the dimension of an image means, and we have seen what is meant by this pixels, and we have also seen that there are RGB images and grayscale images and so on. So the steps involved in image processing are, so in case you have images in different dimensions, so the one step would be to resize all the images to a common dimension. So that is one of the steps. And after that, in some cases, we will try to convert this RGB images to grayscale images. So you can consider this RGB images as colored images, and grayscale images as the images, a black and white image which has only one color channel, and so on. So these are some of the image processing tasks that we have. And once we have these images, we have to build the labels for these images. So once we have this image data as well as the label, we can split this data into training data and test data, similar to how we do this in any machine learning task. Okay, so we will train our neural network with this training data, and we will evaluate our neural network with the test data that we have. Okay, so once we have trained our neural network, so we will feed this data to this neural network, and this neural network will be trained on the data set that we have. So in this case, our goal is to give an image, and the neural network should tell us what that particular digit is. Okay, so the different digits that we have are from 0 to 9. Okay, so these 10 numbers, 0 1 2 3 all the way up to 9. So this is like a single digit detection neural network. So you can think about like that. Okay, and once this neural network has been trained, if you give an image of a new image, or the image that contains some number, it kind of recognizes what that particular image is. So this is what we are going to do in this MNIST handwritten digit classification problem, where the ultimate goal is, if you feed an handwritten digit, this trained neural network should tell you what that particular digit is. So this is the idea, and so this is the process we will be following. Okay, so once we train this neural network, once we evaluate it with the test data, we will build this predictive system where if you feed the image, it will tell you what that particular digit is. Okay, so let's get started. And so I'll just open my Google Colab now. Okay, so this is the MNIST handwritten classification problem. So the first step will be to import the dependencies that we need. Okay, so dependencies are nothing but the libraries and the functions that we need. So I'll make a text here as importing the dependencies. So if you haven't worked on any deep learning projects, or if you haven't trained any neural network, like you can understand this particular video, because I'm going about all the basics that we have. So don't worry if you haven't worked on any deep learning use cases. So first I'll import the NumPy library. So I'm importing NumPy as NP. And the next thing I'm going to import is the matplotlib library. So import matplotlib dot pyplot as plt. Okay, so this numpy library is very important in deep learning projects, because we have seen in the previous video itself that we will convert the image data into numpy arrays. So we need this numpy library, and then we have this matplotlib library. So once you have this numpy arrays, we can visualize this image so using this matplotlib plots. So once you feed that numpy array to the plots of matplotlib, you can see what that particular image is. Okay, and the third library that I'm going to import is cbound. So this is also useful for certain plots. So I'm going to import cbound as SMS. And the next library will be CV2. So CV2 is nothing but the OpenCV library. Okay, so this OpenCV stands for computer vision, and this is one of the important libraries that we have when it comes to image recognition tasks. Okay, and the next thing that I'm going to import is from google.colab.patches import CV2 I am sure. Okay, so this CV2 I am show function is just used to show an image, to display an image. So this is actually a function that is present in this OpenCV library, but Google Colab doesn't allow you to use this particular function that is available in the CV2. Okay, so instead of that, so they gave an alternative in this module google.colab.patches. Okay, so from this we can import the CV2 underscore I am show. So like if you are working on Spider or PyCharm, so you don't have to do this. So you can import this, or you can work on this like cv2.imshow. So you just have to import this OpenCV library alone. As we cannot do this in Google Colab, we are importing this as cv2 underscore imshow. Okay, and let's import another image processing library, which is Pillow. Okay, so from pill, where pill stands for pillow. So from pill, let's import this image module. So this is helpful for us. And after this, let's import the deep learning libraries that we need. First, I'm going to import TensorFlow. So we will be working on TensorFlow and Keras. So let's import TensorFlow as TF. And now I'm going to set the random seeds. So TF dot random seed. Okay, so sorry. So TF dot set seed. So TF dot random dot set seed, and let's set the seed to 3. So you can give any values for this. And the purpose of this setting the seed is that, so when you're training a neural network, when you're feeding this data to your neural network, and once this neural network is starting to learn from the data that you feed, what happens is there are several values that randomly gets generated. So like let's say that there is some parameter that has to be given for this neural network, and in some cases these values will be generated randomly. So because of this randomness, each time you train your neural network, you will get different results. Okay, so even if you use the same data, so the accuracy values and other values may slightly change. Okay, so there won't be a large change, but they will slightly change. So when you set this random state to a particular number, so this changes won't be there. Okay, so this is the reason for setting this random seed. You can set any numbers you want. So if you give that particular number, you will get the identical result. So this is just like the random state value that we have in train test split function. Okay, and the next thing is from TensorFlow, let's import Keras. Okay, so Keras is another important deep learning library. So the most important and the famous deep learning libraries that we have are TensorFlow, Keras, and PyTorch. Okay, so PyTorch is developed by Facebook and TensorFlow is developed by Google. So Keras is just like it is a wrapper of these deep learning libraries. So previously it was difficult to build neural networks with this TensorFlow library. So they created this Keras library, which helps us to easily create this neural network. Okay, so we will use this keras, and in the backend there will be this TensorFlow. So after a point, TensorFlow included keras in their own library itself. So we will be working on the APIs that we have in keras. Okay, so we will be working on sequential and other layers and so on. So that is the idea of importing this keras. And then from keras dot datasets, let's import MNIST. Okay, so as I've told you, this MNIST is a famous dataset, and this is useful for someone who is starting to learn about deep learning. And this dataset is available in this Keras library itself. So we might have came across this breast cancer data, diabetes data, and these datasets are present in the sklearn library, right? So similarly, we have a few datasets in this Keras library. So and here we are going to use this MNIST library. So that's the idea here, and we will see how we can load this library. But this is the reason. So we are from this keras.datasets module, we are importing this MNIST, and finally I'm going to import from TensorFlow dot math, import confusion matrix. Okay, so these are all the things that I want. So let's run this. So we have NumPy for NumPy arrays, Matplotlib and Seaborns for the plots and graphs that we want. CV2 is the OpenCV library for image processing task, and then we have the CV2 IMShow for displaying the image. Pillow is also used for image processing task, and then we have the deep learning library TensorFlow, and we are setting some seed for this TensorFlow, and then we are importing Keras, and from Keras the datasets MNIST data, and finally we are importing the confusion matrix. So these are all the dependencies that we need. So the next step is the data collection part. So I'll mention the text here as loading the MNIST data. Okay, so MNIST data. So this is basically image data from Keras dot dataset. Okay, so how we can import this data set is like this. So we have to give this so MNIST dot load data. Okay, so we have already imported this tf dot keras dot datasets. So instead of doing this, we have imported this keras dot datasets like directly. So first we have imported this keras, and then we have imported this keras dot dataset. So from this we have imported this MNIST and so on, right? So instead of that, from this TensorFlow itself they are loading this. So they are basically the same thing. So we are doing this step by step, and here they have mentioned as one single step. So that's the thing. So we have to mention this MNIST dot load data. Okay, so that's what we need to do. And so once you load this, you will get 4 arrays, and the 4 arrays that you get are xtrain, ytrain, and xtest and ytest. Okay, so the thing here is this is an already processed data, so you don't have as raw images. So we have seen in the previous video, right? So in the previous video was about how to process the image data for deep learning, and we have taken a single image. So we have taken the single dog image, and we have seen what are all the different processing that we do. So we have seen that we have to convert this image into a NumPy array like this, and so this is an example of a RGB image, right? Because we have 3 here, so 3 represents this 3 channels that we have: red, green, and blue, and these 2 values are the dimensions of the image, the width and height of the image. And the next thing is like so the other processing that we do is we have to resize the images. This is because if you have 10,000 images in your data, if all the images are of different dimension, then it is hard for the neural network to understand this images. So we have to resize the images to a common dimension. So in this case we have used this pillow. So this image module, from that we have used this from this pillow library image module, we have used the resize function, and we have resized to 200 comma 200. So this is another processing, and after that we have to convert this RGB image into grayscale image, so that we can save some storage space and the computation power and so on. Whereas in some case we have to work on the RGB images, but for this digit classification we can work on the grayscale images itself. And all this processing has been already done, and they have been stored in this MNIST data. Okay, so all the processing has been done, and they have also splitted the data into training data and test data. Okay, so we don't have to worry about that. So if we just go to this workflow, until this part everything is covered, from image processing to the train test bed, all the things has been covered. But it won't be the case in all the things. So in some cases you will have only the images and you have to process them and so on. So we will discuss about that in the upcoming project videos on how we can do that. But in this case, we already have the processed images and the data has been split into training data and test data. Okay, so you have to mention the four arrays here. So X train, Y train, X test and Y test. And so let's create them. So X train, comma, Y train, and then X test, Y test. Okay, is equal to mnist dot load data. So we can see this function here. So we have this mnist load data, right? So mnist load data. So we have to mention the parenthesis. Okay. So when you run this mnist dot load data, you will basically get four arrays, and those four arrays are nothing but this X train, Y train, X test and Y test. Okay, so that's what they have mentioned here. So this is how you can load this X train, Y train, X test and Y test. The only difference is that I have just used this caps for X and Y. So that's the only thing, but the process is kind of the same. Okay, so let's run this. So this will load this mnist data to these arrays, and you can also check the data type of this arrays. So we know that we have the keyword type in Python in order to check the data type. So I'll give this as type of X train, and here I can see this is in the form of numpy n dimensional array. Okay, so this is just to understand that the images has already been converted to numpy array. So we don't have to do that again. So we have the numpy array, so images have been converted to them. And now let's try to check the shape of these arrays, X train, Y train and X test and Y test, and then we will try to understand what these four arrays means. So shape of the numpy arrays. So this is the basically the data that we have. So I'm going to print. I just copy all these things. The X train, Y train, X test and Y test. Let's put this here, and I have to mention this as X train dot shape and Y train dot shape. So I'll remove this parenthesis. Y train dot shape, X test dot shape, and finally Y test dot shape. Okay, let's try to understand what this signifies. Okay, so the value that we have for this X train dot shape is 60,000 and 28,28. So what this basically means is your X train contains 60,000 images, and each image has a dimension of 28 into 28 pixels. Okay, so these are the value of height and width of the image, and these are the pixel values. So we have already seen about this. Okay, so if you consider this dog image, so it has printed like this, right? So what this means is, like, the height of this image is 200, and the x-axis value, which is the width of the image, is also 200, which is represented here. So here we have this 3. So what this 3 means is it has an RGB image, whereas we don't have that particular number here. So this means, like, this is a grayscale image. So X-train is my 60,000 images, and like each image is so 28,28 is the dimension of each image, and this is a grayscale. All the images are grayscale images, and the label for all these images has been stored in this Y train. Okay, so let's say that this X train has the image as, let's say, 7. Okay, so we can see this particular image. So once we train our neural network, we will feed this image, and we will check whether our neural network can recognize this image. So we have this 3, right? So this image has been converted to numpy array, and it has been stored in this X train. Let's consider that. And the label, so in this case the label is 3, right? So that will be stored in this Y train. So 60,000 represents my training data images, and the label for all these images are stored in this Y train. And then X test represents all my test data images. Y test represents the corresponding labels for all these test images. So that is how this data has been splitted. And if you see the count here, we have 10,000 test images. So the number of training data that you have is 60,000, and a number of test images that you have is 10,000. Okay, so that will be mentioned here as well. So you can see. So yeah, so X-train is unit-8 numpy array of grayscale images. So this is what I mentioned, because if that is an RGB image, there will be another value as 3 in this case, but we don't have it. This is a grayscale images of 60,000 values, and all the values ranges from 0 to 255. So we know that all this value represents what is the intensity of the white color. In the case of RGB images, we have three matrices, and each matrix correspond to red intensity, green intensity, and blue intensity, right? So all the values in an image range from 0 to 255. So we know that, and all the labels are present in this white range, and the values range between 0 to 9. Okay, 0, 1, 2, 3, all the way up to 9. And then in the test data we have 10,000 images. They also in the 28 into 28 pixels, and sorry, height and width, and they also have the values between 0 and 255. As 0 means that particular pixel is completely black, 255 means that particular pixel is white in color, and the corresponding labels has been stored in this white disk. Okay, so this is the shape that we have, and you can see here. So this is a data set of 60,000 28 into 28 grayscale images of the 10 digits, along with the test set of 10,000 images. So that's what we have understood here. And so let's just make some text here of what is present in this data set, so that if you look at this at a later time, you can understand this. So let me put this as training data is equal to 60,000 images, and my test data is nothing but 10,000 images. Okay, and each image has some dimension of, so image dimension is 28 into 28. Okay, and grayscale, so these are grayscale images, right? So grayscale image, so grayscale image means they have only one color channel. Okay, so unlike RGB images which have three color channels. So this is the basic information of the data that we have. So as I've told you earlier, we don't have to convert these images into grayscale images, and we don't have to resize the images and so on, and we don't have to convert this to numpy array. So all these things has been already done, and all this has been splitted into training data and test data as well. So until this part, everything has been already done in this data set. So we have to just try to see what are all the images that we have to get some basic idea, and after that we can train our neural network. Okay, so what let's do is let's try to print an image from this data that we have. So let's take one particular image. So printing, let's say I'm going to print the 10th image from this X train. So I'll mention this as print X train, and in this I'll say 10. So 10 is the index of this image, so which is basically it is the 11th image, because we know that in Python indexing starts from 0, right? So the image in the 10th index, so these are all the values. So we know that it is in the form of a numpy array, and all the values range between 0 and 255, right? And we have already seen, once you have this in the form of a numpy array, we can convert it back into an image, right? So let's see how we can do that. And I'll also check what is the shape of this image. So xtrain 10, so this is the image that we have worked on, right? So xtrain of 10 dot shape, so this will tell you what is the shape of this image. So it is a 28 into 28 image. So this is the height and width. So totally we have 60,000 images, and all these images have this particular dimension. So this is why I told you that all the images has been resized already, and all these images have the constant dimension. Okay, so this is the single image dimension, and now we are going to display the image. So displaying the image, plt.show, sorry, plt.imshow. So this plt.imshow is used to show an image. So we know that plt means the matplotlib library that we have, and I'm going to show, let's say you can just mention any images that you have. Xtrain, now it is in the form of numpy arrays, and we are going to convert it. Let's say the index is equal to 50. Okay, and plt.show, so this will print my image, sorry. So xtrain 50 and plt.show. Okay, and now what I'll do is I'll also print the label. So in this xtrain, I will take the image with the index of 50, and from this white line, and I will take the 50th label as well. Okay, so let's see. So plt imshow, which stands for image on plt.show, and here we will print the corresponding label. Okay, so print white train. So white train is my training data label, right, of 50. So let's see. Okay, so this is the 50th image that we have, and this is the label for that image. So you can just give anything here. So let's say that I'm printing the image with index 25 and I'm printing the corresponding label. So both the things will be same. So previously it was in the form of a numpy arrays, and we are just converting back into an image to just check whether the image and the labels are correct. Okay, so this is the image. So this, we know that this is two, the image of the number 2, and we have the label as 2. Okay, so this is nothing but, so this is what we are printing here, white rain of 25. So you can change these two values and see the image and the corresponding label. Okay, and then image, so this is actually a grayscale image, but this is the color that we will get in matplotlib show. Okay, so you don't have to think that this is a colored image. This is actually a colored scale image because this is only one color channel. Okay, and so let's try to analyze some of this labels that we have in this for these images. So image labels, so just some basic analysis of what are all the different values that we have and so on. First, I'll try to print this white train shape, white train dot shape, and y test dot shape. Okay, so the first value represents how many values are there in X train. So this is nothing but the label for the 60,000 training data images, and this y test represents the 10,000 labels for the test data. Okay, now let's see what are all the unique values that we have in white train and y test. Okay, so unique value, and another important thing, we can use this data set in order to classify only, like, or in order to recognize only one digit. So you cannot have multiple images, the model may not predict it correctly because we are training it with only one digit, right? So that's the reason. So unique values in white train, and I'm going to use this print. For this, we can use the function np. So we know that np means numpy, right? So there is a function called as unique in numpy, and within this parenthesis, you need to mention y train. So what this function will does is it will take this y train array. So we know that this is a numpy array, right? So it will take this array and it will try to find what are all the unique values that we have in this array. So I'll copy all these things, and I'll also print the unique value in y test as well. Let's see what are all the labels that we have. Okay, y test. So these are all the unique values. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is for all the unique values y train, and this is all the unique values in y test. Okay, so the training data and test data images. So this is what is given here. Okay, so y train is nothing but the digit labels which range from 0 to 9, and all these things are in the form of integers. We can see that here, right? So they are not in the form of floating points. And again, y test also ranges from 0 to 9. So y10 is my training data images and y-test is my test data images. Okay, so we can use this labels directly. Okay, or you can also perform one not encoding. So in this case, I'll just use this directly. So in some other deep learning use cases, I'll show you how you can do this one not encoding on this labels that we have. Okay, so I'll just mention this here. We can use this labels as such, or we can also apply one not encoding. Okay, so basically what happens in one not encoding is if your label is 0, in that case the first value will be 1. Okay, so the first value will be 1 and all the remaining 9 values will be 0. So let's say that there are like 9 zeros here, 0 0 0 and so on. If the label is 1, your second value will be 1 and all the remaining values will be 0 and so on. So this is what one not encoding is. And let's do this in some other cases. Let's have this label as such in for this one. Okay, so now what we are going to do is, so okay, so, and the other thing, as I've told you, we don't have to resize the images as all the images are in the in the dimension 28 command 28. So I'll also mention this here so that you can remember this. So all the images have the same dimension, same dimensions in this data set. If not, we have to resize all these images. This all the images to a common dimension. Okay, right. Okay, so if you have images with different dimensions, you cannot put that together in a single array, so it won't be compatible, right? So you can, create numpy arrays with elements of the same shape. So that's why we have this array. If not, we cannot create this array. So we can say that all these images are in the shape 28 comma 28, and this is also given in this particular documentation here. So all these are 28 into 28 and grayscale images. So these are not colored images, and these have only one color channel. And now what we are going to do is we are going to scale the data that we have, scaling the values. So we know that all the values are in the range of 0 to 255, right? So here also we have, so 0 to 255, which basically tells you the intensity of the colors that we have in this. So instead of having this range from 0 to 255, we can convert this so that we can have the values between 0 to 1. Okay, so I'll show you how we can do this. So this is also called as normalization, so that all the values are in the kind of same range. So this is like very helpful for us, because if the values are large, like 254, 81, 40 and so on, it is hard for the neural network in order to do the calculations, as the number is large, right? So whereas if you convert these numbers into small numbers without changing the information that this data has, all the things becomes easier, and we can also get better prediction. So this is kind of similar to the standard scaling that we have in machine learning, and the normalization that we have to that we used to do. So I'll take this x train. So x train is equal to x train divided by 255. So in most of the cases, if you don't do this, you will probably get a lower accuracy. So in this case, the accuracy may not change, but in most cases, that will be the thing. Okay, so it's better to normalize this. So x train by 255 and x test by 255. So what I'm doing here is I'm taking my all the training data and I'm dividing it by 255, and I'm storing it in the same variable called as x train. So you can also give another like name as extrain scaled or something like that. Okay, so it's not a thing. So I'm just giving the same name so that there is no confusion and all that. Okay, so I'm taking all this extrain, dividing it by 255, and I'm storing it in again this extrain, and this x test to this same. So I'm again taking this x test, dividing it by 255 and x test. So let's understand what happens when we do this. So let's say that the number is 0. Okay, so we have like all the values here, right? So each value will be divided by 255. Let's say that there is this value which is 0. So if the value is 0 and I divide it by 255, we know that the answer will be 0, right? And when the value is 255, so we are dividing it by 255 because 255 is the maximum value that can be present in this data. So that's the thing. So there is like nothing more to why we are using this specific thing. So it should be divided by the maximum value that we have. Let's say if the value is 255 and we are dividing it by again 255, now we know that we get the value as 1. So 0 is the minimum value that you have in your training data, and 250 is the maximum value. So the minimum value now you will get is 0, and the maximum value will be 1. So all the other values will be between them. So I'll try to show this to you. So let's say that, sorry. So I'll just open this calculator. And so let's say that we have this value zeros and zeros and all that, right? So we know that if we divide this 0 by 255, so the answer is again 0. So this is my minimum value. So the minimum value that you can have in this is 0. And let's say that if it is 255, we know that when we divide it by 255, this is just very basic math, this is 1. Let's take some other values. Let's say that the value is 40. So if I take 40 and divide it by 255, I will get this value as 0.156 and so on. If I take this value 214, so let's see. So I'm taking this 214 and I'm dividing it by 255. It will be 0.83. So the idea here is all the values will be in the range between 0 and 1. Now it is easier for the neural network to understand the images, to understand the data better. So that's what we are doing here. So let's try to do this. I'll close this one and okay, so I'll remove this and let's run this particular cell. Okay. Okay, now we can print this extrain 10. So let's print this 10th image itself. So this won't affect our image because like all the values are changed, right? If you change only like few values, in that case the original data has been compromised, but we are changing all the values. We are just changing the range in which these values are present. So previously you add the range between 0 to 255. Now we are having the values between 0 and 1. So that's the idea. Now if you print this particular value, you can see the values are between, so we have the 0 0.0. So and the values have been converted to floating point, we can see here. So previously the in the first row we have all the things as 0 and so on. So we have the value as 0.996, and then we have this 0.3368 and so on. So previously we add the values between 0 and 255. So this is how we can do this normalization, or we can scale the values between 0 and 1. So instead of having the values between 0 and 255. Okay. And now so these are all the processing that we have to do, and after this we can build our neural network. Okay. So I'll create a text here as building the neural network. So here we won't be using convolutional neural network, so we call this as CNN. So we will build a very simple normal neural network. So in convolutional neural network, you have this convolutional layers and so on. So there is a lot of concepts that has to be discussed in this. So we will discuss all these things in the deep learning course. But for now, understand that we are not using CNN here. So CNN are like very efficient neural networks that can be used on the image data, and we also have another type of neural networks called as RNN. Okay, so this RNN stands for recurrent neural networks, and this particular neural networks are very helpful when we are working with the text data or audio data and so on. So CNN is widely used for this image recognition, and this RNN for this text recognition and audio recognition things and so on. So here we are not CNN, we are not building CNN, as it may sound a bit complex to you. So we are just building some normal neural network. Okay, so a very basic one. So the first step that we have to do is setting up some layers for our artificial neural network. Okay, so setting up the layers of the neural network, and for this I'll just create a variable as model, and for this model I'm going to use keras dot sequential. Okay, so this is why we have imported this keras library. So keras dot sequential, so we have to mention the parenthesis and two brackets, square brackets, and within this we have to set up the layers of our neural network. Okay, so keras dot sequential. So first thing that I'm going to mention is keras dot layers dot flatten. So we have seen the use of this flatten in the previous deep learning project itself. So in the previous deep learning, the first deep learning project, we have worked on this breast cancer classification using neural network. So we have seen what is the purpose of this flatten. I'll also explain that to you now. So within this flatten, you have to mention the input shape. So in this case, the input shape is 28, 28. Okay, so what this flatten is, so you cannot feed the data in the form of this matrix. So here we have the data in the form of matrix, right? So 28 into 28. So that means like there are 28 rows and 28 columns are there in this particular image. So each image consists of like 28 rows and 28 images. So you can consider this as a matrix of this shape 28 into 28. So we cannot feed this data in the form of this matrix or this kind of an array. So we have to feed this in a single dimensional array. Okay, so what happens is, like, instead of having these rows and columns, all the values will be loaded as a single line. Okay, so that's what we do in flatten, and this is how neural networks kind of get the data as input. So this is the purpose of this flattening, and in this flattening we have to mention the input shape. So input shape is nothing but what is your image dimension, and here this is a grayscale image, so we don't mention any numbers here. If you are working on RGB images, so let's say that you are training your neural network on RGB or colored images itself, in that case you have to just mention another value as 3. Okay, so this means that so this is just to tell the model that I'm flattening all the values and all these images are RGB images. Whereas if you just remove this number, so now the model can understand that, okay, these images are grayscale images. Okay, so that's the reason for it. So if you are doing RGB images, just include another 3 years. So first layer is for flattening all the values. So this is just feeding all the values to our neural network. And now we can set some layers for this neural network. Okay, so layers dot dense. So dense is nothing but all the layers in this particular neural network is connected to the neurons in the previous and the next layer. So that is the reason of this particular dense thing. Okay, so we are building this dense neural network, and you can give this value. So I'm setting this value to 50. So 50 is nothing but the number of neurons that we have in this layer. So this is we have this input layer, which is the flattening, and then we have this dense layer with 50 neurons. So you can also change this values. So let's discuss later on, what the number of neurons we should have and how many layers we should have. So all these things we will discuss later, but for now, understand how we can implement the neural network. So let's go into the conceptual part later on. So 50, and we have to mention activation function. So activation is equal to ReLU. So ReLU is one of the widely used activation, and it is a very efficient activation function that we have. So ReLU stands for rectified linear unit. So you can do some research on this part. So this is few neurons will be activated. So activated in the sense their value will be 1, and few neurons will have the value as 0. So when you use the activation as ReLU, so the activation formula kind of changes. If you use sigmoid activation, so that neurons kind of fires differently. So you have this ReLU, sigmoid, and leaker ReLU, and so on. So we will discuss about all these things later on. So here I'm giving this activation as ReLU, and so you have to mention a comma here. Okay, and I'll also create another layer. I'll just copy this one, and I'll create another layer. So I have this input layer where I'm flattening all the values, and then have this dense layer with 50 neurons, and I have another layer with again 50 neurons, and finally I have an output layer. Okay, so keras dot layers dot dense. This is just to tell that all these neurons should be connected to the neurons of the previous layer. Okay, so dense 10, and activation is equal to, let's say, sigmoid activation function. Okay, so you can also change this to relevancy. So you can change this relu to sigmoid, you can change the sigmoid to relu. Your accuracy probably will change, so you can try that out. But this is the thing that I'm taking. So for this first two layers, I'm taking this relu as activation function, which is my rectified linear units, and for this final thing I'm using the sigmoid. So for this output neuron we shouldn't include this comma. Okay, so you can have any number here. So not any number, like you can take the neurons as 70, 75, or 100 or something. So here also you can take a different number of neurons, but this should be 10 here. So what this 10 means is the number of classes that you have in your labels. So in this case, if you check out the labels that we have the values as 0, 1, 2, 3, all the way up to 9. So the total number of values is 10, right? So we are starting from 0 and up to 9. So totally there are 10 values. So that is why we have the number of neurons in the output layer. So this is my output layer as 10. So in the previous deep learning use case video, the breast cancer classification video, we have add the value as 2 because we just had two classes, right? One is benign and the another one is malignant. So in this case we have 10 classes, and that's why we have 10 neurons here. So this is the layers of my neural network. So first I have this flattening layer, which is try to convert this matrix into kind of a single dimensional array, which as the values you can consider that all the values will be in the single column. And then we have this another layer with 50 neurons with ReLU activation function. There is another layer. And finally, we have this output layer with 10 neurons. And in this case, we are having the activation function as sigmoid. So you can just interchange it and check how the accuracy is kind of changing. So I'll run this one, and once you have set up this layer, so we are just specifying the specific, basically we are just telling what are all the specifications on neural network. Now we have to compile this. So this part of the code will be compiling the neural network, and for this we have to use this model is nothing but we have loaded this keras.sequential, right? So that's the thing. So model.compile. So there are like few important things that you have to mention. Okay, so you can see, so one is optimizers, and then we have this loss, and then we have this so we have to specify the accuracy, so it will be in the form of metrics. So model.compile loss, the arguments. Okay, so let's see, but the three main important things that you have to mention are this optimizer, loss, and metrics. So here it is. So let's see. So I'm going to mention this optimizers. Again, you have different optimizers are there, and I'm going to choose optimizer is equal to Adam. Okay, so Adam optimizer, and now I'm going to mention the loss. So loss is equal to sparse categorical cross entropy. Sparse categorical. So this is nothing but what is the loss function that you want to build your model on. So loss is equal to sparse categorical entropy, and the other argument is metrics. So what is the metrics that you have? So this is a classification problem. So let's say that the metrics should be accuracy. Okay, so let's try to understand this. So first is optimizer. So we have in machine learning, we know that we have this gradient descent optimizer, right? And the purpose of this optimizer is to determine the most optimum, model parameters, right? So if you consider a linear regression, we have the parameters as W and B, and our gradient descent will try to find which is the most optimum parameter. So optimum parameters in the sense, if you choose that value for your parameters, then you will get accurate prediction. Your accuracy values will be more. So similarly, Adam is one kind of optimizer, and then we are specifying this loss function as sparse categorical cross entropy. So here we have seen that we are using this labels as such, right? So this is in the form of kind of integers and simple numbers. Whereas if you convert the labels to 1-hot encoded labels, in that case you have to use the loss function as categorical cross entropy. So this won't work. So this is when you have the labels as simple label encoded values as a 0, 1, 2, 3, and so on. Whereas for 1-hot encoding, you have to remove this sparse underscore. So you have to use categorical cross entropy. And in the metrics, we have this accuracy. So we all know what does this accuracy mean. It is just the number of correct predictions divided by the total number of data points that you have. And you can do some research on what are all the different optimizers that we have in Keras and what are all the different loss functions that we have. Okay, so try to see and try to change this optimizer and see what are all the what is the change in the accuracy that you are getting. Okay, so I'll leave that to you, so you can do some research on the part and check it out. Okay, and I'll run this one. So we are basically compiling our layers, compiling the neural network that we have built with this Adam optimizer with sparse categorical cross entropy as our loss function and metrics as accuracy. So I'll run this one, and now let's train our neural network. So this part will be training the neural network that we have. Okay, so let's say model dot fit. So fit is nothing but we know that we use this to train our model, right? So this is similar to how we train our model in machine learning, right? So here we have to give your training data. So training data is nothing but my X train and Y train. So X train is my training data images, and Y train is the label for that corresponding images. So we have to give both of them. Okay, so model dot fit, and I'm going to say X train comma Y train. So I hope you remember that we have normalized out all the values. So all the values will be between 0 and 1 instead of between 0 and 255. So X train and Y train, and the other parameter you can mention is epoch. So what is the number of epochs that you want? So I'll mention the epochs as 10. So epochs is nothing but how many times your neural network should go through the data. So each time it will try to change its parameter values, and it will try to give you what is the accuracy and so on. Okay. So this is my first epoch, and so these are all the number of steps there in the epochs. Okay, so this particular neural network is training kind of in a fast manner, right? But in most cases the training takes a very long time. So the reason is here the dimensions of the images are like pretty less, 28 comma 28, right? So here you can see each image is 28 comma 28, so it is not a huge workload for the neural network, so it doesn't require that much computation power. But when you have the images in this shape of 200 comma 200, so actually 200 into 200 is actually a small image, but even all the images are in this particular shape, this model will take a very long time, and it will take a very huge computational resources and so on. So this is just a very small images with 28 into 28 dimensions. So the training has been done quickly. Okay, so you can see how many so what's the time that has been taken for this each steps. And so this is the first epoch, and this is the loss function value for the first epoch, and the accuracy is 91%. So we know that loss function is nothing but the distance between your true value and predicted value. If your loss function value is high, that means your model is not working properly, it is not making good predictions, it is making kind of wrong predictions. So our main goal is to minimize this loss function for a model or for a neural network. So you can see the loss function has been constantly reduced here, and we know what is meant by this accuracy. So the accuracy kind of increases. So 91.3. So what does this means is, like, if you predict the handwritten digits for, like, 100 images, you will get correct predictions for 91 images. So that is what this accuracy means. Like, we can see that loss function decreases, which is what we want, and the accuracy increases in each epoch, and we get the maximum accuracy as 0.989, so which is just equal to 98.9. It's almost 99% accurate, right? So that means out of 100 images, it will give you correct predictions for 99 images. So that's the idea. So this is basically the accuracy on training data. So that is very, very important. So we have to check it for the test data as well to see whether our neural network has overfitted. So what happens in overfitting is that you will get high accuracy like this for training data, but for test data you will get low accuracy like 50% or 60%. So I'll mention here that the training data accuracy is 98.9%. 98.9%. Okay. And now we are going to evaluate our neural network, right? So this will be accuracy on test data. So this is what we are going to do now. So just make this bold. So this part is nothing but model evaluation. We are going to evaluate our neural network. So I'll mention two values, loss, comma, accuracy is equal to. So within this model, so model is nothing but we have built this neural network with this keras.sequential, right? So we have this function dot model dot evaluate, and within this you have to give this x test and y test. Okay, so what happens is, so your model will take this x test alone and it will give its prediction. Okay, and those predictions will be compared with the true label. So this is my true label, which is y test, or you can also call this as ground truth, the original values that we have. So the model will make predictions and y test is made true value. So it will compare both of these things and it will give you what is the accuracy on the test data. Okay, so the test data is something that the model has not seen before, whereas the training data it has already seen. So we cannot take this accuracy as the final one. So it's important that we have to find the accuracy for test data, right? So let's do this. So when you run this model dot evaluate, you will get two values. The first value you get is loss, and the second value you get is accuracy. So that's why we have two variables here. And now I'll print my accuracy value, and let's see what is my accuracy. Yeah, okay, so the loss value is 0.104 and something, and the accuracy value is 0.971, which is like my model is 97% accurate. Okay, so this is the training data accuracy, and I can say that my test data accuracy, I'll just make another text here as my test data accuracy is equal to 97.1%. So 97.1, that means like this is the important accuracy metric that we need. So out of 100 images, your trained neural network can make correct predictions for 97 images. Okay, so we can say that our neural network doesn't overfit. If it does overfitted, in that case your test data accuracy will be very low. So we know that, right? So we have discussed about this several times in our machine learning use cases and course and so on. Okay, and now what I'm just going to do is I'm going to print the shape of this x test. So print x test dot shape. Okay, so we know that the test dataset contains 10,000 images and each image is of the dimension 28 into 28, right? So I'm going to display the first image. So first data point in the test data, so first data point in x test, which is my test data, let's say plt dot I am show x test of 0. So 0 means the index 0. So index 0 means the first image or the first entry or data point. So plt dot show. So I'm going to display that image. plt dot im show x test of 0. So the first image that we have in this x test is this 7. So we can see that this image is 7, right? Now I'm going to print what is the true label for this. Print. So y label is my true values, true labels, y label of 0. So it will be 7. So we know that. Okay, so y label, sorry, it's not y label, it's y test. Sorry. So y test. So 0 is nothing but the first data point. So the first image that I have in this x test is 7, and the corresponding label is, we know that it is stored in this y test. So it is 7, right? Now what we are going to do is we are going to give this X test to our model, and we are going to see what is the prediction made by our model. So it is just this evaluate. So for this evaluate, we have checked the overall accuracy, but I'm going to see the individual predictions made by the model. Okay. So let's create a variable called as ypred. So y test is my true labels, and I'm storing all the predictions made by the model in this variable called as ypred, where ypred stands for y prediction. So we have to mention model.predict. Okay, model.predict x test. Okay, so this will predict the labels for all the 10,000 images, and all the 10,000 labels will be stored in this ypred, which is my prediction value. Now you can see this ypred shape, ypred dot shape. So we know that this also kind of contains 10,000 values, right? Because there are 10,000 images. Okay. Now you can see there is an interesting thing. The value is 10. So we have to understand what does this 10 means. So I'll print the first value in this ypred. So ypred of 0. So this ypred is nothing but, so we are feeding all this x test to our model, and all the 10,000 labels predictions made by the label has been stored in this ypred. And when I run this will basically give the prediction made for this particular image, this first image, because this is 0, this is 0 as well. So this is the one the true label or the ground truth, and this will tell the predictions made by my model for this particular image. So you can see the value like this. So we totally have 10 values here, so that's why we have the second value as 10. So we have 10,000 labels. I'm just printing in this for only one label. So we have seen what is the significance of this in the breast cancer classification using neural network itself, the first deep learning project itself. The thing is, for machine learning model, when you use this predict, it will return the label value. So whether the label is a 0 or it is 1 or 2 or 3 or so on. Whereas when you use this predict function with this neural network from this Keras neural network, it kind of works differently. It will tell you what is the probability that the value is this one. So if you see this, so 3.51 into e power minus 03. So e power minus 03, you can just think what would be, without this exponent, you can think about it. So this value is what is the probability that the label is 0. And if you check the second value, this is what is the probability that the value will be 1, and so on. So this is the idea for it. And in order to convert this, so each represents a probability of each label. So first one for 0, second one for 1, third one for 2, and so on. And we have seen that we can convert these values to the labels that we want using np.argmax, right? So we have seen in the previous video. So let's try to do the same thing here. So I'll also mention this, that model.predict. So this is very, very important. So model.predict gives the prediction probability of each class. So each class is nothing but 0 to 9 in this case. So totally we have 10 classes. So you have 10 values here for that particular data point. Okay. So instead of giving that label or the label, it will give this prediction probability. Now we are going to convert this. So this part will be converting the prediction probabilities to class labels. Okay, so it is nothing like for which class or which label the value is maximum. So that is the final answer. So out of this, we have to find which value is the maximum value. Okay, so if you see here, the maximum value will be for this one, right? So because like all the things have the values as e power minus 03, minus 01, and so on. So this is the highest value that we have among all the things. So it is nothing but the one for 7. So this is for 7, for this is for 8, and this is for 9. So this is the maximum value that we have. But now we don't have to do this manually, because we cannot do this manually for this 10,000 images, right? So instead of that, we can use this argmax. Okay, so you can just tell that let's say that label for first image, so we are creating this variable, and I'm going to use np.argmax. So this is actually in the form of a numpy array, and when I say this np.argmax, it will tell what is the index of the value that is maximum. So np.argmax, we have to mention this ypred. ypred of 0. Okay, so ypred of 0 is nothing but, so this is my ypred 0 values, right? So out of this np.argmax will tell you which value is maximum. Let's run this, and let's also print this one. So print label for first image, so label for first test image. So this test image is nothing but this 7. Okay, so let's see our model has predicted this correctly. So print this one 7. So this is the value predicted by our model, because we are taking this from ypred. So we are using our model to predict the value of this X test, and we are taking the first image alone. So this is the prediction probability that we got, and we got the value as 7. So what this 7 means is that, so the value in the index 7 is the maximum. So if you count, this is the index 0, this is 1, 2, 3, 4, this is for 5, 6 and 7. So this is my 7th index value. So we start from 0, and this is my 7th value. So this is for 8 and 9. So what the 7 tells is the value in the index 7 is the maximum one. So that is your label. So this is how we can convert this prediction probability into the classes that we have using this argmax. So the role of this argmax is just to tell you the index of the maximum number in your array. So this is a numpy array, and it will tell you the index of the number which is the maximum compared to other values. So here we have done this for this ypred 0 alone, right? Now we are going to do this for all the 10,000 values that we have, so that you get instead of having this probability, you will get the label values. So converting, so it is the same thing. Okay, converting the prediction probability. Okay, so converting the prediction probability to class label for all test data points. Okay, right. So I'm going to create a variable as ypred labels. So ypred will basically contain the probability values, and ypred labels, we are converting them to this labels that we want, the format that we want. So ypred label is equal to np.argmax of I for I in ypred. So this is a simple way of creating a for loop. I'll tell you what this for loop does. Print ypred labels. Okay, right. So what we are doing here is, so we are creating a variable called as ypred labels, and np argmax of I for I in, sorry, so this should be I for I in ypred. So when the for loop runs for the first time, it will take the first value in this ypred. First value in this ypred is nothing but ypred of 0. So this is the first value. So this is the first value that I have in this ypred. So this will be my I. So my I will be ypred of 0. So that will be given to this I, which is my np.argmax. So basically this step happens each time the for loop runs. So when the for loop runs for the first time, the first image, the argmax will be applied. The second time, for the second image predictions, the argmax will be applied, and so on. So all this prediction probability will be converted into the labels. So let's run this one and see. Okay, so instead of having all this as labels, we have all the values here. So you can also compare how the values are there previously. Okay, so I'll show you. So print ypred. So this is how the values were before. So this is the prediction probability for my first image. This is the prediction probability for my second image, and so on. So this value, this numpy array, has been converted to the value 7. So it is just to tell the digit in that particular image is 7. So the second value, so this is my second entry, and so this happens when the for loop runs for the second time, and the np.argmax value is 2. That means the digit is recognized as 2, and so on. So we are just converting all this probability into classes like this, so that it is easier for us to understand. So I'll just delete this one. So this is our final predictions made by our model, whereas the true labels are my y test. So this y test, where is my y test? Okay, so this is my true values, true labels that is given in the data set, and this ypred labels are the ones predicted by my model. Okay, so I'll just mention that here. So y test is my true labels, or you can call this as ground truth. So all the things means the same. Okay, so true labels, and this ypred labels. Okay, so ypred labels represent my predicted labels. Okay, the values predicted by my neural network. Okay, so this is the test data prediction. So that is what this ypred labels is. Now we have already done this evaluation, right? So we have done this evaluation and we have seen that the accuracy score is 97.1 percentage. There is another interesting evaluation that we can do, which is building the confusion matrix. Let's see how we can build this and how we can infer this confusion matrix. Okay, so I'll create a variable as confusion matrix. So let's just mention this like this. So if you remember, we have already imported this confusion matrix, right? So from tensorflow.math, so tensorflow has this math module, and within that we have this confusion matrix. So this is the function that we are going to use. I'll copy this and paste it here. So I'm going to build the confusion matrix for this predictions. So for this, we have to give the true labels as well as the predicted labels. So we know that true labels are whitest and the predicted labels are whitest, right? So first you have to mention the true labels. So whitest. So you know how you would calculate the accuracy score in ML. So it is just kind of the same thing. Whitest and widespread label. So so the first array should be your true values, and the second thing should be your predicted values. So I'll run this one. So this will build my confusion matrix. You can also print and see this. Okay. So print confusion matrix. Okay. So confusion matrix is not defined. So I misspelled it. Let's paste it here. Okay. So this is the confusion matrix that we have. Now it is hard to understand what these values mean in this format. So now what we can do is we can build a heat map. So we know that we have built heat map several times for this correlation matrix, right, in our regression problems and so on for the machine learning use cases. So similarly, you can build a heat map with all these values. Okay, so I'm going to, for this purpose, I will be using this matplotlib, and this is why we have imported the cbonds library. I think we have never used this pill library, right? Pillow library we haven't used, but it's okay. So now we are going to use the cbonds and matplotlib library. So I'm going to say plt.figure. So this is the basic plot on which this heat map is going to be constructed. So here you have to mention what is the size you want for your plot. So this is like pretty simple things. So fixed size, which stands for what is the width and height you want for your plot. I'll mention it as 15 and 7. So with 15 and height as 7, and SNS. So SNS stands for the cbound library that we have imported, and cbound has this function called as heat map. So this is used for creating this heat maps. And here you have to mention from which we are going to convert this heat map. So as I've told you, we are going to convert this heat map from the confusion matrix that we have. So we are going to build this based on these values. Confusion matrix. So SNS.heatmap confusion matrix, and annotation is nothing but the annotations for this plot. So annotations is equal to true and fmt. Okay, so fmt is equal to d. So d is nothing but I'm telling it that all the values should be in the form of integers. So that is the purpose of this. Like if you mention this fmt is equal to %2, that means like two decimal values will be given and so on. But in this case all the values are integers, so we have to mention this fmt is equal to d, and cmap is equal to blue. Okay, so you shouldn't give blue, the value should be blue. So it is just to set the color, so you can have any colors that you want. So let's create the heat map in blue color here. And now I'm going to give this y label, plt.y label for my heat map. So let's have this true labels in this y label. True labels, I'll explain you what these things means. Just wait for a second. Let's name this x label as predicted labels. Okay, right. So yeah, so let's run this. I think everything is correct. Okay, let's try to understand what this particular heat map means. So if the value is 0 and if the value is small, it is basically represented in a light color, so a very light blue color. And if the value is large, if it is like 800 or if it is 900,000 and so on, it is represented in dark blue color. So this is why we mentioned the C map as blues. If you change it, it will kind of change. So the color of the heat map will change. So just a second. Okay. Now all the values in this diagonal represents the true predictions made by your model. Okay, So all these labels are my true labels, and all these labels are predicted labels, the values predicted by my model. And now let's try to understand what these numbers mean. Okay, so if you see this first box, we have the true label. So you have to see the x-axis, sorry, the y-axis and the x-axis as well. So this is my x-axis where my predicted labels are there. So this is my y-axis where true labels are there. So what this 969 means is like 969 means is like how can I explain you this? So 969 zero images has been correctly predicted to zero. If you see this, the true label, so you have to see the vertical axis here, which is my y-axis, so that will give you the true label. So what this one means is like my true label is zero, but that one particular image, the model has predicted it as one. So you can see what is the value in this x-axis. Okay, and if you see here, so the true label is zero. Actually, the true label in the sense the digit present in that image is a zero, but it has been predicted as two. So that is what it means. Like zero means no images of zero has been predicted as three. So that is what the zero means. And what this three means is like there are three images, and all those three images represented zero, but our model has predicted it as eight. So this is how we can infer this confusion matrix. So it is just to tell you what is the correct predictions made by our model. So 969 means like 969 images of zero has been correctly predicted to zero. And if you see this 1122 images, one images has been correctly predicted to one, and so on. So all this diagonal means the correct predictions, and all other values represent my false predictions or wrong predictions. And if you want to find this, you just have to see the y-axis for the true labels and x-axis for the predicted labels, and so on. So this is very, very important for us in order to understand like which numbers has been predicted like what. So if you see this one, so it is like a large value, right? So what this means is like 24 9 images has been predicted as 4. So if you see this one, so you have to see y-axis. So true label is 3, so 23 images of 3 has been predicted wrongly as 5. So this is how you can infer this confusion matrix. So it is not easy to infer from this one, but we can kind of put this in an heat map and kind of visualize this like this. Okay, so I hope everyone understood until this part. So this is all about model evaluation. I think like this video is pretty large, but you can learn a lot of things here. And the next, so this is the last part of the video, which is to build the predictive system for our model. So using this trained neural network, we have to build a predictive system. Okay, so what this predictive system is, when you give a new image, so in this case we will give this 3 image. Okay, so when you give this image, the model should predict that it is 3. Okay, so you cannot use like different images of typed images or so on. So if you are training with MNIST images, it should, you have to predict with this image. So that is like obvious, right? So machine learning models and neural network models doesn't know what it is not trained on. So they only know about the data that they have seen. So like so it is just like you cannot train your model on the numbers, and you cannot predict alphabets there, right? So similarly, like we have predicted with this MRIST data, so the image that you are going to predict should also be similar to the data that you have trained on. So that's the idea. So just a second. Okay, so now we are going to build this predictive system. So this is one of the interesting part of this code. So building a predictive system. So let's do this stepwise, and then we will consolidate all the codes of this predictive system. So first is I'm going to mention input image path. Okay, so input image is nothing but the image which you are going to predict. Okay, so input image path, I'll upload the image here. So I'm just going to this file. So this is where I'm going to import the image. If you're working on your PyCharm or Spider, you have to mention where that particular image has been located. So this is that 3 image mnist digit.png. So this image has been loaded. So I'll copy the path of this image. Okay, and I'll paste it here. So this is the path of this image. So first I have to read this image and convert it to NumPy array. So we are going to do the processing that we have seen here. Okay, so previously the data has been present as already, it has been present as a NumPy array, right? So it is 28 into 28 pixels and so on, whereas this image is not in that format. If you see this image, the dimension is 318 into 318. So we have to convert this dimension, and we have to read this to NumPy array, and few processing are there, and we will do this. So this is where we will use the things that we have seen here. And I'll create a variable as input image. So input image is equal to cv2 IM read. Okay, so CV2 IM read, and the first thing that you have to first argument it takes is input image path. Okay, so I'll just copy this. Okay, so input image path, it's not like you have to put it like this. So instead of creating this variable as input image path, you can also copy this path and you can paste it here. So both of them are the same thing, so I just wanted to do this in this way. Okay, so the thing is this im read function cv2 dot, okay, so it's not underscore, it's cv2 dot im read. So this function take this path of the image as the argument or the parameter. Okay, so I'll run this one. Okay, so now you can check the type of this input image. Type of input image. So it will tell it is a numpy array. So this image, this 3 image, so you can see this here. This 3 image has been converted to a numpy array. You can see the values here. So I'm going to print this one. So print input image. So this will how this numpy array will be. Okay, so 0 means black and 250 means white. So with this dots mean like there are several values in between. So I'll just remove this output. Okay, so now you can, again, as I've told you, you can print this image using the cv2 imshow function. So we have this cv2, so this is why we have imported this google collab.patches. If you're working in spider, you can just use cv2.imshow. You don't have to import this one. So collab doesn't allow cv2.imshow function, as I've told you before, so that's the reason. So cv2 imshow, so this is just to display the image from this numpy array. cv2 underscore imshow input image. So this is the image that we have, right? And let's check what is the shape of this image. So this is an interesting thing. So now you can see that the image shape is 318 comma 318 and there is a 3 here. So this is the interesting aspect and the thing that you have to be clear about. So we can see this image is kind of black and white, but actually this has been read in the form of a RGB image. So this has been considered as a colored image. So this is a kind of a crucial thing here. So instead of reading this as a grayscale image, the cv2.imshow is reading this in the form of RGB image. Now the problem is we have trained the images. You can see if we take a single image, where it is. So I'll just go to the image that we have printed. So here, like if you take this two, the shape is 28 comma 28, whereas in this case the dimension is 318 into 318 and it is 3. So 3 means RGB channel. So we have to convert this image to a grayscale image and after that we have to resize it. Okay, so these things are there while building this predictive system. I'll create a variable as grayscale and now we are going to convert this image. Grayscale is equal to cv2 dot cvt color. Okay, so cvt color, and the parameters that we have to mention are input image comma cv2 dot color rgb to rgb. Okay, sorry, so see color underscore color rgb to grayscale, where it is. Okay, so this is the one. Okay, so what we are doing here is, so cvt is nothing but I'm going to convert the color. So what I'm going to convert this is this input image, this 3. So I'm going to convert this image from RGB to a grayscale image. So this is just basically color conversion. Okay, so let's run this one and now you can print this input image. Okay, so input image, so we have converted this to grayscale. So we have taken this input image, converted to a grayscale image and stored this in this particular variable. So I'll mention grayscale dot shape. Sorry, so this should be shape. Okay, now this 3 is not there, right? So what this means is like this RGB image is now has been converted to a grayscale image. So that's what we are doing here. And the next step is to resize the image. So this 318 comma 318 should be converted into 28 and 28 dimensional image. Okay, so input image resized, input image resize is equal to cv2 dot resize. Okay, so cv2 dot resize is the function that we have. So in the previous video we have seen that we can use this pillow library as well. So where it is, so we have imported this image module and from this we have used this resize function, and this function is from cv2 library. So cv2 also has the same function. So cv2 dot resize, we have to mention what is the image that you are going to convert. So it is the grayscale image. Okay, so grayscale comma. So here you have to mention what is the dimension that you want to convert. So it's 28 comma 28. Okay. So what I'm doing here is I'm taking this grayscale image and I'm going to convert it to the dimension 28 comma 28, and I'm going to store this in this input image resize. Okay. So let's run this one, and now you can again check the shape of this input image resized one. Okay. So input image resize dot shape. So previously it had 318 comma 318 as your size, and now it has been converted into 28 comma 28 because this is the size that is compatible with the neural network that we have built. So you can see here. So we have mentioned that the input shape is 28 comma 28. So the model expects the image to be in this particular dimension, in this shape. So that's the reason we are doing this particular step. Okay. So you can also show this image. I'll also use the CV2 function again. CV2.IMShow. Now let's see how the image is looking like. CV2 underscore IMShow, and now I'm going to show this input image resized. Yeah, so previously the dimension of the image is like this, and now it has been like shrunk to this. So this is the dimension before, so 28 comma 20. So this is a 28 comma 28 pixel image. Okay. So next step is like um so next part is the other thing that we did is scale the image. So we have did this normalization part, right, where it is this 25. Yeah, so this 255. So we have converted all the image. So previously the values between 0 and 255, right? Now it has been converted to 0, between values are between 0 and 1. So how we did that is by dividing all the value by 255, right? So we have to do that here as well. So this is like very, very important. So what are all the things that you did for your training data should be done for this as well. So this part will be uh, I'll just take this as input image resize itself. So I'm not changing the name. So input image resize is equal to input image resize divided by 255. Okay. So now all the values will be scaled and all the values will be between 0 and 1. Okay. And there is another important step. So before predicting, there is only one more step that is pending here, which is to reshape. Okay. So image reshape is equal to np dot reshape input image resized. I'll explain you what is the necessity of this comma. And here I have to mention 1 comma 28 comma 28. Okay. So if you have seen my other videos, my previous machine learning use cases videos, when we are building a predictive system, first we will take all the values and we will kind of reshape it to 1 comma minus 1. So the reason for doing this is to tell the machine learning model that I am predicting the label for only one data point, right? So we have done this np dot reshape 1 comma minus 1. So we call that as input data reshape. Similarly, we have to tell the neural network that I am going to predict the value for only one image. So I'm not giving you 10,000 images or 60,000 images, and I'm giving you only one image, and you have to predict the label for this one image alone. So that is what we do using this reshape. So if you have some doubts, you can copy this input image resize and you can check this shape, not type. So this type is nothing but numpy array. So this is not in the form of images. So CV to IMShow will basically convert the numpy array to an image. So this is actually in the form of a numpy array. So you can see this. Now we are taking this numpy array and we are reshaping it. Okay, so it is just similar to that 1 comma minus 1. So we have to understand why we are giving this particular value. So I'm creating a new variable called as image reshape, and I'm using this numpy np numpy. So we have the same reshape function, and we have to pass the image that we are reshaping. So this is the image that I have after resizing and after scaling down the values. And the second argument that I pass is 1 comma 28 comma 28. So what this means is I am going to predict the value for only one image, and the dimension of this image is 28 comma 28. So that's what we are doing here. So there is like nothing complicated in this. So I'm taking one image 28 comma 28. If if I'm, let's say, predicting for 10 images, I have to mention that 10 comma 28 comma 28. So here I'm taking only one image, which is 3, right? And another thing, if you are working with RGB images completely, so let's say that you are training your neural network with RGB images and you're predicting for RGB images, in this case you have to include a 3 here. So this is a grayscale image, so we don't have to include anything here. So this is a very important step. So if you don't do this, so your prediction will throw error. Okay, so that's the thing. And Let's run this one, and again, so here as well, if you're, I think I have mentioned this already, so if you're training your neural network with RGB image, so along with this image dimension you have to mention as 3. So here it is grayscale image, so it is not necessary here. And yeah, so it is this part is for reshaping. So I'll run this one, and now we can use our model to predict. Okay, so I'll create this variable as input prediction. So input prediction is equal to model dot predict uh, image reshape. So this is the final array, the processed image that we are going to feed. And let's also print this prediction. So print input prediction. So we are predicting the value for one image, and we are printing it. Let's see. Okay, so we have successfully printed it. So this is the value. So we know that this is the probability value, right, for each classes. Now let's again use this np.argmax in order to find the label. So I'll name this as input pred label. So it is nothing but input prediction label is equal to np.argmax of input prediction. So I'm taking this input prediction array and I'm going to find which is the highest value. So that's the idea. So let's run this one. And now let's print this input data prediction, sorry, input pred label. So now let's see what is the model is predicting. Yeah, so now the model has predicted correctly that this image represents 3. So we have successfully printed it. So if you see here, this is for 0, this is for 1, 2, 3. So this is the maximum value that we have, right? So the model has predicted correctly. So this is nothing but plus 1. So all the other values are e power minus 3, minus 8, and so on. So the model has correctly predicted that the value is 3. So we are predicting this from model. So this model is nothing but the neural network that we have built. So this is how you can build a predictive system. I'll just combine all this code so that it is in the in a single shell. So the same, so I'll just put a text here. So we are not going to do anything new. So predictive system, so I'm just going to combine all this code for this predictive system. And the first thing is input image path, right? So input image path, so this is the first thing that I want. Yeah, this do itself here. So input image path. And now, so instead of hard coding this, instead of mentioning the path here itself, I'm going to create an input function. So input of path of the image to be predicted. Okay, let's see how this kind of works. Path of the image to be predicted. And then, so once we give this prediction, so what happens is like this will show this particular statement, and the user has to specify the path of the image, and after that that will be loaded. So you can give different paths or different images each time you run. So that's the idea. So input image cv2.imread input image path. And the next thing is, let's also show the image. Okay, so once the user has mentioned the path, let's also show the image that is present there. Put image path, so show the image. And the next step is to convert the images to grayscale image, right? So this is important. Grayscale cv2.cvt color, and then input image resize. So all the things should be done. So this is my resizing thing. Okay, input image resize. And the next thing that I have to do is reshape it. Sorry, so we have to do this as well, right? So we have to scale the values down. So 255. And the next thing will be reshaping. So reshape all the values. So this is for predicting only one image. And this is my input prediction. So we don't have to print this prediction. So we just have to find the label. So I'll just remove this. Finally, my input prediction label. Okay, so input pred label, which is the np.argmax of input prediction. And finally, we can print that the handwritten images. So the handwritten digit is recognized as, we can put this input pred label. Okay, so what we are basically doing here is, so first when this line executes, so it will ask the user for the path of the image file. After that, that image will be read using the cv2.imread function into the variable called as input image, and we will also display the image to the user itself. After that, we will convert the image to a grayscale image, and then we have to resize the image to the default value that we are taking, which is 28,28, and after that we have to scale the values down so that the values are between 0 and 1 by dividing it by 255, and then we are resizing the image. As I've told you, we have to tell the neural network that I'm not predicting for 10 labels, I'm predicting for one label, and then we are using this model.predict. So this is for predicting the values, and once we have this prediction, we know that it will be in the form of probability, so we have to convert this using this np.rmax, and finally it will print your labels. Let's see how this works. So I'll run this one. So here you have to give the path of the image file which you want to predict. Okay, so I'll go to the files, I copy the path of the image that I want to predict, and I'll paste it here. Let's see how this is working. So once I give the path of the image, so you can see here, so I have given the path of this image here. So this code will display the image that has been given, and it will give this statement that the handwritten digit is recognized as 3. So in this path, so when you run this, instead of, you can have multiple images. I mean, like, you cannot give multiple images at once, but you can give different images each time you run this. Okay, so you can take another MNIST image and you can give this value. So it will display the image and show the result. So the process that are happening are, first it should read the image, it should convert it to grayscale, then resize it and divide it by 255, then reshape the image and make the prediction and print the print statement. So that's it for this video. And I know that this is a very long video, but this will be like very useful for you, moving on to the image recognition projects that you have. I'll just give a quick recap so that you kind of remember all the things that we have done. So first part is just importing all the necessary libraries. So we have NumPy, Matplotlib, Seabounds, and so on, and we have this deep learning libraries, TensorFlow, Keras, and so on, and confusion metrics for building our confusion metrics and displaying it in heat map. So we know that the data is in the form of MNIST. So but the thing is, it won't be in this format every time. So the actual data that we have will be in folders. So you will be given a folder, and that particular folder will contain 10,000 images or 20,000 images. So you have to do all the processing, and then you have to convert it to test image and train image and so on, but we will work on that later. So here we have the data set in this keras.datasets itself in that module. So we have loaded the data set, and we have got this training data and test data separately, and we have seen that there are 60,000 training images and 10,000 test images, and this is the image dimension, and we know that all the images are in the form of grayscale. So we have printed and seen what are all the values, and we have taken like one image and we have printed it, and we have also seen the corresponding label. So all the values are correct, and we have seen that this is the count of the labels we have for training images and test images, and we have seen what are all the unique labels that we have, and we have found that there are 10 labels, right? And then we have scaled the values so that the values are between 0 to 1. So before we had the values between 0 to 250, now we have the values between 0 and 1. So that is the next step, and later we have seen so how the values has been changed and so on. So this is not that much important. So this is the important part, which is building the neural network. So we have built a very simple neural network where you have to create this flatten layer, and you have mentioned the input shape. So input shape is nothing but the dimension of the image, and then we have built some layers for this neural network with 50 neurons, and we have mentioned the activation function as redo, and the final output layer. So this is my output layer with 10 neurons because we have 10 classes 0 to 9, and then we have compiled with Adam optimizer, and the loss function as sparse categorical cross entropy, and metrics as accuracy. So that's why you are getting this accuracy value here, and we have fitted. So this is the training of neural network, and we have trained it with 10 epochs, and we have found that the training data accuracy is 99.9, which is almost 99% accuracy. And then we have calculated the test data accuracy, and the next part is taking the first image of the test data, and we are passing it to our model, and we are asking it to predict, and we are converting this probability into label using this np.rmax, so it is predicted correctly, and we are doing this for all the values that we have, and this is the final labels that we are getting. And using this, we are building the confusion matrix, and we are visualizing this to see how many correct predictions are there and how many wrong predictions are there for each classes. And later, the important part of building a predictive system, where we have done all these things. So when you give the path of the image, so it will first show the image to the user, and it will uh, read the image in the form of NumPy array, convert it to grayscale, resize it, divide it by 255, reshape it, and finally make the predictions using neural network and apply Rmax in order to give the result. So I hope everyone has, everyone understood all the things that we have covered in this video. So please practice all the things. So this is a very, interesting use case. So try to do all the things. It's okay if you kind of, just looking at the code and you're practicing it by yourself. That's not an issue. So, you will get better by practicing. So I suggest that you have to practice all the codes that has been done in this particular video. And yeah, so that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. In today's video, we will be building a dog versus cat classification system using transfer learning. Transfer learning is a very important concept in deep learning where we use pre-trained models in order to build our use cases. So in this case, we will be using a pre-trained model called as MobileNet V2, where we will train that particular model on images of dogs and cats, and in turn, this model can tell you whether an image represents a dog or a cat. Okay, so this is what we are going to discuss in this particular video. So first of all, let's try to understand what this transfer learning is, and later I'll explain you what is the workflow that we are going to follow for this use case, and later on we can move on to the hands-on part where we will build this system using Python. So first of all, let's try to understand what this transfer learning is. So transfer learning is again a deep learning technique where we use a pre-trained model. So this pre-trained model is trained for one task and can be retrained for a similar task when you have a smaller data set. Okay, so this is what transfer learning is. So it is all about using a pre-trained model. So when I say pre-trained model, so this model has been trained already on a particular data set. So it has some weights on it. And later we use this model and we train this with a different data set, but the only difference is that you can also have a smaller data set. So when you train a model from scratch, when you have a smaller data set, you cannot like achieve good accuracies. So this is like other reason why we go for transfer learning as well. So it gives you higher accuracies compared to training model from scratch. Like in most of the cases you can like achieve like good accuracies. And the thing is like it is trained on a data set. Again, it should be used for a similar task. So you cannot take a NLP model and like use it for image recognitions and things like that. So it should be a similar task. Only difference is that you are training it on a bit different data. So say for example, if you have built a model and trained it on some image recognition task, so you can take that model, train it with some different data set, which is again a image recognition. So in this use case and in this video, we will be taking the MobileNet V2 model and we will be training that with images of dogs and cats, as I've told you. Okay, so this is what we are going to do. And again, when we say transfer learning, there are like different and famous transfer learning models like VGG16. So all these are like a few examples of pre-trained models that are available. So we have this VGG16, which is a very famous image recognition model, and then we have this ResNet 50, Inception V3, and so on. So in this video, we will be using this MobileNet V2, which is more of a lightweight model. Okay, and we also have this YOLO, which stands for you only look once. So it is like mainly used for object detection tasks and so on. So similarly, we have like these pre-trained models which we can access. Okay, so this all about transfer learning. And now let's try to understand the workflow that we will be following. So as we know that the first step is to collect the appropriate data. So in this case, we need images of dogs and cats, and for that we'll be using Kaggle API in order to extract the data from Kaggle. So that is the first step. So once you have this data, so we know that the next step is this data processing. So in this, we will be doing some image, processing techniques like we have to reshape these images and we have to like convert them into NumPy arrays and so on. So this is like the major step in this use case. So once you do all these image processing tasks, we can then split this data into training data and test data. So the end result is that you have like set of dog images and the respective labels, and then you have cat images and the respective labels for those cat images. And then we will split this data into training data and test data. And we know that we use this training data to train our model and test data in order to evaluate our model. And then you feed this data to a pre-trained MobileNet model. So again, you can use different models as well, but in this case, we'll be using this MobileNet V2 model. So once we train this with a smaller data set that we have, we will be, having a MobileNet model that is like trained on top of this dog versus cat data set. And we will also like evaluate this model with the test data that we have. And later, when you feed a dog image or a cat image, it can tell you what particular thing that is. So it will tell you whether it is a dog or a cat. So this is what we will be doing. Okay, so I hope like everyone is clear until this part. And now let's move on to the hands-on part. So we will be doing all this coding in Google Collaboratory. So I have my Google Collaboratory setup open here. So just go to Google and search like dog versus cat data set. So let me just type it here. So dog versus cat data set Kaggle. So this will take you to this site. So this is the dog versus cat competition. So this is the data set that we'll be using. So here you can go to this data. So you can just go through it in order to understand about this data and like what are all the tasks that you can do. So go to this data, and here you can find this API. So this is the API that we have, and we will use this API in order to extract this data set to our Google Colab environment. So you can see the size of this data set here. So I'll go here. So this pip install Kaggle will install the Kaggle library, but it will already be pre-installed in this Google Colab environment. So next is we have to get this like kaggle.json file. So that you can find in your accounts. So here you can see your account details. So there, go to your account. So there you will see this create new API token. So once you click this, a file will be downloaded, which is nothing but kaggle.json, which contains your account credentials. So then you need to upload that kaggle.json file into your collab environment. So I'll go to this files, and I'll try to upload this file. So it is in my in my desktop. I have a folder called as kaggle json file. So this is the file that I have downloaded. So similarly, download your file, and make sure you have like verified your account with your phone number or your email address. So then only like this will work. So then I'll like run this. So this will stay common. So we are just basically configuring the path of this kaggle.json, right? So you can just copy this code snippet, and you can like use it. So I'll run this cell, and now we can import this dataset from Kaggle. So I'll just create a text here, and I'll name this as importing the dog versus cat dataset. That's it, from Kaggle. Okay. So here we need to give the Kaggle API to import the data. So that we have seen here, right? So we have to go to this data. Just a second. So there you will find this API. So you can click this copy API command, and now we can paste it here. So before that, we have to include an exclamatory mark and then paste your API command. So now I'll run this. So this will download this dog versus cat dataset into my collab environment, and this is the data that we will be using, which contains several thousand images of dogs and cats. So it will take few seconds, and now we so this will basically download this data set in a zip file. Okay, so all these three files will be in a compressed zip file, and now we have to extract that. Okay, so this has like downloaded this file. So you can see this here. So this is dogs versus cats.zip. So if you wanted to print that files at here, you can just mention ls, which basically list all the files in your directory. So we have this dogs versus cats.zip. So this is the data set that we'll be working on. Now let's extract this file. So I'll mention this as extracting the compressed file, which is basically the data set. Okay, now there is a library called a zip file. So from this zip file library, I'll import this function called as same zip file. So here this z and f should be in caps. And now we have to give the path of this data set. So data set is equal to, so it's basically the path. So you can either put this docs versus cats.zip, or you can also paste the full path. So both will work, because this will just take the current directory that you're in. So the best thing that you can do is like copy this path always. So I'll just replace this. So again, both of this will work. So I'll paste the entire path, and now I'll say with this zip file, in this bracket I have to say dataset comma r. So we are reading this data set, and let's read this as a zip. So again, this is a variable, you can give any name, and now I am going to say zip dot extract all. So this will extract all the files that is present in this zip file. And now once this is extracted, I'm going to print a statement. So I'm just going to say the data set is extracted. So let's put this in quotes. Okay. So first we need to import this function from zip file, then mention the path, then we are like opening this file and reading this as a zip, and then we are extracting this. So these are like the basic steps that we do. So this will like do this extraction. And if you look at this data, we have this three files. So one is the sample submission.csv. So this is basically to submit the predictions that is made. So we don't need the sample submission and this test.zip, but we are interested in this train.zip file. So we need to do the same extraction for this train.zip. So I'll go to this files. You can see that here. So we have this test sample submission.csv test one and train zip, right? So now I have to do the same thing, this extraction process for this train.zip. So I'll copy this code, and now I'll replace this dogs versus cats.zip with this train.zip. So I'll copy this path and replace it here. Okay, so now let's extract this. So this will basically give you a folder that has images of dogs and cats, which are JPG files or PNG files. So we can like analyze that later. Yeah, so this has extracted the file. So you can see a folder called as train. So you can like expand this, but this will take few minutes because like there are several thousand images, so it will like take few seconds. And now in order to count the files that are there in this directory, you can like do something like this. So I'll import OS library, and now we are going to count the number of files there are. So it's taking some time, so I'll just like close this. Let's like see this here as well. So counting the number of files in train folder. So this train folder is something that we have imported, right? So from train folder, and now I have to create like two things. So we have to create this path and directories and files. So here I can say next. So these are like the conventional code that we use. So there is like nothing complicated in it. So I'll use this os.walk, and here I have to give the path of this train folder. So I'll copy the path. Let's paste it here, and I'll create another variable called as file count. So this will basically create like this path directories and so on, and this will create this list. So this files is basically the list that contains like all those file names. I'll say file count. The file count is equal to, I'm finding this length of files. So it will tell you like how many files are there in this particular directory, and later we can also print like number of images. The number of images in this train directory, and this is equal to, so we can print this here. So let's say file count. So it says like there are totally 25,000 images. Okay, so again we won't be using all these images because we are using a pre-trained model. So I'll just take a small sample of this, and we can like train our pre-trained model. Okay, and now let's try to print the image, like name of this image files. So I'll create a text and name this as printing the name of images. So I'll create a variable called as file names, which is basically a list, and I'm going to use this OS. So we have imported this OS directory, OS library, right? I'm going to say OS dot list dir. So this will like list all the files in a directory, and it will basically create a Python list. And here I'll paste this path, which is content train, and I'll print this file names. Okay, sorry, so we have to include an underscore here. So these are the name of the files that are present here in this string. Okay, and as you can see, we have dog images as well as cat images. So in some cases you will receive a data set where these two classes are present in separate folder, but in this case we can see both the class of images, that is dog and cat, are present in the same folder. Okay, so we have to like do some processing within that itself. So these are the files that are in this like particular folder. So now let's do this processing. So the next step is, let's try to import all the required libraries that we need. So this will be mm, importing the dependencies. Okay, so first let me import numpy library as np, and I'm going to import from pill. Let's import image. So pillow is a library which is like used a lot in this image processing tasks. So I'll import that as well. And next I'll import matplotlib dot pyplot as PLT. So we need this again to do some image processing to display, the images that we have and so on. And then from the same matplotlib library, let's import a different module which is matplotlib dot image. So we can import this as mpimg. Again, this is the convention that we use for this module. And then we will import train test split from sklearn dot model selection. From this, we are going to import train test split. Okay, so from sklearn.model selection train test bed, and finally I'm going to import from google.collab.patches import cv2 I am show. Okay, so this is basically we have a function called as imshow in cv2 library, which is opencv. So that cv2.imshow won't work in Google Colab environment. So as an alternative, we have this cv2 underscore imshow in this google.colab.patches, which basically do the same thing. So it will like display the image. So that is the purpose. So let's like run this cell to import all the libraries. And apart from this, we need this TensorFlow keras in order to build our model. So that we will import later. So now the next thing that we are going to do is like display the images. Okay, so we have this dog image, cat image, and so on, right? So we are going to display these images. So I'll create a text here and say displaying the images of dog and cats. So we will like take this particular files and we will like display this using this like matplotlib library. So first thing we are going to display dog image. Okay, so here I'll create a variable as img, and now I'm going to say mpimg, which is our matplotlib dot image, so which we have imported here. So mpimg dot imread, so this will read the image file, and the image file that I'm going to read is this some of these files. So I'll go to this files, so you can try opening this. I'll copy the path and paste it here. And after this, so we know that these are all the name of the files that is present in this train, right? So I can just put this name here. So I'll just take this dog 8298 dot jpg. Okay, so this is these files we know that are present in this train folder, right? So I'll paste it here. So this will read this file in this variable called as img, and now we can create another variable called as img plot. So this is to display the images in this like output cell itself. So here I'm going to say plt.show img, and then I can like, I think we can do this as plt.show itself. Let's see whether it is working. So first we are reading this through this mpimg.imread, and we are like displaying this through this matplotlib.pyplot as plt. So let's run this. Okay, so seems we have to load this to a variable. So I'll just say this as img plot img plt is equal to plt dot show of this image, and then we can say plt dot show. Let's run this. And the truth value of it more is ambiguous, so seems there is an error. So let me just check. So mpimg plt dot, okay, so this should be plt dot im show. So as we can see here, this will display the images of the dog that we have. So similarly, you can take a different file and you can just replace this here. So that will like display the images of the dog or cat that you're working on. And now let's try to do the same thing, but let's try to display the image of a cat. Okay, so here let's copy the name of some cat file. So here we have cat.454352. So I'll copy this particular file name. and let's paste it here. So this should be a cat image, right? So let's see. Okay. Here you can see this. So similarly, we have images of dogs and cats. So I'll just replace this with cat image. Okay. So the main thing that we have to note here is we have 25,000 images that we know, but all these images are of different shapes and size. So this is, you can see, the x-axis size is 450 or 500 or something. So in this case it's like 400 or something. So all the images are of like different size. So this is a very important thing to note, because while you're training your neural network, all the images should be of same size. And for our case, we are going to use the model called as this mobilenet v2, and it kind of needs the images in a specific shape, which is like 224 into 224 pixels. So that means like x-axis length should be 224 pixels, and this y-axis length should be 224 pixels. So that is one main thing, and we have to take all these images and resize all these images to the said pixel. So then only the model can like read this data. So that is one thing. And if you want, you can also convert this RGB images. So we have already discussed in a different video on what these RGB images are, basically the colored images. So if you want, you can take this colored image as well. If not, you can convert these images to grayscale images, which are black and white images. So these images will be smaller in size, so your training will take place in a short period of time. So that is like the other processing that we can do, but in this case we will just go with the RGB images itself. So these are some of the data processing or this image processing tasks that we do. Okay, so the main thing is to resize all the images to a common size, so common pixel value. That is the other thing. Okay, so next what we can do is like resize all these images, as I've said. So I'll create a text file. So similarly, you can like print and see like different images of this dogs and cats using this particular file name. So now I'll create another thing as resizing mm, all the images. Now, in this case, we can directly resize this images, store it in some NumPy arrays, and then like train your model from it and so on. But in this case, what I'm going to do is create a different directory, resize all these images, and put those images there. Okay, so that is what I'm going to do in this case. So because let's say I want a copy of this original images as well as the resized images. So in this case, you can follow this particular step where we save this resized images. And as I've told you, we are using a transfer learning technique where we use pre-trained models. So I'm going to reduce the number of images that we need. So we totally add like 25,000 images, right? So here you can see. So I'm not going to, so it's probably like there are 12,500 cat images and 12,500 dog images. So you can like see this somewhere here. I think it is mentioned here. So, so let me just go to this overview. Okay, so I think here it is. So the training contains 25,000 images of dogs and cats. Not sure whether some information are there. Okay, so we can also calculate this by a simple for loop. Let's do that. So I'll create a code cell here. So now what I'm going to do is, we know that this file names is a list that contain the name of all the images, right? So now I'm going to take this file, iterate through a for loop, and find like how many dog images and how many cat images are there. So we know that all the dog images are like named with this dog dot some number, and cat images are named with this like cat dot some number, right? So here I'll create a for loop. So I'll just create the same list here, so that it's like clear for you, so that it doesn't like confuse like once you're going through this code. So we have this file name. So this is basically a list that contain all the images of these dogs and cats. So I'm going to say for like file, or let me just say this as for image file in file names. So we are iterating this list which contain the image, like the name of the files of dogs and cats. So this image file is nothing but a list. So let's just print this like 5 times. So let's say for I in range length of file names I'm going to say print this file name. Sorry, so it should so file names, which is the list, and we can like mention the index. So this will like print the name. So I'm going to print the first 5 files. So for I in range. Okay, so let's not put this as I in range. So let's put this as for I in range of 5. So this for loop will run for like 5 times. So here we can say, I think we can run this. So this will print the first 5 files there are. Now this will like give this, right? So these are basically string values. And now what I'm going to do is like create another variable called as name. So name is equal to file names of file. So each time this for loop runs, this will take the name will take this names. Okay, and now I'm going to print the first 3 letters. So name of 0 to 3. Yeah, so this will give us this dog, cat. So the basically the first 3 letters. Now we can count this using this. So here I'll say this file name. Again, you don't have to like run this every time, this file name, so it will be the same, but I'll just create this list here. Now I'm going to say for image file in file names. So each time this image file will take the name of the file that we have, and now I'm going to create a variable called as name. So name is equal to, so let's say image file of 0 to 3, so the first 3 letters. And if this first 3 letters, so if this name is equal to dog, so I'm going to create a count. So let's create a counter. So I'll call this as dog image count as dog count is equal to 0. So let's initiate it with 0, and let's say cat count is equal to 0. So we are basically doing this to calculate like how many dog images are there and how many cat images are there. So nothing like complicated here. So when the name is dog, so I'm going to say dog count plus is equal to 1. So I'm just incrementing it with 1. So if every time there is the name of the file starts with this dog, so this dog will be incremented by a value of 1. And then we can include a else condition where we know that the name should be like cat. So here I'll say cat count plus equal to 1. Okay, and finally we can just print this. So print number of dog images is equal to dog count. And similarly we can do this for this cat images as well. So this is number of cat images. Okay, so I'll run this. So see, as we can see, so it basically contains equal number of dog images and equal number of cat images, but we are not going to take all this like 25,000 images. So we are just going to take like 2,000 or 3,000 images, and then like take those images and resize those images alone, because we are not going to use all these images, so it doesn't make sense of like taking all these images and resizing it. So first I'll create a directory. So creating a directory for these resized images. Okay, so here you can just create a new directory as like this new folder or something. So instead you can use this os library. So I'll just say os.mkdir. So this is nothing but make directory. So here I'll say this path, which is this content. Okay, so for like it should be forward slash content. So I'll say forward slash content, and again slash, I'll name this to image resized. Okay, so this is the folder where we are going to store like all the resized images. So I'll run this. So now this will create a directory called as image resized tier, right? So this is basically a empty directory now, and now we are going to save all the resized images in this particular directory. So that will be the next step. So I'll create another variable as original directory, or let's name this as original folder. which is the train folder, which contains all the images with that original shape. So I'll copy this path of this train, paste it here, and then I'll create another variable as resized folder. So here let's paste the path of this image resized path. So let's copy the path, paste it here. Okay. Now we know that like we have to iterate through this files name list, right? So it is basically a list that contains the name of the files. So similarly, we are just going to iterate only the first 2000 images. So here we have like iterated through the entire thing and found that totally there are like 25,000 images. But I'm not going to do that. So I'm just going to run this for loop for like 2000 times, so that it will extract me only 2000 images. So I'll say for I in range of 2000. So this for loop will run like 2000 times, and each time I have to take a file. Hmm. I'll say file name, just a file name is equal to os dot list directory. So this is, we have already seen this, so this will like list all the files in a folder. So what I'm going to list is this original folder, this content train. So this will like do nothing, just do what we have like done here. So this will create a list that contains like all the names of the image files. So once I create this, I'll give this as image path. So image path is equal to this original folder plus file name. Okay, so and again, so the main thing here is we have to include a forward slash here as well. So let me tell you what this does. So first, this is nothing but the original folder, right? So original folder is the path of the train folder. But what we are interested in is finding the path of the image, which is nothing but this one. So content train and this image name. So here it is like content train doc point 8298, all these things, right? So this is what this image path will do. So first it will take this original folder and concatenate the name of the file. Okay, so that is what we are doing, and so it should be original folder of I, original folder I, because like each time this for loop runs, it will take one file. Okay, so the let's try to understand this. So this for loop is running for the first time. So this file name is equal to os.list directory of 5. That means os list directory of 0. So this will take this image name, which is doc.1206.7.jpg, and now we will like add these two things. So that will be stored, file name stored here, and this will concatenate these two things. So this path name and this image name. So the second time this for loop runs, so it will take the name of the second file, which is cat.11189.jpg. So that will be stored in this file name, and then we are like concatenating it with original folder plus file name. So we are just doing this in order to give the path of all these individual files. So once you have this path, now we can resize it. So I'll create a variable as image img, and I'm going to use this image.open. So this image.open is nothing but the function that we have in pillows library, so which we have like imported here. So from pill, like we are importing this image. So from this we can like open this image and resize it. So image.open. So I'll copy this image path and paste it here. Okay. So later I'll say image is equal to img dot resize. So again, as I've told you, MobileNet expects the images to be in the size like 224 comma 224, and this is like the like pixel range like that most of the pre-trained model has. Okay, so you have to say image dot resize, open parenthesis, and within another parenthesis mention 224 comma 224. So this is the it's kind of the horizontal number of pixel and vertical pixels that we have, and then I can say image is equal to img dot convert RGB. Okay, and now I'll say new image path. So this new image path is equal to this resized folder. So we have to save this in this new folder that we have created, right? So resized folder plus file name. Okay, later we can say, so we are just saving that with the same file name. So the only difference is that the directory changes. So it will be saved in this image resized. So new image path, and then I'll say img dot save of new image path. So yeah, so that is also, let's try to understand this for loop. So first we are creating two variables with the name of the original folder, which contain like all the original images which are not resized, and then we are creating a directory here which is called as image resize, which will contain all the images that we are going to resize. And now I'm creating a for loop that will run for 2000 times. So each time this for loop runs, this file name variable takes the name of each individual image file. So that is what we have mentioned this. So I is basically the index of this list, which gives you the name of the file. Then we are like creating this variable called this image path, where we are concatenating this path and this file name. So that's what I have mentioned here. So folder, original folder plus file name. So this is basically the individual path that we take. So each time the for loop runs, so image path is the full path of a image. So we take that image, pass that to this image dot open, which will like read this file, and then we are resizing this using this resize. So again, this resize is present within this pillow library. So we are opening this image using this image dot open, then resizing it to size of 224 comma 224. So if you wanted to convert this image to a size of 200 comma 200, you can like mention it here. And then image dot rgb convert, which basically tells you that colored image. So this is again a mandatory thing. And then once you have resized this, we have to save this image, right? So I'm giving this new image path, which is nothing but this resized folder. So make sure you are including this forward slash at this end, otherwise it won't work. And then we are like saving this image. So let's run this. So this will probably take a minute or two, because like as we have like several images, it takes some time. So here we are like resizing 2000 images. So once we resize this image, let's try to like display the images and see whether all the images are of same shape. So like what we have did here, so I'll copy this cell, so let that code run. I'll paste it here. So this is for resized images of dogs and cats. So display dog image, so I'll name this as display resized dog image, and here it should be this path. This image resized path is where our new files will be stored. So I'll copy this and paste it here. Okay, so this cell like completed running. So all the 2000 files will be resized, and it will be stored here in this image resize. So now let's print this. So here you can see, so the size is like almost it's 224, and it is like 224 here. Previously it was like something around 450 and 400 or something, right? So this is how you can like resize this images. And let's try to do the same thing for this cat image as well. So previously we know that these two images are of different shapes or size, so basically the dimensions. And now let's try to do this for the resized cat image. Resized cat image. And now I'll just copy this image resized. So this will also contain the image in the dimension of 224 comma 224. Let's try this. See, so it's like 224 and 224. So both these images are of like same dimensions. So like all the files, all the image files in this image resize will contain the images in their resized formats. Okay, so you can like again display different images, and you can like recheck here. So the next thing that we have to do here is like create labels for this images. So we have this dog image and cat image, right? So I'm going to create like labels for this, and you cannot like randomly create like zeros and ones here. So let's say that we are going to label this cats as a zero and this dogs as zero. So how I'm going to create this labels is go through this image resized and check whether the image starts with dog. If the image file start with dog, so I'll label it as one. If the name starts with cat, I'll label it as zero. So that's what we are going to do. So this is for creating the label. So I'll create a text here and say as uh, creating labels for resized images of dogs and cats. Okay, I'll just put this in bold. And like I'll take all the cat images and label them to 0, And in the case of dog, let's label them to 1. Okay, so you can like change this to vice versa, so you can label cats to 1 and dogs as 0, so that will like work as well. So how we are going to do this is create a for loop that will like iterate through this image resized folder. So if the file name starts with dog, we have to label it as 1. If the file name start with cat, we have to label this as 0. So similarly, like what we have done here, so in this case, so we have like iterated this for loop through this list and check whether the first three letters is dog or a cat, right? So here we have just found the count of dogs and cats. So similarly we are just going to create the labels as well. So I'll just mention a comment as creating a for loop to assign labels for these images. Okay, so I'll create a list called as labels, and this is a empty list, so this is where we will like append all the labels. And here I'll say for I in range 2000, so because we know that we totally have 2000 images, and I'm going to say file name. It's basically the same that we have did here, so file name is equal to names of I. So again I'll create a list like this. Okay, so let's create a list. So the main thing is you shouldn't like mention train, but mention this image resized path. I'll copy this path. Okay, so file names os.list directory labels for I in range 2000. And so file names, so it should be file name. So this is what I have mentioned here. So each time the for loop runs, so this file name will take the names of that individual file, and then I'll create this as label. So label is equal to file name of 0 is to 3, which basically tells you whether it is a dog or cat. So like what we have did here, so we are just checking whether it is a dog or a cat, so we are just slicing the string. Okay, so label is equal to this file name, and then now we can introduce a if condition. So if this label is equal to dog, in that case we can say labels. So labels, this labels is nothing but this list. Okay, so or else I'll just, yeah, so let it be labeled, so I can say labels dot append 1. And now I'll include a else condition and say labels dot append 0. Okay, now let's try to understand like what happening here. First we have like did this like several times. So I'm creating a variable which is basically a list, so it contains a list of all the names of the images of this dogs and cats. So once I have this, uh, I'm creating another empty list called as labels. So this is where I'm going to store like all the labels for I in range 2000. So this for loop runs like 2000 times. So for the first time, I will take the value of 0, then 1, 2, 3, and so on. So this will go on until like 1999. And each time I mention this file names of file, so file name will take the name of a file, so each individual file. And I'm creating a variable called as label. So this label is nothing but the first three letters of that file. Say for example, when we run this for loop for the first time, so we take this file name and then slice this first three letters. Okay, so when it is a dog file name, so this will extract this dog. When it is a cat file, it will like again slice the first three values, which is this cat. Okay, so I'll also try to print this as well. So okay, so let's do one thing. So we are just slicing it. So if that sliced string is dog, we will append 1. If it is not, we will append 0. So this basically tells you whether it is a dog or cat. So let's run this, and now I'll just print the first 5 files here. So file names of 0 to 5. Print file names. So we have this dog, cat, and all the things and so on. So if you go here, so 12067, it's probably the same order, or the order may change, but like we are not sure about that. So we have this file names, image resized. Now you can also like check the number of files. Okay, so I'll remove this and say length of file. So totally there would be like 2000 images, right? Now I'll print this labels. So it should be done here. So the only difference is that now we are finding this for labels. So as we can see, if it is a dog, the label is 1. If it is a cat, the label is 0. So this is what we have done here. So we take each file name, slice the first 3 letters. So if those 3 letters is dog, we will append 1 to this label list. If it is not, we will append 0 to this label list. So this is how it works. So the training data for our neural network is all these images of dogs and cats, these 2000 images, and the labels will be this particular list, whether it is a 1 or a 0. So here I've printed only the first 5 elements, so but it totally contains like 2000 elements, as we can see here. Okay, so you can now count how many dog images and how many cat images are there, because we have just took the first 2000 values, like 2000 images or something. So we know that in total it is like distributed as 12,500 dog images and cat images, but we have to check whether the distribution is equal in this case as well. So this is for so within this 2000 images I'm going to count how many dog images and cat images are there. So for that, so I'll just mention a comment as counting the images of dogs and cats in dogs and cats out of 2000 images. Okay, so for that, you can just say values comma counts is equal to np dot unique. So this np numpy, we know that np is numpy library, and there we have this unique function that will tell you like how many unique values are there. So in this case, unique values are 1 and 0. So here we have to pass the labels list and say return counts is equal to true. Now I'll print this values and also the counts. Okay, so this tells us like 0, which means like cat images are 992 and dog images are like 1008. So total you have this 2000 images. So the distribution is like almost even. So it is like we don't have like 500 cat images and 1500 dog images and so on. So it's like almost equal. So we don't have to worry about this. So if the distribution is uneven, in that case you have to like build a for loop differently here, where there can be like even split of this dogs and cats, but this 992 and 1008 is like we can like work with that, so there is no issues here. Now the next step is to, before training our model, we have to read all these images and convert them to numpy arrays. So that will be the next step. Okay, because we know that our models cannot understand images, but they understand numbers. So we have to take all these images and convert them to arrays. And I have also like explained in the previous videos on how this image processing works, and how to extract this pixel values and convert that to numpy array. So if you have not watched those videos, I'll just give you the link of those videos in this video description. You can just check that out. So here I'll just create another text as converting all the resized images to numpy arrays. Okay, so here I'll import cv2, which is the OpenCV library, and we need another library called as glob. Okay, so these are the two things that we need. And here we just given the directory which contain all these resized images. So we will read all the images here and convert them to numpy arrays. So that's what we are going to do. So I'll create a variable as image directory. So this image directory is nothing but just copy this image resized path, and don't forget to mention this forward slash here, and then mention this image extension. So this is important thing, so it might not be necessary in this case, but you might need it somewhere else, so in some other like data set. So I'll mention png and jpg. So in this case I think like all the files are in this jpg format. Here you can see this list. I think like all the images are of JPG format, but in some data set the images will be in JPG format and PNG format. So in that case, like it's better to mention this extension in this list. Try with these both extensions, so in that case it will work. So if you have PNG and JPEG images, so if you don't include this line, in that case you may get error in your code. So I'll create a list called as files, as empty list, and then I'll say files dot extend globe dot globe. So this is basically to read all the images, and I'll say image directory plus, so we have to mention an asterisk symbol plus dot. So I'll explain you what, like why we are doing this. So let me just complete this quickly, and I have to say for e in image extension. Okay, so after this we can say dog cat images is equal to np dot as array cv2 dot imread file uh, for file in files. Okay, so let's try to understand what we are doing here. So first we are importing this cv2 and the globe library, and then I'm mentioning the image directory, which is nothing but the resized image directory, which contains 2000 resized images, and then I'm mentioning this image extension as well. So let me just run this cell, so it will take some time. So in that meantime I'll explain you what's happening. And then we are like creating this empty list called as files, and I'm mentioning this files dot extend globe dot globe. So it is basically again to locate that file. So image directory plus this asterisk of dot. So as I've told you, in this case you don't have to do this because all the files are in JPG format. So if you have this JPG and PNG format, you can do something like this, which is basically to either check whether the file is PNG or JPG, and then like convert it to a numpy array. So that's why we use this, and we use like a for loop to iterate through this PNG or JPG. So just two things here, and then after that we creating this like a numpy array. So I'm just saying this as np.as array. So cv2.imread for file in file. So now this file, so we are like appending it here. So files.extend is like similar to this extend like appending, where we are like uh, taking each file names, and then we are like reading this file. So reading this file through this cv2.imread, which is using this opencv library. So after that we are converting all these things into numpy array. So this cv2.imread will read an image and convert it to a numpy array. So the reason we have this np.as array is all these images are now in the form of a numpy array, and all these numpy arrays will be in a single numpy array. So that's why we have this. Okay, so this will take each individual image, convert it to numpy array, and this will uh, put all those numpy arrays in a single numpy array. So that's the reason behind this. I'll just check whether this code is right. So just a minute. So png files dot extend globe of globe image directory e for e in extension, and dog cat images mp.as array cv2.imread for file in files. Okay, so let's run this. So this is the final data that we have, which we will like pass it to our mobile net model in order to train it. Now I'll just try to print this dog cat images. So now all these should be converted to numpy array, as you can see here. So these are nothing but the pixel values that we have. So these are like present in a numpy array. So you can also like print the type as well. So type of dog cat images. So this is nothing but the data of all those 2000 images, not like one single image, because we have like we enclosed all these image files. So as I've told you, so each time this for loop runs, so it will take one image and convert it to a numpy array. Later we put all these files in a single numpy array. So it is nothing but this dog cat images. Now let's check this shape. So I'll say print dog cat images dot shape. So this will tell you like there are 2000 images, and each image is of shape 224 comma 224 pixel, and this 3 represents the RGB image. So if this value is 1, that means the images are like grayscale images, or you won't get a number here at all. So that means like the images are converted to grayscale, and when you have RGB images, this 3 will be there. So this 3 is nothing but the red, green and blue intensity values that are there. So we have 2000 images of shape 224 comma 224, and 3 basically represents the RGB images. Okay, so now this is the data that we have. So now we take this 2000 images and we take the labels that we have created here. So labels is present in this labels list, right? So we take this and then we will like apply train, test, split, and again do the training and all those things. Okay, so I'll just like create two variables as x and y because it is like more convenient. So x and y. So let's take this dog cat images. So I'm just basically renaming the numpy array here, and I'm going to take this labels list which contains this 1 0 and all the things here. Yeah, so I'm just going to take this labels which is in the form of a list and convert it to a numpy array and then store it in this y. So I'll say np dot as array. It should be as array np.array. So here we pass this labels. Okay. Yeah. So this X will now contain the images of dogs and cats, and the corresponding labels will be stored in this Y. And now we can apply our train test split. So all the other things are something that we already know. So train test split. So here the main thing that you can notice, the number of images that we take is 2000, which is very small in terms of deep learning, right? So we often train with like uh, 20,000 images or 100,000 images or so on. So here I'm just taking a small data set, but we will get a good result as we are using a pre-trained model. So like that you can see while we complete our training part. So now we have to apply this train test split. So I'll create four arrays as we often do. So X train, X test, Y train, and Y test. So this is equal to train test split. So we have already imported this. So if you remember, we have imported this train test split function from this sklearn.model selection. So we imported this train test split function. So this is what we are like using now. So here I have to pass this X and Y. So X is my data or my images and Y is my labels. And now I'm going to say test size is equal to 0.2, and then I'll say random state is equal to 2. So again, in random state you can mention any number. So this test size is nothing but the size of your test data. So test size is equal to 0.2 means I want 20 percentage of my images to be test data. The remaining 80 percentage will be my training data. So out of this 2000, 20 percentage will become my test data, and out of 2000, 80 percentage will be my test data. Random state is nothing but I have like explained this several times before. So if you don't know what it is, each time you run this train test split, your data will be splitted in a different manner. So your train data will contain different images and test data will contain different images. So if you want the same split to happen every time, you mention the same number here. So every time you mention random state is equal to 2, your data will be splitted in a similar way. If you mention 3 every time, in that case your data will be splitted in a similar way, and so on. So this is just to replicate that train test split. And once you run this, all the training data images will be stored in this X train, and all the labels, either 0 or 1, will be stored in your Y train. So the corresponding labels for this X train will be stored in this Y train, and your test images will be stored in this X test, and the corresponding labels will be stored in this Y test. So let's run this. Okay, and now let's so this process is complete. Now let's try to check the shape of each thing. So print x dot shape. So this is like the original data set, and now I'll print this x train dot shape and x test dot shape. The X is our original data which contain like 2000 images, as we can see. So this is the 2000 images and the corresponding shape. So this 1600 is nothing but the 80 percentage of data which is my training data, and the 20 percentage test data will be is nothing but my 400 data. And again we have this 224 comma 224 as the dimension of the images and 3 as the RGB image. Okay, so here I'll just mention that we have 1600 training images, and 400 test images. Okay. Yeah. Okay, so we have like splitted this training and test images. Next, before training the neural network, we have to scale this data. Okay, so I'll create a comment as scaling the data. So the scaling is nothing but we have the pixel values like 121, 101, 84, 83, and so on. So the range is like a bit higher, right? So now what I'm going to is do is like scale the data, so all the values are in the range of 0 to 255, sorry, 0 and 1. So again, I've explained in that video where I like explained about image processing that your pixel value ranges from 0 and 255, where 0 means it's black color and 255 means it's like complete white color. So all the pixel value will be in this range between 0 and 255. Now if you wanted to scale this data between 0 and 1, so you need to divide all the values by 255. So that's what we are going to do. So let's call this as extreme scaled is equal to extrain or training data, and it's divided by 255, the maximum value. And similarly we have to do this for test data as well. So this is my x test scaled, x test divided by 255. Okay, so I'll run this. So this will take like all these values divided by 255. Let's see what is the end result that we are getting. So I'll run this. Now I'll print this. So this is my training data scale, this is my test data scale. So this x train and x test are nothing but what we have splitted here. So I'll print this x test alone, sorry, x train scaled alone. As you can see, the values will be in the range of 0 and 1. So this is what this scaling does. Now we can build our neural network. Okay, so I'll create a text as building the neural network. As I've told you, here we will be using a pre-trained model called as MobileNet. So here I'm going to import my TensorFlow library. So I'll import TensorFlow as TF, and you can get this MobileNet V2, this pre-trained model from TensorFlow Hub. So I'll import TensorFlow underscore hub as uh, hub itself. So I'll run this. Okay. So this is where this model is. So you have to mention this link. So this tf hub dev, this mobilenet v2 feature vector under like /4. So this is the link for it. So I'll create a model name for this. Let's call this as mobilenet model, and here we have to mention that path, this url. Okay, so I'll copy this url and paste it here. So you can just look this url somewhere, save this like somewhere, so that you can like use it later. So now I'll call this as pre-trained model, and we have to mention like some parameters. So this pre-trained model is equal to up dot keras. So this k should be caps. So keras layer, and in the parenthesis you have to mention the name of the model, which is this mobile net model. So this will basically like download the models weights and so on, the model, and then we have to mention the input shape. So this input shape is nothing but 224 comma 224, which we have like resized, comma 3. So this 3 is nothing but it says the images are like RGB images. Then say trainable is equal to false. Okay, so as you can see, it's just to tell whether the model is like that particular layer is like trainable or not. So I'm taking this mobile net model, so mention this particular url, so this should not change. And I'll create another variable called as this pre-trained model. So up dot keras layer, so this up is nothing but tensorflow hub. So mobile net model is nothing but url of the model that we are extracting from this tensorflow hub. And the next parameter is this input shape. Finally we have this trainable. Yeah, okay, now we can run this. So the as you can see, so this will like download this mobile net model, and now we can train this. So I'll create a variable called as number of classes. So number of classes is nothing but how many types of images you have. So here we have two types of images, right? So one is dog and the another one is like cats. So here I can say model is equal to tf dot keras dot sequential. So we have like already used this before. So even when you're like building the model from scratch, we use this tf.keras.sequential, and within the sequential create a list. So mention this square brackets, and here I'll say pre-trained model, and this will be my first layer. Then finally I need my tf.keras.layers.dense. So this will be my output layer. So here I'll say number of classes. So number of classes, I mean, you can say number of classes, or else you can just mention two here. So this like if you have like three images or three types of images in your data, so it should be like 3 years, so that like won't change. Okay, and finally let's print this model summary, model dot summary. Yeah, okay, so mobile net model, the URL of this mobile net v2, then pre-trained model is the like variable name, up keras layers and all these things. So input shape and trainable false, and then we have to mention this tf.keras.sequential. So pre-trained model. So again, so this mobile net v2 model has a specific architecture, so it contains a set number of convolutional layers and all the things and so on. So the only thing that we need to include is this output layer. So in the output layer we have to say how many classes are there in our data set. So mobile.summary. So this will tell you what is the layers that you have. Okay, so keras layer, so this is for the mobile net model that we are using. So these are the count of those parameters and so on. So you can do some research on this. So you can go to this TensorFlow hub, you can go to this mobile net v2, and this is the image. So as I've told you right earlier, that in transfer learning the model will be trained previously on a data set, and we can use a similar data set and train in a different use case. So go to this ImageNet ILS VRC and so on. So just search it in Google, so you can see like the data set on which this model has been trained. And if you wanted to learn what is the architecture of this model, you can just go to Google and search it. So it will basically tell you like what are all the different like layers are there in this particular model. So if you want, you can like create this from scratch as well by mentioning like all these things. But again, we know that it will take a very long time to train, as this data set is probably a very larger one. Okay, so you can do some research on this data set as well as this mobile net architecture as well. So probably we will discuss later about in detail about like what these individual layers are and how this model works and so on. But for now you can do some research on this. So this is the thing, and now we can compile this model and train this. So I'll say model dot compile. So here we will like mention what is the loss function we are going to use, what is the optimizer and so on. So I'll say the so let's say model dot compile. So optimizer is like the most widely used one, which is the Adam optimizer. And then loss function is something that we have to mention. So I'll say loss is equal to tf dot keras dot losses sparse categorical cross entropy. So you can like do some again research on what are all the different loss functions there are. So tf dot keras, okay, so it should be keras dot losses dot sparse categorical cross entropy. Okay, so within that I can see from logits is equal to true, and the matrix is nothing but we can take this accuracy score. So I'll say matrix is equal to, within list we have to say this ESCC, which basically tells it's as like the accuracy. Okay, so model dot compile, my optimizer is Adam, and loss function is the sparse categorical cross entropy. So this is like a normal label encoder. So we use this sparse categorical cross entropy. So if you use one not encoder labels, in this case we use the simple categorical cross entropy, and we have mentioned this matrix is equal to accuracies. Now let's run this, and finally we can train our model. So I'll say model.fit, and within this we have to pass our training data, which is my xtrain scaled and my labels. Okay, so I'll just go here. So we have to pass this xtrain scaled and this y train, the corresponding labels. Okay, so model dot fit xtrain, so x underscore train scaled, comma y train, and you can mention epoch. So this will probably take some time, but it will give you good results for like 5 epochs alone. So if you want, you can like increase this epochs. Like you can also include some more hidden layers, and see like how your accuracy changes and so on. So if you include more, there is a chance that our model might overfit. So I'll run this. So this will like train our neural network for 5 epochs, and you can see like what is the accuracy that is like taking place here. Okay, so you can in the meantime, again you can see like what is your loss function value and how your accuracy score is changing. Okay, so this, as I've told you, will take some time, and let's wait until it's trained. So I'll just pass this and resume once this training is done. Okay, so this took a time of 4 minutes in total to train with the set 1600 training images which we have like seen here. So we totally have like 1600 images. So for 5 epochs we took like 4 minutes to train this model, and you can see this loss function value and the accuracy value. So in the first epoch we started with this 91 percentage accuracy, so it kind of increased to 97, 98, and so on. So the final accuracy in the fifth epoch that we got is like 99 percentage, which is a very good accuracy for the very small amount of data set that we have taken. So this is the advantage while we use like transfer learning or the pre-trained models. So we know that this is the training data accuracy. So that this is not all. So we have to do the same thing and find the accuracy for test data as well. So I'll create like two variables called as score and ACC, which is my loss function value and accuracy score for test data. So I'll say model dot evaluate. So this model is the model that we have created. So model dot evaluate, and I'll say x test scaled. So this is my test data, and I'll pass the test data labels as well. So what happens here is like the model will predict the labels for this X test images, and that will be compared with this Y test, like the real labels, and then we will get this accuracy score and basically the loss function value and the accuracy score. And later we can print this as uh, test loss, the loss function value, and score, and the accuracy score value. So this will be my test data accuracy, which is the most important metric. So this test accuracy is equal to ACC. Okay, so this will take few seconds, but not like that much time. You can see the accuracy, it's almost 98 percentage. So we can like take this as 97 percentage. That means like out of 100 images of dogs and cats, our model can correctly predict for 97 images. So we can say, so test accuracy of 0.977 means like 97.7 percentage. Okay, which is a good accuracy. So this is how you can train this transfer learning model, or basically the pre-trained model of MobileNet v2, and you can like build this classification system of dogs and cats. So we just have like one more thing to do, which is to build a predictive system where if you pass a new image of a dog or a cat, our model should say whether it is 0 or 1, basically whether it is a dog or cat. So here I'll create a text as predictive system. Predictive system. So There are like few lines of code that we have to do here. So I'll create a variable as input image path and is equal to, so let's get this from the user itself. So, I mean, in a more detailed use case, so what you can do is build a simple UI in Streamlit or Flash, and keep an upload button or something where you can upload an image, and in the backend your model can predict whether it is a dog or cat, and then you can like deploy that using Streamlit or Heroku. So I'll say path of the image to be predicted. Okay, so path of the image to be predicted, and then I'll say input image is equal to, so let me just put this as image as well. So input image is equal to cv2.imread. So this will basically convert the image. So this will read the jpg image into a numpy array, so cv2.imread, and within this we have to put this input image path. Okay, so input image path. Later I'll also display this image as well. So for this I'm going to use cv2 underscore imshow. So note that this is not cv2 dot imshow, as I've told you previously. So there is an imshow function in OpenCV, that is cv2, but it won't work. So as an alternative, from this google.colab.patches I'm importing the cv2 underscore imshow, which is basically the same function. So cv2 imshow, and within that we have to pass this numpy array of input image. So what happens is, like we mentioned the path of the image for which we need to make the prediction, and then we display that image and finally make the prediction. So the next thing that we have to do is like resize the images like what we have done before. So input image resize is equal to CV2. So previously we used like pillow to resize. Similarly, you can use this OpenCV library as well. So I'll say input image, and in the next parameter you need to mention what is the dimension that you want, which is 224 comma 224, and then this we have to scale this now. So let's call this as input image scaled is equal to this input image resized divided by 255. So what we have already done, now we have to reshape this. So let's call this as image reshaped. So I'll tell you like what is the purpose of this. So let's use np.reshape input image scaled, comma, so in a list I'll mention 1 comma 224 comma 224 comma 3. I'll explain you what this means after completing this. So, and then let's create another variable as input prediction. So this is where our final prediction will be. I'll say model dot predict. So here I'll pass this input image reshape. So image reshaped, mm, input pred label. For this I'm going to use np.argmax of input prediction. Okay, so now let's try to understand what's happening here. So first we need to mention the path of the image. So what we will do is upload a new cat image or a dog image, and once we run this, so this will like ask for the user for the input. So there we will paste the path of this image, and then we will read this image and load it to a numpy array using the cv2.imread. Okay, so after that we will display that image using the cv2 underscore imshow. Later we will resize the image to this. Okay, so this should not be 224 comma 224, so this should be 1 comma, okay, sorry, just okay, okay, yes, this is correct. So this is the first reshape that we do. So the image can be like 500 into 500 pixel or 1000 pixel or something. So we are reshaping this to 224 comma 224. Then we are like scaling this image because we know that we want the values to be between 0 and 1. Later we are reshaping this numpy array. So the reason is it is to tell the model that I'm making prediction for only one image. So I mentioned one here, and 224 is the dimension of the image, 3 is the RGB image. So this one is nothing but I'm making prediction for only one image. So if you are passing like 3 or 4 images, so you will mention that images here, but here we are like interested in only one image, so I'm mentioning one here. And finally we can pass this reshaped array to this model.predict, and then we can apply this np.argmax. Okay, so this np.argmax is nothing but just the prediction. So when you use this model.predict, you will get the prediction probability of whether it is a dog or a cat. Okay, so say for example, the final result will be something like this. So let's say it's 0.85 and 0.20 or something. So this is like, let me put this as 0.15. So this can be any value. So this is 0.85 is what is the probability that the label is 0. This is what is the probability of the label being 1. So it is like telling there is a 85% chance that this image is a cat, and only 15% chance that it is a dog. So this is the result that you get when you have this model.predict. Now when you apply this np.argmax, it will see which number is maximum, whether it is first number or second number. So here the first number is maximum, so the final value is 0. If the second value is maximum, the final value is 1. So this is just basically to have that final prediction in terms of labels. So this model.predict will give you only this probability value. So we are applying this np.argmax to find which value is maximum, either the first value or second value. If the first value is maximum, you will get the value as 0, that means it is a cat. If the second value is maximum, that means it is a dog, you will get a 1. So later we can say if this input red label is equal to 0, so I'll say, so I'll basically print the image represents a cat. Okay, because that is the label that we have created, right? And else we will say the image represents a dog. Okay, so this is the simple if condition. So you, all you have to do is like pass in the path of the image, then it will convert it to numpy array, display the image, then all this resizing, scaling and reshaping will happen, and then we finally make this prediction. Okay, so before like doing the prediction, I just wanted to download some dog image and cat image. So I'll just search as dog images. So let me just open this image and download this file. Save images. So I'll just save this in my desktop as dog.jpg, and let's do the same thing for cat as well. So our model should predict this. So cat images, so can just download some image. So as you can see, it can be any dimension because we are anyway reshaping this. So I'll save this as cat.jpg in the desktop itself. So now I'm going to upload these files, dog image and the cat image. So I'll go to this upload, go to my desktop, and I have this, yeah, dog and okay. So let's upload these two things. So once this is completed, so I'll run this. Now first I'll copy the path of a dog, this dog.jpg. So I'll copy the path and paste it here. Okay, let's press enter. So this should display the image and give the prediction. So path of the image should be predicted as this dog, and we are displaying this dog. So this image is displayed using the CV2 I am sure, and this tells the image represents a dog because the prediction that we get is this, 0. So if you want to understand this clearly, I'll also print the prediction as well. Let's print input prediction. Let me print this here, and let's print this input red label. I'll show you how this will be for the same dog image. So I'll paste this here. So here the second value will be okay. So I have to pass, like, sorry, paste the path. So yeah, this copy path. Okay, so this dog image is placed, and then you can see, so this is the probability of the image being cat, and this is the probability of the image being dog. As we can see, the value is higher for this second value. That means the label is 1. So it says the image represents a dog. So this is how this prediction system works. So I'll copy this entire thing and I'll test this for cat as well. Okay, so let's run this, and now let's copy and paste the path of this cat image. So as you can see, now the first value is maximum. That means the label is 0. Using np.argmax, we have found that. And then we say that this image represents a cat. So this is how we can build this predictive system. Okay. So I hope like everyone is clear with how we have did all these things here. So what I would want you to do from here is like build a simple UI in Streamlit or Flask and deploy this model, so that the final thing that you have is just UI where the user can upload an image, so and that will display this image like this and tell you whether that is a dog or a cat, and you can like use this idea and work on like different use cases, so like predicting different animals or some any classification, any image classifications. And yeah, so that is all. So I'll just give you a quick recap of all the things that we have done from the start. The first is like we are importing this dataset from Kaggle, this dogs versus cats. So this is the same of uploading the kaggle.json file and configuring the path, and then extracting the data through API. And then we are like extracting the zip file, this dogs versus cats.zip and train.zip and so on, and counting that there are 25,000 images of dogs and cats. And then we are importing all the dependencies that we have, and then displaying the image of dog using this matplotlib dot image module, and image of cat and so on. And then we have seen that the first three letters have this dogs and the next three letters have this cat and so on, and we use this to find how many dog images are there and how many cat images are there, and saw that there are equal images, number of dog images and cat images, which is 12,500. Then the important task is we are resizing all the images. So we are creating a new directory called as image resize, and then resizing the first 2,000 images, resizing it of dimension 224 comma 224, and saving it there in the new folder that we have created. And finally we are displaying these images and seeing that these two images having the same size. So we have resized all the images. So the next step is to iterate through this resized folder and create the labels for this. So if it is a dog image, we say the label should be 1. So we are doing this here. And if the image starts with this cat, we say the label is 0. And then we have seen that there is an almost equal distribution of dogs and cat. And then we run this particular code snippet in order to read all these image files and convert it to a numpy array. And later, like we have seen, like there are, like we took like 2,000 images of this dimension and RGB images represented by 3. So next one is like this train test split. So X train, X test, Y train and Y test. So we are taking like 20 percentage as the test data and so on. So 1,600 images will be our training images and 400 images will be our test images. And then we are like scaling the images of 255 and so on. Okay. So the next step is like building the neural network. So we are taking this MobileNet model, MobileNet V2 from this particular link. So this is the pre-trained model that we are using. So you can just go through this code. So we are just applying, adding like one output layer. So this is nothing but 2, the number of classes that we have. And this is a model summary. And we are like compiling with Adam optimizer and sparse categorical cost entropy and so on. We have seen that we get a very good accuracy score, right? And then we have also seen that we got a test accuracy of almost 98 percentage and so on. Finally, we built a predictive system where we can paste the path of the image and it will tell you whether that image is a dog or a cat. Okay. So that is all from my side, and I hope that you have understood all the things covered. So make sure that you are practicing all the code by yourself and try to, as I've told you, try to build a UI for the same, and that will be like very helpful for your portfolio. Yeah. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. This is the fourth deep learning project video in our channel, and in this video we will be working on the CIFAR10 object recognition dataset. So this CIFAR10 data basically contains around 60,000 images of shape 32 into 32 pixel images. So there are 10 different classes. So all these images belong to these 10 categories such as airplane, automobile, bird, cat, etc. So this is basically image recognition problem. So we have to use a convolutional based model, and in this case we will train a neural network, a basic neural network with this data, and later we will use a ResNet 50 model, which is a pre-trained convolutional neural network model, and we try to train that pre-trained model with this CIFAR10 dataset. So this is what we are going to discuss in this particular video, and let's get started. So I've just like loaded this data set here, and I'll tell you how you can do this. So make sure you're in the collab environment, and before connecting your systems, go to this runtime option. So in this runtime option you will find this setting for change runtime type, and in this change runtime type you have to give GPU. So in default it will be none. That means you wouldn't be having any GPU provisions. So click this GPU and click save. So this will reconnect your system. That means once this is connected you have access to GPU. Okay, so the reason we are doing this is it will take a very long time for deep learning models or the neural networks to train, so we use GPU in order to fasten this training process. Okay, so that's the purpose. So that will be the first step. Next is we have to import this dataset from Kaggle. So we are not going to download this data because this is a pretty large file. So you can see the size. So it's like around 750 MB. So we are not going to download this. So instead we are going to download this data directly to Collab using this API. Okay, so I hope that you are sure how to import this data from Kaggle, but I'll just explain you this process quickly. So first we have to make sure that this Kaggle library is installed. So this is the code to run this Kaggle library. So in Collab environment, Kaggle library will be installed, and then you have to the next step is like you have to accept the competition rules. So we have this. Just go to Google and search Kaggle CIFAR10 dataset. So this is the site. So it's www.kaggle.com CIFAR10. So in this, so you can see the link here. So competitions CIFAR10. So here if you will be having some option to accept competition rules, so somewhere here. So once you do this, in the next step only you have to download your kaggle.json file, which basically contains your account informations. So for that, in this top right corner in this account settings, so click here and go to this account. So in this account, once you have accepted the competition rules, scroll below and give this create new API token. So this will download a kaggle.json file. So once this JSON file is downloaded, you have to come back here and upload this file. So once you have downloaded this file, so come to this files and upload this. So if the name of the file is different, like kaggle 1 2 or something like that, make sure you are renaming this to kaggle.json. So this is very important. So once this step is done, once uploading this kaggle json file is done, so just copy this code and run this. So this is like configuring the path of this kaggle.json, so this doesn't change for any data that you are getting. So run this cell, and once this code is executed, now you have to download this data through API. So this is the API for this particular data set. So this you can find here. So I told you, right? So you have to go to Google and search CIFAR10 dataset. Make sure you have an account in Kaggle, and also make sure you have verified your phone number. So then only you can download this data through this API. So that's a mandatory thing. Now come to this data and scroll below. You will find this option for API. So this is the API for this particular dataset. You can copy this from here. Okay. So once you have copied this, come back to your collab, paste this, but include exclamatory mark before this, and run this. So this will download this 715 MB dataset file. Okay, so once this is done, run this ls. So this ls is a Linux command that we have to print the files or the folders that you have in the current directory. So this is the file that is downloaded, which is CIFAR10.zip. So this is a compressed file, right? Now we have to extract this file, and for extracting we will use a library called a zip file. So from zip file I'm importing this particular function called a zip file, and I'm giving the path of this dataset. So you can just go to these files, and from this you can copy the path. So this will basically give you this particular path, and again the code is simple, pretty much what I have given here. So I'm reading this file as zip, and I'm extracting this zip file. So extract all, and once this is done, I'm printing the dataset is extracted. That is all. And again I'm giving this ls to see whether this has extracted the files. Now I have this zip file, which is my data set that I have downloaded, and then I have this test.7z, which is my test images, so we won't be needing this for our work as of now. And then I have the train labels.csv, which has all the labels along with the IDs, so we will come back to this later. And then I have this kaggle.json sample submission, so this is basically how we have to submit the results to this kaggle competition. So this is also not necessary for us right now. This is the important file for us, train.7z. So this is another compressed file which basically contains all your training data images. Now, as this is a 7z file, you cannot extract it using this zip file. So for this, I'm installing a different library called as py7zr. So pip install 7zr, make sure you're including this exclamatory mark, so this will download and install this library. So once this library is installed, I'm importing this py7zr, and I'm creating a variable called as archive, and using this 7zip file, I'm mentioning the path of this compressed file. Mode r is nothing but I'm reading this file, archive.extract all and archive.load. So this will extract all the files. So this will basically give you another folder which is nothing but train. So you can also run your ls again to print whether it has like extracted that particular folder, which is this train, right? So this has been extracted. Now if you want to extract this to a specific folder, in that case what you have to do is, so within this parenthesis you will mention a path. So I'll just show you. So I'll make a comment here. So if you, let's say you want to download this to a specific path, so in this extract all, I have to mention a parameter called as path, and let's say let's create a folder. So I'll create a new folder and I'll name this as training data. So training data, and from here I can copy the path. Like you can do this in your local machine as well. So once I copy this, I can like mention this as training data. So make sure you're doing this after creating this training data folder. So this is a empty folder, so all these data will be extracted to this training data. So this is how you can extract this to a specific location, but in this case I'm just extracting it to the default directory that we have. So these are some of the basic things on how you can get access to this data set. So now let's get into the actual part of processing this data, and how to build our neural network. So as I've told you, first we will build a very basic neural network, and later we will import a pre-trained model which is ResNet 50, and I'll show you how you can train this ResNet 50 on top of your custom dataset and build this use case of CIFAR in object recognition. Okay, so the first step that we have here is importing the libraries. So I'll create a text here and I'll mention this as importing the dependencies. Okay, so first I'll import the library OS. So this is basically to run through the different files that we have here, and I'll also import numpy as np, and I want to import pandas for reading this train labels.csv. And next is, let's import some image processing libraries such as pillow. From pil I'm importing image, so I should be caps, and then I'll also import matplotlib image. So import matplotlib.pyplot as plt, and then let's import the module image, matplotlib.image as mpimg, and then let's also include train test split. So from sklearn dot model selection, import train test split. Okay, so the next step is going through this training data folder and checking like how many files are there in this particular folder. So I'll create a variable as file names. So this file name is equal to OS. So we have imported this OS, and from this I'm importing this list dir, which stands for list directory. So this will list all the files or the folders that is present in a particular directory, and the directory that I want to check is this train. So I'll go here, copy the path of this train folder and paste it here. Okay, so make sure to put this in quotes, and this will basically give you a list. So if you want, you can also check the type of this file name. So this will tell that this file name is a list because we're creating a list using this function, right? And now you can check the length of this file names. So let's see how many files like images are there. So totally there are 50,000 images. So basically this training data contains 50,000 images with labels that are stored in this train labels.csv, and this test data contains 10,000 images for your evaluation. But for this we won't be having the label, so that is with the people who are like hosting this competition, so we are not like worried about this. So we are going to take this training data and we also have the label. So from this we will split this training data into training data and test data, and then we will do our evaluation for ourselves. So this is the step. So we have 50,000 images for 10 different classes. Okay, and I'll also show you, as I told you, this basically list all the files in this directory. I'll show you some sample of the images that we have. So I'll print file names 0 is to 5. So this will print the first 5 elements in this list, and I'll also print file names of -5 of 0. So this will print the last 5 files in this list. Okay, so you can see, so this is the first file that we have, 7796. And these are the first 5 files, and these are the next the last 5 files. Okay, and the next step is to take this train labels.csv and process it such that we could have this labels in a list or a array that is like more suitable for our training. So that will be the next step. So I'll just add a text here as labels processing. Okay, now let's we know that this labels is in the form of a CSV, so let's load this CSV into a pandas data frame. So that's why we have imported the pandas library, and I'll name this as labels df. So labels df is equal to pd.read csv, and within this we have to mention the path. So I'll go here and copy the path of this train labels.csv. So copy the path and paste it here. So now first let's check the number of basically the shape of this data frame, which should tell us 50,000 rows. So let's see. Yeah, as we can see, we have 50,000 rows, which corresponds to the 50,000 training images that we have, and it have 2 columns. So these 2 columns are nothing but your ID and label. So I'll go here and give this labels df dot it. So this will, we know that this will print the first 5 rows in this data frame. So we have 2 columns. So first is your ID. So this is the index. So this is the default one, and then we have this ID and the corresponding label, right? And this ID is nothing but these are the name of your files. So 7796 is nothing but the ID of this particular image, and like in the corresponding value here, like say for example in the 7796 we will have like the corresponding label for this, right? So if you want to see this, I'll just show you. So labels df of labels df ID. So I'm going to mention this particular number, which is 7796.png, right? So I'll 7796. Okay, so let's run this. So this will show this particular row 7796 ID, and it says that this is a frog, right? So similarly these are the IDs, and these IDs are mentioned here in order, and the corresponding labels are given here. But the problem here is the images are not in order, right? In this particular folder we can see that it starts from this these ID numbers, and we could see that this is not in order. So that's the next thing that we have to solve. But for now we can see that this is the data frame that we have, and the other main thing that we have to see is whether the IDs are in order in this data frame. So that's important. So let's check this. So here I'll give this labels underscore df dot it, and I'll put 10 here. So this will basically give you the first 10 rows in this data frame, right? So we can see the ID is in order. Let's also check this for the last 10 rows. So that you can do using the df.tail command. So let's run this. So it ends in 50,000. So we can clearly say that all the IDs are in order. So now what we can do is take this ID column as list and pass it to a for loop and read the images in this particular order. So what I'll do is I'll take this ID column in a list, so and I'll iterate my for loop through this list. So first value is 1, and then I'll add this .png to this, and from this folder, this particular folder, which is content.train, I'll read the file that has the name of 1.png and convert it to a numpy array, and then I will read this 2.png and convert it to a numpy array. So this is basically reading the images in order. So that's the idea of this. And the before going to that part of reading the images and all these things, we can't deal with this particular type of labels which is in the form of a string. So I want to convert this to numbers. Say for example, if it is a deer, I want to convert it to 0. If it is a bird, I want to convert it to 1. So I'm just like numerically encoding these values. So there are like two ways to do this. I mean basically three ways to do this. So first step is to manually convert this strings to some numerical values, or you can also use your label encoder. But in this case I'm not going to prefer label encoder because we may not be sure of how the labels are converted. So we may not know how deer is converted, like whether it is converted to 0 or 1. So that we may not be knowing directly. So I'm going to manually convert this. And the other way, the third way, would be the more efficient way of instead of numerically encoding them, will be one not encoding them. But for now let's not move to one not encoding. So if you want, you can definitely try it, but now I'm just going to encode this with numbers, but I'm going to do this manually. Okay, so let's see. And before just doing that, I just want to make sure that there are only 10 labels and there are no 11 labels as mentioned in this data set. So, and also I want to check how many images are there like in this 10 classes, like how many deer images are there, how many bird images are there. So that I want to do. So just pause this video and think for some time, how you can do this. So I hope you would have some idea. So here what I'm going to do is use a data frame function called as value counts. So we have used this value counts multiple times to check the distribution of the classes that we have. So in this case I'm going to use the same thing. So labels df, and within square bracket I'm going to mention the column name, which is my label. So this column, and after this I'm going to say dot value counts parenthesis. Let's see how the distribution is like. As we can see, there are 10 classes, and for each class we have 5,000 images. So the distribution is even. So this is a great thing, because if the distribution is not even, then our model cannot make predictions correctly. So that's the problem. So in this case what we are going to do is take this frog, convert it to 0, take truck, convert it to 1, and so on. So let's take a very simple way of doing this. So I'll complete this code and explain you what I'm doing here. So I'll create a dictionary and I'll name this as labels dictionary, and I'm using this curly brackets. And first uh, if it is an airplane, I can convert it to, so I'll just use the alphabetical order. So first is I have this airplane, right? So airplane should be 0, and let's convert this automobile. So I'll copy from here. So automobile, let's encode this to 1, and then we have bird. So let's convert this bird to 2, and the next label will be your cat. So cat should be encoded to 3, and the next class is deer, and let's encode this deer to 4, and next will be your dog. So dog should be encoded as 5, and then we have frog. You can take any order. In this case I'm just taking the alphabetical order. Again, it's up to you. So frog I'm taking 6, and horse should be 7, ship should be 8, and finally we have truck. So let's have this truck as 9. Okay, so these are the 10 different classes that we have. So airplanes, I'll just count. So this is 1 2 3 4 5 6 7 8 and 10. Okay, 0 1 2 3 4 5 6 7 8 and 9. Okay, so we have 10 elements here. Now we know that dictionary is a key value pair, and the label names are my key and value are basically how I'm going to encode it. So I want to convert airplanes to 0, automobiles to 1, and so on, right? And now I'm going to create a list, and if it is a frog, I will encode it to 6. If it is a truck, I'll basically encode it to 9. So I'm just going to do this using a for loop and with a list. So I'll create a list called as labels. So this labels is equal to labels dictionary of I. This is an interesting way of doing this. So for I in labels df, label. Okay, So let's try to understand what we are doing here. Okay, so I have this for loop. So first let's look at this for loop. So we have this for loop of for I in labels df of labels. So when I say for I in labels of df, so let's print this alone. Let's see what this is giving. So labels df is my basically my data frame, and this is the column that I'm mentioning. So this will give all these values: frog, truck, deer, all these in order. So which order? It's the basically the order of the id, right? And I'm iterating this through this particular column. So when I say for I in labels of df, so when this for loop runs for the first time, it will, this I will take the value frog, right? And this frog, this basically, this is I is frog, right? So this frog will go here, right? So when I say labels dictionary of frog, so this will look into this particular dictionary and see like what is the value for frog. So it is 6, right? So the next time this for loop runs, it will take, I will take the value of truck, and this truck will be passed here, and it will go through this dictionary of what should be the value of truck. So it should be 9. Right? So at each step it will append these numerical labels to this list called as labels, right? So basically we are initiating a empty list, going through this column, and for a particular label we are converting it to the corresponding numbers that is given in this dictionary. So we are doing all these 3 steps in this single line of code. So this is basically how you can create a list with a for loop. Okay, so I'll run this, and let's then check how this encoding is done. Okay, so we have the first 5 basically first 5 labels and the last 5 labels. Let's see whether this labels is encoded correctly. So print labels 0 is to 5, and let's print the last 5 labels, which is 5 column. Okay, so let's see. So frog should be labeled as 6, so it has labeled correctly. And then we have 2 trucks, and trucks should be labeled as 9, so we have 9. And then deer 4, yeah, so automobile is 1, so it has labeled correctly. So the last should be automobile 1, so we have this 1. This is also automobile 1, truck 9. So this labeling has been done correctly. And the main thing is, the labels are in the order, like they are in the order of the id, because we know the id starts from this 1 2 3 all the way up to 10. Here it starts with 0 because this is not id, this is the index. So this is nothing but this particular index, so we don't have to look into this. So the main idea, the main thing that we have to understand here is, so it contains 50,000 labels, but the labels are in order of id number from 1 all the way up to 50,000. Now in the same order of 1 to 50,000, we have to read the images that are present in this train folder, right? So that will be the next step. Like if you want, you can open this train folder. Basically it will take some time because it contains around 50,000 images, so you can double click it, so it will display the image. So I'm not going to do this because these images are like really small. So you can see that these are 32 into 32 pixel images, so these images will be really small. So if you want, I'll just show you once like how you can read an image. So for this we can use this cv2 library, which is opencv. So I'll just create a uh, comment as displaying sample image. So here I'll import cv2, and here I'll read this image as img is equal to cv2 dot imread, and within this I have to pass in the path, right? So the path will be train data folder. So let's copy the path. And after this we know that these are the files in this path, right? So we have 7796, right? So I'll copy this 7796.png. So these are the files in this folder. So I'm not going to open this from here, I'm just copying this from here, right? So put a column, right? And now we want to display this. For displaying in opencv, basically the cv2, we have a function called as cv2.imshow, but that imshow won't work in Google Colab, because basically that imshow will create a window, and in this Colab it's not suitable to create a window. So they have replaced this with their own function, which is from google.colab.patches import cv2 imshow. Okay, So basically what happens here is when I read this through the CV to IMRIT, this will convert this image to a numpy array, and the CV to IMShow will convert this numpy array and it will display this in the form of an image. So that's the main idea. So I'll copy the CV to IMShow, and within this I have to pass the variable image, which is nothing but this image that has been read through CV2. So let's run this. Right, so I think this is a frog. So this is the reason I didn't want to print this, as this is like really small, because we know that the shape is 32 comma 32, right? So you can also try different images, but I'm not sure whether the image will be clear. So we can also cross check this. We have checked this, right? So yeah, so 7796 is frog. It's actually looking like a frog. Now I'll just copy a different image. Again, I'm not sure whether it will display this properly because of the size. So I'll copy this 45888, and let's see if we could see what this image is. Yeah, this seems like a dog. I think so. So we can also, do something like this. So I'll just like confirm this. Yeah. So with this, we just have to replace the ID. So the ID will be 45888. I'll copy this and paste it here. So we are just extracting this label from the data frame, right? Yeah, it is a dog, right? So similarly, you can just read this image and display it if you want, right? So the next step would be to read these images in order, because we know that the images are not in order in the train folder. So that is the next step. Now what we are going to do is create a list that has values from 1 to 50,000. There are two ways to do this. One is you can basically create a for loop and add values from 1 to 50,000, or rather what you can do is take the values directly from this labels df. So I'll print this labels df once for you. So labels df dot it. So I'll run this. So we have all these things, right? Now I'm going to take this id column alone in a separate list. Okay, so I'll create a variable as id list, and this id list is equal to list of labels df, and in this square quotes I'm going to mention id, right? So I'll show you how this works. So I'll run this, and now I'm going to print the first 5 values and the last 5 values as we are doing before. So 0 to 5, and the next one should be -5 of 0. I mean, you can just say -5, right? So we have the values from 1 2 3 4 5 all the way up to 49,996, all the way up to basically 50,000. Now I'm going to pass this through a for loop, add .png to all these numbers, and then read the image. So that's what we are going to do, and for this, like, that would be the next step. So let's do this. So this process, I'll put this as image processing. Okay, so here let's say convert images to numpy array. And I mean, we don't want to resize the images, so we are just going to take it from 32 comma 32. Okay, so if you want to resize, you can resize in this particular step itself. So if you have seen my dog versus cat video, I mean, this is it's basically the same step of reading a folder that contains images, resizing them, and storing them as numpy arrays. But in this case, we don't want to resize. Let's have this in 32 comma 32. Okay, and here I'm going to give this as train data folder. So I hope you know what's the training data folder. So it's nothing but this one, not this is just the sample folder that we have created to show you like how the 7z works. So let it be there. So this is the folder, actual folder. So I'll copy this path and I'll paste it here. Make sure to include a forward slash here. So this is very important, because to this path, so this is like the default path. To this path, I'm just going to like put 1.png to this. Like if you don't include this, so what you will get is you will get like 1.png, right? So yeah, so 1.png. I don't want this. I want this to be slash and 1.png. So make sure that after train you are putting a forward slash. And next I'll create a list as data. So now what I'm going to do is take 50,000 images, convert these 50,000 images into 50,000 numpy arrays, and I will enclose all these 50,000 numpy arrays in a list, and this list is nothing but the data, right? And now I'm going to say for id in id list, image is equal to image dot open train folder path plus string of id uh, plus dot png, right? I think it's better if I show you how this entire thing work. Okay, so let's print this. Okay, first of all, let's try to print this alone for maybe 5 images. So I'll call this as image path. So this is just to show you how this entire concatenation works. Okay, so training data folder string. Okay, now let's print this image path and let's break this. um, if id is equal to 5, I just want to break this. Okay, sorry, right? So this is what we would get. So basically we are taking this content slash string, and then the next step is we are taking this id. So each time this for loop runs, so this id will take a new value. So nothing but the values in this id list. So first time it runs this id takes this value 1, right? So once this id takes the value of 1, so we convert this 1 to a string, because then only we can add this dot png, right? So I'm converting this 1 to a string, and then I'm adding this dot png, which is nothing but this part, and later I'm adding this dot png to this train data folder, which is this, right? So at each step you would get this particular path. So once I have this path, I will read the images, convert it to numpy array, and store this in data is equal to this particular list. So that's what we are going to do. So for now I'll remove this. So I hope you are clear with what we are doing here. So for id in id list, image is equal to image.open. So this image is nothing but the one that we have imported from pillow library. So I'll just show you quickly. Yeah, so you can see, so from pill we are importing image. So again, this is a very useful library for processing your images. So image is equal to image.open your train data folder, and then as I've told you, we have to convert this string, this id into a string, because then only we can add this dot png to it. So dot png, so again, so all the images are in the form of dot png. If there are like jpg images, that this won't work. You have to work something in that so that you properly add jpg or png to this. But for now we don't have to worry about this, because all the images are of dot png extension. Okay, so image.open training data folder, converting the string to id, this string to id, and then adding .png. So this image.open will read image using this pillow, but it won't convert it to a numpy array. So it will be a different object called as pillow object or something. And now I want to convert this image to a numpy array. So I say np.array image, right? So this image is nothing but this image, right? I'm not changing the variable name. So first we are reading this image, converting to a numpy array, and storing it to the same variable name, and this is the numpy array that I need. And now I'm going to append this to this data list. So data dot append image. Okay, so let's try to understand what's happening here. So this won't change, this training data folder string won't change, and then we have a empty list. So let's say that this for loop runs for the first time. So when I say for id in list, that means id is equal to 1. Now image is equal to image.open, so this path plus 1.png, so this image will be read and stored in this image, which is a pillow object, and then we are converting this pillow object to a numpy array, and we are appending to this data. So once this for loop runs for the first time, this data list contains one element, which is numpy array of the first image. When I say first image, it's the numpy array of 1.png. Next time it runs, it converts the image of 2.png, and it stores in this list, and this process goes on. So I'll run this. This may take few seconds depending upon the size of your data. So if you want to resize this image just before converting this to numpy array, we can like resize this using pillow. There are like different functions for this, so I mean you can look those things, right? I'll just show you the type of this data. So this should say this is a list. So we have this list, and I'll also check the length of this list to make sure all the images have loaded correctly. 50,000. So I have all these 50,000 images. Now we have to check what is the type of the first element in this list, right? So I'll say type of data of 0. So when I say data of 0, it's the first element in this list called as data, right? So I'm going to check this data. So to make sure that it is in the form of a numpy array. As we can see, it is in the form of numpy.nd array, which is n dimensional array. Now I'm going to check what is the shape of this numpy array. So I'll say data of 0 dot shape 32 comma 32 comma 3. So just take a moment to just think what is this shape. So why we have this 32 and 32 and why we have this 3. So this is very important. Okay, so I have explained this in my image processing video. So if you want, I'll give a link in this video description. So I have explained you what are all the different types of images, how this image data is converted to this array, and so on. So it's like, it's best if you watch that video if you haven't watched it already. So this 32 is nothing but your height of the image and the width of your image, and this 3 basically represents your color channel. So there are two types of images. One is grayscale image and the other type is a colored image, which we call it as RGB image. So RGB stands for red, green and blue, because all the colors can be made from these three colors. So these three are the base colors, right? So when it is a grayscale image, or basically a black and white image, you won't have any values here. So you will have the shape as 32 comma 32. So basically, if this data set contained the images in the form of black and white, the shape in this case we would have got it as 32 comma 32. That doesn't mean there are no channel. It means that there is only one channel, that is my white and black channel. And when it is a grayscale image, we get this as 3, which is my red, green and blue. So this is really important. We know that this is a colored image, so we get this shape as 3, right? So this is basically, each image can be represented as a 32 comma 32 matrix, basically 332 into 30, 32 into 32 matrix, right? So first matrix corresponds to the red color intensity, second matrix corresponds to green color intensity, and the third matrix corresponds to blue color intensity. So this is the meaning of this 3. So now let's just print this data of 0, right? So it will give you this array, and these are the values. Now if you say this, all the values ranges between 0 to 255. Again, I have explained this in that image processing, so you have to watch that. So basically 0 means it is as I've told you, there are like 3 matrix, right? So if for a first pixel, so if in this first value all the values are 0 in the 3 matrix, if the first value is 0 in the R matrix, G matrix and the blue matrix, that means the color of the pixel is black. If the value is 255 in all the first value, that means the color is white. So similarly, you have all those color combinations and so on. So the main thing that you have to understand here is, when we convert this image to a numpy array, all the values range between 0 and 255. So that's the key thing. Okay. And yeah, so basically we have what we need. So we have 50,000 images. All of these images have been converted to numpy array, and this is the shape. So all these images will be of this shape. And there is other thing, if in this case, they have mentioned that all the images will be of the shape 32 comma 32. There are cases where the images will be of different shape. In that case, you cannot pass that directly to your neural network. You have to make sure that all the images are of same shape, right? It can be any shape, but you have to make sure all the images are of same shape. So that's really important. And so in the next step, what we can do is convert this. We know that this is in the form of a list. This data is a list, and our labels is also in the form of list, this label. So these two are the things that we need to train our neural network. Let's convert this lists to numpy arrays, right? I'm going to rename this to x and y. So let's put a comment here as convert numpy, basically images and labels to numpy arrays. Now it is in the form of list. Okay, let me put this as images list and labels list to numpy arrays. So this is a very simple step. So I'm going to say x is equal to np dot array. So x should be my images, so I'll say data, and we just have to do the same thing, but in this case we have to rename this to y, and np dot array labels. I'm just changing the data type, so there is like nothing much going on here, but this is important. So now I'll check the type of x and y. So I'm not going to check for both, I'll just check it for x. So we know that it's a numpy array, and I'll also print the shape of this. Print x dot shape, and let's print y dot shape. So there is some interesting thing that we could see here. 50,000 comma 32 comma 32. So what this means is there are 50,000 numpy arrays or 50,000 images of shape 32 into 32 with 3 color channels. So that's the meaning of this. So this represents the number of data points or the number of images. So this is your height and width, or it can be your width and height. I'm not exactly sure of that particular order, but I think it's height and width. And then you have the color channel. If it is grayscale, you wouldn't be seeing any values here. It means that it is understood that it is 1, it's not 0. So this is important, just keep this in mind. So we have, in this case, we have 50,000, 32, 32 and 3, and this 50,000 is nothing but your y shape. So it basically contains your 50,000 labels. Okay, in the next step we have to perform train test split. Like, I mean, we have been doing this for ages, so we know what is meant by train test split. So we take this 50,000 data, take some data as training data and some data as test data. So train test split, making this bold, and I think I've already imported it. Okay, so x train, x test, y train, and y test. So this order shouldn't change at all. So we have x train, x test, and y train and y test. So this is equal to train test split. So if you remember, we have imported this train test split from sklearn.model selection. Again, this is a very basic thing. So sklearn.model selection, we are importing this train test split, and here we have to pass this x and y. So let's say x comma y, and test size of 0.2. So I'll tell you what this test size means. Random state is equal to 2. Okay, so I always use random state is equal to 2. You can use any number you want. So we are passing this x and y, which are my images and labels. Test size of 0.2 means out of this 50,000, I want 20% of images to be my test data. So you can calculate like how much will be your 20%. So 10% will be your 5,000 and 20% will be your 10,000, I think so. So 20% will be your test data, and the remaining will be your training data. Now random state is again an interesting parameter, but not that much important. So when you run this train test split, it will split the data in a particular order. Like some random images will be your training data, random 40,000 images will be your training data, and the random 10,000 images will be your test data. And if you run it the next time, it won't contain the same images. So there is some kind of a shuffle that's happening. If you want to retain the same order, in that case you will use random state some number. Okay, and the other reason is just to reproduce your code. Let's say that I'm splitting my data in a specific order, and you want to split your data in the same order, then in that case we both have to mention the same number, right? So it's basically for that purpose. So I'll run this. Now my data will be split to training data and test data. Now I'll check the shape. I'll check the shape of x, which is my original data set, and then I'll check the shape of x train, which is my training data images, and I'll also check my test data images. Okay, so this should, yeah, so 50,000. So this won't change the dimensions of the image. So we have to look into the first number. So original data contained 50,000 images, and 80% of this 40,000 will be your training data images, and 10,000 will be your test data images. Okay, and the next is a very important step. Now we are going to scale the data. So this process is, again, it's called as normalization. Basically we are going to scale down the data. So I've mentioned you that the values ranges between 0 to 255, right? Now I'm going to convert these arrays such that I have all the values from 0 to 1. So basically what happens here is, if the value is 0, in that case basically your value will be 0, right? And if your value is 255, in that case your value will be 1, right? So all the zeros will be the same zeros, and 255 will be converted to 1. So we are scaling to this range of 0 and 1. So all the numbers between the 0 and 255 will take the numbers between 0 and 1. Like, we are just scaling down the pixel value. There is like nothing much complicated going on here. So this is done, and in most cases it will increase the performance of a neural network. So this scaling is a very important step that you have to follow. So I'll show you how you can do the scaling. It is a very simple step. So I'll show this. So let's create a comment here as scaling the data, and I'm going to scale this and store this in a different array. So scaling the data, so we have to, I mean, we don't have to scale the labels because it has the values from 0, sorry, yeah, 0 to 9, right? Yeah, I think so. So let me quickly check. So we have 0 to 9, so we are not going to affect this. The only different thing that you can do here is, instead of numerically encoding, you can apply one not encoding, which will be a more effective way. But in this case, let's go with the normal numerical encoding as we have discussed earlier. Now let's scale this. So I'm creating an array called as xtrain scaled is equal to xtrain divided by 255. Okay, similarly we have to scale our test data. So this will be your x test scaled, so this should be converted to x test, right? So this is the step. Now it's a very interesting thing. You can't do this in a list, but in the case of numpy array, when you divide this numpy array by 255, all these values will be divided by 255, right? So when I do this, if it is 0, it's nothing but 0 divided by 255, so you will get 0. If the value is 255, 255 by 255 is 1. So as I've told you, all the values in between them will lie between 0 and 1, right? So that's the basic idea. So we are basically scaling down it to 0 and 1. So I hope you are clear with this. Again, there is not much complicated in this. So I'll run this. Now I'll print this xtrain scaled, the first image of this for xtrain scaled, right? So you can see all the values are between 0 and 1, like you can go through this. But if you print your xtrain, it won't have those things. Xtrain of 0, right? So we are converting this numpy array to this numpy array, right, by just basically dividing it by 255. So when I do this, so all these values, yeah, so all these values will be divided by 255, and this will happen on all the 50,000 numpy arrays. So that's what happening here. And yeah, I think that is all. Now we can probably move on to building our neural network. So for this we need libraries like TensorFlow and Keras. So let's work on that. I'll make sure I'm explaining the things simply, so that even if you don't know much about the deep concepts of neural network, you will get to know how to implement this. So that's the main idea for doing these use cases. So I'll create a text as building the neural network. Sorry. So building the neural network. So I'm going to import TensorFlow as TF. So I mean, again, TensorFlow is already installed in Colab, but if you're working on your local machine, if you're working on Jupyter Notebook or Spider or VS Code, you have to install these libraries. And from TensorFlow, import Keras. Now let's just quickly discuss about this TensorFlow and Keras. So TensorFlow is like the base library. So TensorFlow is developed by Google, and there is another famous library called as PyTorch, which is developed by Facebook. So these libraries are used for building our neural networks, and Keras just makes things easier. It helps us to use these libraries in a easier way. So Keras is just like a wrapper. It uses TensorFlow or PyTorch in its backend, but again, we are building the neural networks on TensorFlow or in PyTorch. But Keras just makes things easier. So that's the thing. So if someone asks you what is meant by Keras, you can just say it is a wrapper of the libraries like TensorFlow and PyTorch, which are basically your deep learning libraries in Python. There is another library developed by Microsoft, which is called as CNTK, which stands for Cognitive Toolkit. Okay, so this is the purpose of this library TensorFlow and Keras. And now let's build our simple neural network. And like I'll tell you, the performance will be really low. Later we will be using Resonant 50, which will boost the performance of the model. So that's what we'll be doing here. Okay. So I'll first create a variable and I'll call this as number of classes. So here we just have to mention how many classes are there in our data set, which is 10. Right? And now we are going to set up the layers of our neural network. So I'll mention this as setting up the layers of neural network. So I mean, we are not going to add convolutional layers, as this is a very basic one, but this ResNet 50 has those convolutional layers in them. So first let's just build a basic network. So if you have a neural network, there are three main layers to it. First is your input layer, and then you have multiple hidden layers. So I mean, you can have any number of hidden layers you want. And finally you have your output layer, which predicts the class that image belongs to. Okay, so create this variable as model, and I'll say model is equal to keras.sequential. So this process won't change for the neural networks that you build. So keras.sequential, and within this parenthesis I'm going to open a list. And within this we can mention the different layers that we want. So let's say 1 sec. Yeah, so keras dot layers dot flatten. So I'll explain you what's the purpose of this flatten in a moment. So input shape is equal to 32 comma 32 comma 3. Put a comma here, so that's again important. So keras dot layers dot dense. I'm going to take, okay, I'll take 64 neurons, and I'll put this activation as relu, which is rectified linear units. And then I'll add another, basically the output layer, layers dot dense. Here we should put the value as 10, so this value should not change. In this case you can have the number of neurons as 32, 120, 256 or any number, but here the value should be 10 because it's nothing but the number of classes that you have. So again, it's a good practice to put this variable, so in this case to just, so that someone, reading your code understand like what you have done. So instead of putting 10, I prefer, I also suggest you to put this 10 in a variable and putting that variable here so that it is clear. And activation is equal to softmax. So you have different activation functions. So you have relu, as I've told you, which is rectified linear units. You have sigmoid, softmax, and so on. In the output layer, it's not like the rule, but we generally use sigmoid as the activation layer when it is a binary classification problem, or in other words, you are predicting only two classes. If it is a multi-class classification problem where you have more than two classes, where in this case we have 10 classes, we can preferably use softmax. Right, so we have the input layer, which is this flatten, and we have one hidden layer with 64 neurons, and then we have the dense output layer, like the final layer with 10 neurons. So each 10 in this 10 neurons, each neuron correspond to the 10 classes that we have, right? So if the image is a frog, then there is a neuron that is assigned to this frog, so that neuron will give you the highest probability. So we just like look into this probability and find like which class the neural network is saying that this image belong to. Say, like, let's say we are training the model and we are passing a new image to predict which class it belongs to. So we look into this 10 final neurons output, which is basically a probability value, and see like which neuron gives you the highest probability. If the you know frog neuron, which is the number 6, gives you highest probability, we say that that image is a frog, and this same for the other images, right? Now let's discuss this flatten, and the important parameter that we have to mention is this input shape. Here you just have to mention the shape of your image. If it is a black and white image, we just say 32 comma 32, right? So that 32 is nothing but the shape of the image, as we have seen in this case. Just a moment. As we can see, so if it is a 224 comma 224 image, in that case we change this here. So this is the only thing that changes. Flatten. So what happens in this flatten is, we know that this is a 3 matrix with shape of 32 into 32, and we won't be passing this as a matrix but in the form of a vector are nothing but like it just has a single dimension. So you can think about this as a single column of values. So this is what is done by this flatten. Again, this is a common step in the neural networks that we build. And then we have this hidden layer that has 64 neurons. Activation function, as I've told you, there are different activation functions we have, and this output layer. And another interesting thing about this hidden layers, so why I've used a 64 is, you can use any numbers. You can, use 65 or 70 or something, but generally people use values in the power of 2. Like the usual number of neurons that we would have will be 32, 64, 128, 256. It's not that you shouldn't use some other numbers, but like the reason we use these two powers of 2 is it's computationally efficient to maximize the usage of RAM CPU basically for that purpose. But again, it's not that you have to use this number. Basically your training will be efficient when you use these numbers. So if you have like multiple neurons, we start with a larger number like 256, and in the next layer we will be having 128, and then we'll be having 64, and then 32, so something like this. So in this case I'm just having one hidden layer and I'm having this as 64 neurons. Okay, so let's run the cell. My runtime is disconnected, so let me see. So this will be the step where we are building a neural network, and in the next step we have to compile it with some the optimizers, metrics and other things. So I'll show this to you now. Yeah, so the cells are executed. Okay, so let's run this. So this is just setting up the layer. Now we have to compile this. So compile the neural network. Okay, so I'll say model.compile. So here we have to pass three things. One is your optimizers, which updates your weights. So I'll say optimizer is my Adam optimizer, which is a most commonly used optimizer. And for loss I'm going to use sparse categorical cross entropy, basically your loss function. Again, so there is another important thing here. So the reason I'm using this sparse categorical cross entropy is I have like numerically encoded labels like 0, 1, 2, 3 and so on, right? So where is this? Yes, I have this like numerically encoded ones. If I have one not encoded labels, in this case I can use categorical cross entropy, right? So if you interchanges, it will give you an error. So that's the thing about this. And the next thing that we have to include is your metrics. So for compile we have this laws and metrics, right? Yeah, so metrics should be accuracy, as this is a classification problem. So I'll say metrics is equal to ACC. Okay, I think this, yeah, I think this is sufficient. And now let's train our neural network. So again, this is the usual steps that we have. So first we have to set up the layers and the input shape, all these things for our neural network, compile it with suitable optimizers, laws and metrics, and then we will fit our model. So this step is training the neural network. Okay, and again, so this process will take a long time if you don't change your runtime to GPU. So that's other thing. So that's why we are selecting GPU at the start itself. So model dot fit x train scale. So I hope you remember that we have scaled our data. So scaled data will many times give you better performance. So corresponding labels will be my y train, and I'll give this validation split. Should I give this validation? Okay, so I'll give this validation split as well. Split is equal to, let's take 10% of data, and epochs, let's have 10 epochs. So let's try to understand this. So I'm passing my images and the corresponding label. So the model will try to find the relationship between the labels, which is my y train, and the images. And validation split. So validation split is just like your test data, right? So when I say epochs is equal to 10, that means like my model will go through the data 10 times. So when I say epoch, it means one forward propagation and backward propagation. That means like your data goes through this neural network in forward, and it will also come back backward, and in this process your weights will get updated, right? And in each epoch 10% of data will be reserved as your test data, and at each epoch we will get our training accuracy and your validation accuracy. Okay, and later once this training is done, we can also evaluate our model with the test data that we have splitted using this train test bit. Okay, so let's run this. So this may take some time. Okay, so we are getting some error. So unknown loss function, sparse categorical cross entropy. So here I shouldn't mention a underscore. So that's the reason we are getting this error. So I'll run this. Now let's see. Yeah, it's working now. So this is the first epoch, and this is the steps that we have. So it seems this is not taking much time. You can see the accuracy value, loss function value. So loss function is nothing but the distance or the difference between your true value and your predicted value. So our goal is to minimize this loss function. So if your loss function minimizes, automatically your accuracy will increase. Okay, so we are starting from 29 percentage accuracy, and we can see it's going up to 40 percentage accuracy. Again, this is a very simple model. We don't even have convolutional layers to it. So convolutional neural network, which we call as CNN, works really well for image recognition problems. And I mean, in not all cases we would get a good model. Like, I mean, like, when I say good model, I mean, like, for most cases we can't build a accurate model, because like it's too hard for these models to capture this data. For this, we use a technique called as transfer learning. Okay, because like in this case, if you see, we starting from this 29%, which is basically 30%, and in the third or fourth epoch itself, it's closing to 40 percentage accuracy. But after 7 epochs, there is no significant change, right? It's still at 40 percentage, and the validation accuracy as well. So we use a technique called as transfer learning, where we take a pre-trained model which is already trained on a data set, and we use that model to train a similar data set. So we are not training it fresh, we are using the pre-trained model. We are training that on top of our own custom data set, as we have here the CIFAR 10 data set. And in those data sets would achieve better performance in a small number of epochs, and it's like always preferable. Like, that's what like we mostly use, because we can't build models from scratch all the time, because it takes a lot of resources and you need a lot of data which is not available all the time. So in this cases, we move to this transfer learning techniques, where we have this open source ResNet 50 and the other models. So there are like models like ResNet 50, Inception, and other things. So you can search those things to get a better idea. So in this case, let's see how we can train a pre-trained ResNet 50 model, and basically train it with the CIFAR 10, and get a better performance than this. So that's the idea of this particular video, as I've told you. Now let's go on to that important part of that video. So I'll create a text and I'll call this as ResNet 50. And again, you will have different versions of these models. So we have to import this model first. So I'll import certain things. So from TensorFlow.keras, import sequential models and layers. So I mean, these layers are nothing but we have used keras.layers. So in this case, I'm just importing this layers directly from this TensorFlow.keras, and then we'll copy this from TensorFlow.keras import. So this probably won't change. From this, I'm going to import dense. So we have also built some dense layer in the above network that we have built. I'll also import this dropouts. I'll explain you what's the purpose of this dropout. Again, this is a very important thing. Flatten, as we already add. And from here, I'm going to import my load model. Okay. Okay, so load models should be in TensorFlow.keras. Okay. So from TensorFlow.keras.layers, we have to import this dense and drop. So these are like the different layers that we have. And load model should be imported from this load model from models. And there is another thing called as batch normalization from TensorFlow.keras.layers. So I'll explain you, don't worry about all these things. So this may seem a bit complex, but these are pretty simple things. So I'll explain you while we are implementing this. So layers, let's import batch normalization. Yeah, batch normalization, load model, and from TensorFlow.keras.model, import model with a capital M. Now uh, let's import our ResNet model. So it's present in this from TensorFlow.keras.application. So there is another option, like from where you can import the pre-trained models, which is TensorFlow.app. For our dog versus cat classification, we have imported our mobile net model from TensorFlow app. You can also refer to it. So in this case, TensorFlow.keras.applications dot ResNet 50 import. So in this case, ResNet should be should be in lowercase, and here R and S should be, sorry, R and N should be in uppercase. ResNet 50, and finally let's import our optimizers from TensorFlow.keras dot. Again, you have different optimizers. You can also search what are all the different optimizers that we have. Okay, I think this should be enough. Let's see. Invalid syntax. Yeah, my bad. Okay. No model name TensorFlow.keras.model. Okay, so this should be models. Okay, so first from this TensorFlow.keras we are importing the sequential. Sequential is nothing but we are going to stack all these layers within the sequential. So that's the purpose of this. We do this all the time. So models, layers. From this layers we are importing dense layer, dropout and flatten layer. And we are also from this layers we are importing this batch normalization, which is again a key thing. I'll explain you why this is used. We have also have this load model again for loading those models and just some small purposes. And then again this we have model from the same module of models. And from this TensorFlow.keras.applications.ResNet50 we are importing ResNet. This is the actual model that we are going to use. And finally we have optimizers from this TensorFlow.keras. Okay, so we have executed this. Now let's load the ResNet model. Okay, so I'm going to call this as convolutional base. So as I've told you, convolutional neural network is just similar to any other neural network. It's just similar to what we have here, but it just like additional layer called as convolutional layer. Like multiple convolutional layers can be there. And again you have this like pooling layer and so on. So let's discuss this in detail when we come to learn about this convolutional layers in our deep learning course, but just have this idea as of now. So in a CNN there are like apart from the input hidden and the hidden layer, we also have this convolutional layer. So these layers can capture the information in the image better. Right, so you can also like build convolutional neurals from scratch, and in this case we are not going to use this. So we are going to use the convolutional layer of ResNet50. So that's the purpose. So I'll create a variable as convolutional base. So this convolutional base is nothing but our ResNet50. I'll call this ResNet50, which we have imported from here. And within this I have to mention some parameters. Weights is equal to ImageNet, and include top is equal to false, and input shape is equal to 256 comma 256 comma 3. Now let's try to understand what these parameters mean. So we are creating a variable called as convolutional base, to which we are going to load this ResNet50. Weights is equal to ImageNet. So this ImageNet is nothing but it is a image data. It's like a image database where several like these models are trained. So this ImageNet data basically contains millions of images. I think it contains around 14 million images. If we want to train those images, I mean, you can think about the resource that it needs, which we can't actually do with our machines. So again, that's one thing. So when I say weights is equal to ImageNet, we are, when a ResNet model or any neural network or any model is trained based on this particular data set, it will derive some weights. Now I want to import the weights that the model has derived by training this ImageNet data. So I'll repeat this again. So when this ResNet50 model is trained on this ImageNet data, it gets some weights, and then we are going to retain those weights. And with our custom data set, we will train with this data, update few weights. So this is the process. So when I say weights is equal to ImageNet, it's basically the weights that are derived while training with this particular data. And now we have the include top is equal to false. So before going through this, I suggest you to just search about ImageNet and see what are all the different classes that we have, the number of images that we have. So this ImageNet data, I think it contains about thousands of classes, 1,000 classes or more than 1,000 classes. I'm not exactly sure. So in that case, your output layer may contain like, let's say 1,000 neurons, because it has to distinguish 1,000 different classes, right? Like something like that. But in this case, we don't have 1,000 classes. We just have 10 classes, right? So all those frog, bird, automobile, and those things, right? So when I say include top is equal to false, it will import the ResNet50 model, but it will drop the final layer, which is my output layer. And we just add our own output layer to this, because we know that
we are not predicting 1,000 classes, we are just predicting for 10 classes. And other thing about transfer learning is you can't take some model and you can take and you can like train it with some data that is not related to it. Like ResNet 50, this ImageNet is, this data is similar to what we have here. So we have some basic objects and animals, right? Frog, dog, and automobiles, and all these things are. ImageNet also contains like those kind of images, so we can use this. Like if your model is trained on truck image and something like that, that can be used to predict car images. But you can't take a model that has been trained on truck and use it to predict dog or cat. So that won't work most of the times, right? So that's other thing. So there should be some similarity between the data that the original model has been trained on and the data that you're training. In this case, CIFAR 10 is a bit similar to the ImageNet data, so we are using this. And as I've told you, include top is equal to false means we are not including the output layer. So this is very important. So we will add our own custom output layer with 10 neurons as we have seen before. And input shape is equal to 256 comma 256 comma 3. And this is again a key thing for you to remember. So this is nothing but the shape in which ResNet 50 take the images, which is 256 width and 256 height, and 3, which is basically RGB images. Now our image, the CIFAR dataset that we have, we know that it is not of this shape. This is 32 comma 32, right? And I have also told you this multiple times before that uh, you can train a neural network with images, but all these images should be of the same shape. And while predicting also, you should pass the image with the same shape. Like you cannot train a neural network with 256 comma 256 images and predict an image with 200 into 200 shape. So you have to rescale this to 256 comma 256. So this is how it works. But unfortunately in this case, we only have 32 comma 32 images and we don't have 256. So I'll show you how you can resolve this, but for now just have this idea. So first parameter is your weights, which is nothing but the data sets we mentioned it, so that it retains the weights of those weights it derived while training on that data set. Include top false, which means like we are not including the output layer. And input shape, the shape in which image ResNet 50 expects the data to be, right? So and then I'll print this summary convolutional base dot summary. So it will just show you the different layers that this model has. So this will download this data. When you say this ResNet 50, as you can see, it's download the neural network first, and this is the architecture of ResNet 50. So I strongly suggest you just go to Google and search ResNet 50 architecture. It will show you what's the input layer that you have. So as I've told you, these are some of the convolutional layers that we have. This is the pooling layer, right? So all these things. So again, we have this batch normalization. I'll explain you what this does and so on. So this is the architecture. This can be too much to look into as of now, but just search for uh, ResNet 50 architecture and just have a look. Right, you don't have to understand all these things right away. I'll explain you a few key things. So this is the architecture, right? So this is the convolutional base, which doesn't have that output layer, right? Okay, now we are going to add our own layers to this. So let's work on that aspect. So we are going to add some layers to this base, to this convolutional base, right? So I'll add this, create this same name as model. So model is equal to, I think we can use sequential. Let's use this models dot sequential. Okay, so previously we have used this models dot sequential. Within this parenthesis we have created a list and added all these layers. There is another way of doing this. So you can use this add function. So first I'm creating this models dot sequential, and I'm going to say model dot add. So from this also we can add layers to our neural network. Right, so this model is nothing but this one. So we are loading the sequential to this variable called as model, and first I'm going to add a upscaling layer. So layers dot upsampling, sorry, so upsampling 2D. I'll explain you what's the purpose of this. Just a sec. 2 comma 2. I'll copy this. Here you don't have to mention comma. So there we have mentioned this comma because within that sequential we have created this list. But we are just using this add function. You don't have to mention this comma. So I'll copy this 3 times. And model dot add convolutional base. So I'll explain you all these things. Don't worry. Just give me a moment. So convolutional base model dot add as dot flatten. I think we have imported this flatten. We can use this directly or layers dot flatten. I mean, both the things are same. And model dot add as dot batch normalization. Okay, so make sure you mention this parenthesis here. So in flatten also we should have parenthesis. Okay, and then model dot add layers dot dense. I think so. I mean, you don't have to mention the layers. I just want to have a uniformity. That's why, because we have already imported this dense, dropout, flatten, all these things. So you don't have to say layers dot batch normalization or layers dot flatten. So you can just say flatten, so it will work. So layers dot dense. Let's take 128 neurons. And activation, we are going to use relu as we have used before. Activation is equal to relu. And now I'm going to add a dropout layer. So model dot add layers dot dropout 0.5, and I'm going to add another batch normalization. Yeah, okay, after dropout, and I'm just going to repeat these steps. I'm just going to change the number of neurons as 64. I'm sorry, 64, 128, 64, and finally we can add a dense layer, basically your output layer, which should have 10 neurons as I've told you before. So here I'm going to, instead of 64, I'm going to say num of class. We have already created this variable, but just to avoid confusion, I'll create this variable again. Okay, number of classes is equal to 10. So first we have the sequential upscaling 3 times, convolutional base, and we have flatten, batch normalization, rectified linear units, dropout, again batch normalization, the 64 neurons, 0.5 batch norm. Okay, now let's try to understand how we are setting up these layers. Okay, as I've told you, okay, so int object has no attribute lower, layers dot upscaling. Some issue that's happening. Int object data format is equal to value lower, int object has no attributes, layers dot model. So models dot sequential, model dot add layers dot upsampling. Okay, so I should put this in another parenthesis, so that's why. Okay, all right, yeah, this should probably work. Let's see. Okay, so let's run this. Yeah, it worked now. Okay, let's try to understand what's happening. So number of classes, we know, we just have to mention the total number of classes that we have in our data set. Models are sequential, so in the within the sequential we are going to stack up all the layers. Now let's try to understand about this upsampling 2D. As I have told you, ResNet 50 is probably trained on images that is of the shape 256, 256. In the previous case, if you have watched my dog versus cat classification, in that video, we have mentioned that we have to rescale the shape of the images to 224, 224, because in that case also we use transfer learning, but we use mobile net model. And the mobile net model is trained on images that are of the shape 224, 224, right? But in this case, we don't have that luxury to do that. We are not like, basically, I mean, we can do, but in this case, we are not rescaling the images while converting those to numpy arrays. But ResNet 50 needs the images in the shape 256, 256. Three color channel is not an issue because we also have colored images. The ResNet 50 also takes image as a colored image. Now, when I say model dot add layers dot upsampling 2D 2, 2, your height and width will be multiplied by 2 times. So it's basically like scaling up your image. Okay, so that is, it's like you're taking a 720p image and converting into 1080p image. So it's all about scaling. And 2, when I say 2 comma 2, 2 times of height and 2 times of width. And you can say I'm doing this 3 times, because when you multiply 32 by 2 one time, you will get 64. Again multiply this 64 by 2, you will get 128. Again multiply this 128 by 2, you will get 256. That's why we have this 3 layers. So before passing your images to your convolutional base, we have to make sure that we have upscaled our data to the shape of 256 comma 256. So the first thing is like scaling your data twice, which is it will become like 64 comma 64. Next time, once we do this step, your images will be of 128 comma 128, and after this process is done, your images will be of 256 comma 256. I mean the processed thing, not the base image. And then we are passing this to this convolutional base, which has all these layers as we have seen, right? And then we have this flatten. I've told you what's the purpose of this flatten. We just convert this matrix into a vector, so that all the values are in a form of a single column, right? So that's the main idea. So it's in the form of a single dimension. And then we have this batch normalization. So first, we have to understand what is meant by normalization. In machine learning also, while doing feature scaling, we have discussed about this. We have two things called as normalization and standardization. So normalization is to make sure that all the values are of same range. If you have 10 columns in your data set, we have to make sure all the values are in the same range, right? So that's called as normalization. And we have already scaled our data. We know that all the values will be between 0 to 255, right? Strictly speaking, if you have scaled your data before, you don't have to use this batch normalization. But even though you scaled your data, if you use batch normalization, your training process is going to be efficient, your performance is going to increase, like most of the time. So what happens here in batch normalization is, so let's say we have an input layer and you have 3 hidden layers and you have a final output layer. So some processing is happening in your first hidden layer. So as I've told you, you have 3 hidden layers, and there are, like, let's say in the first hidden layer you have 10 neurons, and some processing happens here in this first hidden layer, and this first hidden layer will output, or will give this processed input to the second hidden layer, right? Now this batch normalization makes sure that all these values are of, all the values are normalized. So all this, so initially the image values that we are passing are normalized, basically they are scaled, but these processed values may not be normalized. So this is why we have this batch normalization at the end of each layer. So first we have this flatten layer, we are applying this batch normalization, and then we have our another dense layer. So as I've told you, we use values like 256, 128, 64, and 32, the powers of 2, so that it's efficient in terms of memory and computation. So here we have 128 and activation relu. So okay, so final case I'm going to use softmax. As I've told you, for multi-class classification, most case we use softmax in the output layer. So let's come back to this. So we are adding this output layer with 128 neurons and activation of relu, and this dropout is a very important aspect. So neural networks are a very complex model and they have a tendency to overfit. So I hope at this point you know what is meant by overfitting. So overfitting is when your training data, your training accuracy is high, but your test accuracy is very low. So there is like a huge difference between them. So that's called as overfitting. So that happens when your model cannot generalize generalize the data, generalize the modeling technique basically. So please, if you are not sure about this overfitting, please go through it. It is a very important concept in both machine learning as well as deep learning. And this dropout, what happens is, if there are like 128 neurons, it will turn off few neurons. So when I said turn off few neurons, it will basically give the output as 0, right? So some set of neurons should be turned off, and that how many neurons or how much of neurons should be turned off is determined by this value. So you can refer to what is meant by the 0.5, what happens when I mention 0.3 and all those things. So dropout is to turn off few neurons so that our model doesn't overfit. So this dropout is generally done to reduce the risk of overfitting. You can also train this without this dropout layer, but again you have this risk of getting a overfitted neural network. And again we are performing this batch normalization so that the output from this network is normalized. And then we are having another layer of hidden layers with 64 neurons, adding dropout to it, batch normalization. Finally we have our output layer. number of classes is 10 and activation is equal to softmax, right? I hope everything is clear. So this is actually much simple. Okay, and similarly, previously we have compiled and fitted our model, right? So we have to do the same. So I'll say model.compile. Just a moment. Okay, so model.compile, we have to add three things: optimizer, loss, and your metrics. So optimizer is equal to optimizer. So we have imported this optimizers. If you remember, we have imported this from, yeah, tensorflow.keras optimizers. So I'm not going to use atom, I'm going to use a different optimizers called RMS prop. So I suggest you to check the different optimizers that you have and what they actually do. I mean, the concepts go much deeper. I don't want to go into these things as a, I mean, right away. So within this, I'll mention the learning rate as 2e power minus 5. So this basically learning rate determines how much your weights are going to change, right? So at each iteration, when your model learns from the data, it updates the weights, and learning rate determines how much change do we have to impart to that weight. So that's why we have this like learning rate. And I mean, if you remember gradient descent, it's similar to what's happening there as well. And the loss, again, it should be the sparse categorical cross entropy, because we didn't do one not encoding. If you did one not encoding, we use categorical cross entropy. So that's the difference. Sparse categorical cross entropy, yeah, so there shouldn't be a underscore there. So cross entropy. Next we have metrics. So metrics should be accuracy, as we have classification problem here. Okay, so let's run this. Yeah, model app compile. Now we have to fit our model, but before fitting, I'm going to fit it to a variable called as history. I'll explain you why I'm doing this after like this training is done. So model.fit xtrain scaled, comma, ytrain validation split. So I've already explained you what is meant by validation split. It's just like your test data, but the thing is it kind of like at each epoch it reserves some data as your test validation data, right? And validation split, I'm going to take 10 percentage of this, and epochs, I'll give 10 epochs. So this will take so much time to train. I think it will take around an hour. So let's see. So history is equal to model.fit xtrain scaled ytrain validation split of 0.1 and epochs of 10. Okay, so let's run this, and this will carry out the training process, right? Okay, so let it run. In the meantime, I'll just like complete one last thing of plotting our loss and accuracy change. I mean, this is again a standard thing that we do in any neural network training. I'll load this history to a variable called as h, just like an abbreviation. And I think I've already imported matplotlib, right? Yeah, so we need matplotlib here. And first we are going to plot the loss function value, like how your loss value changes in 10 epochs first, and then we discuss like how our accuracy changes in the 10 epoch. So I'm going to say plt dot plot h dot history, sorry, so yeah, h dot history, we have loss. So we will print both, plot both validation loss as well as your train loss. The label is equal to training loss, and now we have to do this for validation loss. Val loss is nothing but your validation loss. Okay, and plt dot legend and plt dot show. And similarly, we have to plot our accuracy change as well. So basically we'll get two plots. Plot the accuracy value. So h dot history of ACC, this should be training accuracy, this should be your validation accuracy. So your accuracy should increase and your loss should decrease. So that's the idea. So should this be validation accuracy? Okay, so let me quickly check this. So PL H is equal to history, loss, training loss, validation loss. Okay, history. So this is just the label for our plot. So this is not important, but this shouldn't change. These four things shouldn't change. Okay. Okay. So again, as I've told you, this training will take around an hour. So I'll pause this video and I'll continue this once this training is done. Okay. So this training process almost took an hour. So you can see how much time this has taken. So it says like 52 minutes, and I think it took like a bit more time. So this is how we have fitted the data to this neural network. So we have fitted this scaled training data along with the training labels, and we have given validation split as 0.1, which is 10 percentage of this training data, and epochs is equal to 10. As we can see, the model has achieved good performance at the fifth epoch itself. So this is another reason that we go with transfer learning, so that we could achieve good performance with a lesser number of epochs, whereas previously with the model that we have built, so this is the performance that we got. So in the first 5 epochs we were able to achieve only 38 percentage starting from 29, whereas in this case with the resonate 50 that we have trained, so we have started with 46, and we were able to increase the accuracy almost like 91%. And at the end of 10th epoch, so there were like almost 98% accurate with validation accuracy of almost 95, right? So you can change these things. So you can like I mean, you have to upscale the upsample this like 3 times. So similarly you can add a more dense layers to this, or you can try without batch normalization, all these things. So try different activation functions maybe. So you would get like different results. So similarly like a different optimizer. So Adam, I think like Adam kind of gave a lower performance in this case, so you can like try different optimizers as well. So this is the final result that we are getting, and this is the evaluation of the model on the test data set. So you can see, so we are passing this X test scaled along with the testing data labels, and the accuracy is almost again 94 percentage, similar to what we got in this validation. So the change is not that much. So I mean, the model is definitely not overfitting, so we get a very good performing model with high accuracy. And as we have discussed before, we are plotting this history. So we are fitting this model dot fit to this history. From this only we will get this loss value, accuracy value, and so on. So we are plotting this h dot history. So we are just like renaming this. So when we say h dot history loss, it will take that loss value, and we say train loss. So you can see this legend that says train loss and validation loss. So we are mentioning the labels here. So we are plotting the loss for the training data and the validation loss. So the train data loss is represented as blue color, and validation loss is represented in this orange line. Okay, so you can see at a point like after this fifth or sixth epoch, there is not much difference in the loss. Similarly, it's like we don't have much change in the accuracy after this fifth epoch. So this is the result that we are getting. So if you want, you can also build a predictive system out of it. So take this trained model and just like build a predictive system where you can like pass in an image that belongs to those 10 classes and make the model to predict it. So you can like refer to the dog versus cat that we have seen. So the process would be a bit similar to that. So that's about it. I'll just give you a quick recap of what we have done from the start, so that it's a bit clear for you. So first we have just importing this library called Kaggle to load this data. Okay, one sec. So we are installing this Kaggle library, and as I've shown you, we need to import this, or we need to download this Kaggle.json, and then like configure the path of this. Then we load this data directly from Kaggle to our collab environment through this Kaggle API, which is Kaggle competitions download CIFAR 10. Like once we download this, we are extracting this zip file. Later we found that the file was a 7g compressed file, and for this we are using py7zr. So later, once we are extracting the train folder also, so once that has been run, we can see that these many number of files are there, which is 50,000. So after that we are processing this labels data frame. So we get to know that there are totally like 5,000 images that belongs to each of these class, and we know that there are like 10 classes, and then we are like numerically encoding each of these strings, which are nothing but our labels, right? So once that has been done, we are just like displaying few of the images. So we can see some frog and dog images there, and later we are like processing the image in the order of 1 to 50,000 in the order of this IDs. So like in this process we are reading the image in order, converting it to a numpy array, and storing it in a list which we will convert to a numpy array later, right? So you can see the first, this is the first image, so data of 0, and later like we are converting to numpy array here, x and y, where x is your numpy array of images and y is your numpy array of labels. And we can see the shape that it's 32,32 image with 3 channels, which is a colored image. And the next step is train test split with 20% test data, and then we are scaling the images, which is nothing but dividing it by 255 so that all the pixel values are between 0 and 1. So once that has been done, we are building a simple neural network with just one hidden layer, its softmax activation, and so on. So in this case we could see the performance, and later we are loading this less than 50. So without this output layer, which is include top is equal to false, and the weights of image in a data set, and we are mentioning the input chip. So I've also clearly explained to you like what are all the different layers we are using here. So what is the purpose of these many upsampling, batch normalization, and so on. And then again we are compiling the model, fitting it, and later testing it with the test data, and finally building the plots of loss and accuracy. So I hope that you are clear with all the things covered in this video. So please practice this. So you can also try with different data sets that is similar to this data for object recognition with the same approach that we have done. Okay, so that's it from my side, and I'll see you in the next upload. Thanks for watching.
Hello everyone, I am Siddharthan. This is the fifth deep learning project video that we are working on, and in this video we will be building a face mask detection system using convolutional neural network. So we will start with the dataset where we work on processing this image dataset so that we can train our convolutional neural network. So once this process has been done, we will also be building a predictive system so that this trained model can be used to make further predictions of predicting whether a person is wearing a mask or not. Okay, so let's get started right away. And before going into the hands-on part, let's try to discuss the workflow that we are going to follow. As mentioned earlier, the first step is collecting the appropriate dataset. So this dataset basically contains two set of images. The first set of images is people wearing mask, and the second set of image is basically people who are not wearing a mask. So this is basically a binary classification problem, and this is the dataset that we will be working on. And we will be working on a Kaggle dataset for this purpose. So once we have this dataset, there are a lot of processing that we have to do. So this process is called as image processing, where we have to do processing such as resizing of images, converting these images into numpy arrays, and all those things. So once this image has been processed, the next step would be to split these images as training data and testing data. As most of you might be aware that we use this training set to train our neural network, and we use this test set to evaluate our model's performance. So once this step is done, we feed this data to our convolutional neural network, which tries to find how a person with mask look like and how a person without a mask would look like. So once this training has been done, we will evaluate this convolutional neural network with certain evaluation metrics. So once all these are done, we will build a predictive system where if you feed an image to this convolutional neural network, it will tell you whether that person is wearing a mask or not. So these are the steps that we will follow, and let's get started. So I'm opening my Google Colab environment. So this is where I'll be doing all this programming. So this is the site where you can get this face mask dataset. So there are like a lot of datasets that is available for this particular use case. So you can refer those. And this is the dataset that I'm going to work on. I'll also share this link in this video description. You can check that out. Okay. So the first step is to make sure that the Kaggle library is installed in your Google Colab environment. Actually, it will be installed, but it's better to run this cell. Okay, and the next step is connect your system. As this is a deep learning use case, we can get GPU access so that the training happens quickly. Okay, so to enable GPU privileges, go to this runtime and choose this change runtime type. So here in this hardware accelerator, I need to select GPU. Okay, so if you run your training without this GPU, so it will basically run on CPU, so it will take a long time to complete the training. So make sure you have enabled this GPU, and I'll save this. So now I can connect my system, and
I'm not going to download this data set, so you can see the size of this data set. So what I'm going to do is import this data set using the API. So from this you can copy the API for this data set. So I'm sure like most of you might know this already because I have done this in many of my videos. I'll also show you what are the things that need to be done. So to get this data set from the API, you need to have a API token. Okay, so it's basically a JSON file that is found in your account. So make sure you have an account in Kaggle, and also make sure your account is verified with your phone number. Then only you can get access to this data set. So otherwise you will get this 403 forbidden error. So make sure all these are done. Okay, so once that part is done, on top right corner you will see this account option. So go to that account. So here you can see this your profile and account. Now we have to go to this account, and here just scroll below, you will see an option called as create new API token. So once you click this, a file will be downloaded, which is kaggle.json. So I already have this file, so I'm not going to download this as of now, but make sure you have downloading this API file. And in some data, in some competition, you need to accept the competition rules, then only you can use that API. So that's like the other thing that you need to keep in your mind. Okay, so all the things that you have to do are like just create an account in Kaggle, verify your phone number and details, and download the kaggle.json file, and come back to your Google Colab environment. Go to this files, and here is where we have to upload this kaggle.json. It basically contains the details about your Kaggle account. So here you can see this upload to session storage option, or you can just right click here and give this upload. And now I need to upload this kaggle.json file. So I have this in my desktop, so I'll search for this. Okay, so I have this file, so you can see this here. So kaggle.json. So once this file is downloaded, you can run the other cell. So this code snippet is like pretty common. So it is just like configuring the path of this kaggle.json. You don't have to change any of these details. And also I'll be giving this link for this particular collab notebook in this video description. You can download this file and you can like work on it as well. So first I'll run this cell, which is basically to install the Kaggle library in Python. Here we can see this has already been installed, so no issues. And now we have to run this cell to configure the path of this kaggle.json. So once this has run successfully, now we need to import this dataset. As I've told you, you can do this by going to the site, and here from this option you can copy this command. Okay, so it's basically it's nothing but it contains this Kaggle datasets download D and this particular account and the dataset name. Okay, and make sure you include exclamatory mark before this API command. Okay, so then only you can like download this dataset. So I'll run this cell. So this will download this dataset which is present here. So once this data has been downloaded, you can see your dataset files from this files navigation bar. So let's wait for this. So it won't take much time. It's just like 163 MB. So it has downloaded. Now I'll go to this files and see if my file is downloaded. So this is the file that we downloaded using this Kaggle API, which is in the form of a compressed file, which is .zip. Now we need to extract this file, and this is the code snippet for this. So we have a library in Python called a zip file, which is also installed already in Google Colab environment. So I'm importing this zip file class from the zip file library, basically this module, and this is what we are going to use to extract our files. And this dataset variable is nothing but the path of our compressed dataset file. So you can get this by going to this files and copying the path. So once you copy this path, it's basically nothing but this path that I've pasted here. Okay, and we are opening this, basically we are reading this file as a zip, and then we are extracting. Once this extraction is done, we need to print the data set is extracted. So I'll run this. So once this process is done, we can also see what are all the folders that we have. So I'll go to these files again. So we have a new folder called as data. So this is the extracted content of this face mask dataset.zip. So I'll open this. So here we have two folders. First folder is with mask and the second folder is without mask. So this folder contains all the images of people wearing mask, and this will contain the images of people not wearing the mask. So this dataset is basically present in two folders. So sometimes what happens is this won't be the case. So all these two class or three class of images will be present in the same folder. So in that case, you need to get the labels in a different format. But in this case it's pretty easy because all these images are segregated already, so we don't have an issue on that part. So I'll close this. And also you can run this exclamatory mark and ls command, which is basically to list your directories, so what are all the folders and files that you have. So we have this data, face mask dataset.zip, kaggle.json, sample data, etc. Now, the next processes that we have to do are import the required dependencies, create labels for our images, process the images, split it into train test split, train a convolutional neural network, and build a predictive system. So these are the steps that we will follow. So let's start with importing these data sets. So I'll create a text cell and I'll mention this as importing the dependencies. So I'll import the basic libraries. So I want to import OS to access the files that we have in those folders. I'll also import numpy as np because we will convert these images into numpy arrays. Pandas won't be necessary in this case, so I'm not like importing it. I'll also import matplotlib dot pyplot as plt. I'll also import matplotlib dot image as mpimg. So these two, matplotlib library has this modules of pyplot and image, and we are going to use these modules in order to visualize our images and basically do some processing. That's the purpose. I'll also import cv2 library. So this cv2 library is used for image processing and all those tasks which are related to images. And there is another function that we need to import, which is from google.collab.patches import cv2 imshow. Now this is an interesting function. So in cv2 library we have a function called as imshow, which kind of creates a new window and displays your image in that window. And in this collab environment it's not possible to do that. So Google Collab kind of has a similar function which is stored in this Google Collab patches, and this is called a cv2 underscore imshow. So if you want to use the one that is present in cv2 library, so you would give this as cv2 dot imshow, but we won't use that in this notebook environment. So I hope that is clear. And the next thing that we will import is from pill, which is basically your pillow library. I'm going to import image. So pillow is also another image processing library that we have. It is used to read images and do some processing on it. And then I'll import my train test split from sklearn dot model selection import train test split. So this function is used to split our data into training data and test data. So let's run this cell. So these are the libraries that we need. So apart from this, for building our neural networks, we will be using TensorFlow and Keras. So we will import that later in this course, later in this like video. And now I need to analyze the images that is present in these two folders. So let's work on it. So here I'm creating a variable called as with mask files is equal to os.list.dir, and here I need to give a path. So this os.list.dir, which basically list your directory, kind of creates a list. So this list contains all the file names that is present in a particular folder. So in this case I'm going to copy the path of this with mask folder and I paste it here. So what happens is this list directory function will create a list which contains all the file names of with mask folder. Okay, and we are storing this list in a variable called as with mask file. So this is what happens. So this is like pretty simple. And then I've just wanted to check the total number of files here, or let's print the first 5 file names of this with mask file. So with mask files, so I'll copy this and I'm going to say 0 is to 5. So when I say 0 colon of 5, I'll print the first 5 files or the first 5 elements of the list, and in the next line I'll say minus 5 colon. So this print the last 5 file names. So let's run this. Yeah, as you can see, so this kind of creates a list that has all the file names in this with mask directory, and you can see all these image names start with underscore mask underscore, and there is a number, maybe some image number that is present. And these are the first five file names, and these are the last five file names. So we will like use this later as well. And now similarly, I'll create another a folder, and I'll call this as without mask files. So without mask files, I'll copy and paste this here. And now I'll copy the path of this particular folder and paste it in this line. So we are just doing the same thing but for without mask folder. So let's run this. Okay, so it says you're connected to a GPU runtime but not utilizing the GPU, because the only time we will use the GPU is when the training is happening. So you kind of get this warning, but it's not an issue. So next step that we need to do is just check how many images of mask, I mean like how many with mask images are there and how many without mask images are there. So we are just basically going to count the number of elements in this list and this particular list to make sure that the data set is balanced. So I'll say print number of mask with mask images, and here I'll say length of with mask files. And similarly, let's print the number of without mask images. So we have to paste this. Okay, sorry. So this should be given here. So let's run this. So this will give us the count. So here we can see the number of images with mask is 3,725 and without mask is 3,828. So this is the count that we have, and we can see there is no imbalance. This is like almost equal, so we don't have any issues. Now the next step that we are going to do is create labels for these set of images. So there are like almost 7,500 images, and we are going to create labels. So in this case, creating the labels is like pretty easy. So all we have to do is like create this many labels for with mask and this many labels for without mask. So this becomes an interesting challenge when all these images or all these files are present in a single folder. In that case, what you will do is you will read the file name of each of this file. If it is starting with mask, you create the label as 0. If this file name start with without mask, you create a label as 1. So that is the process that we follow. But in this case, we don't have to do that because all these are like segregated, so that won't be an issue. So let's create the label as the next step. So once this labels are created, we can move to the image processing part, where we will like display some of the images and do some processing on it. So I'll create a text cell and name this as creating labels for the two class of images. So let's make this bold. And now what we can do is let's label this as numerical values. So I'm going to say uh, if a person is wearing a mask with mask, then the label should be 1. If the person is not wearing a mask, so without mask, the label should be 0. Okay, so this is the label encoding that we are going to do. So I'll create this is the part where we are going to create the label. So I'll write a comment as create the labels, and let's create a variable which is basically a list with mask labels. Okay, so with mask labels is equal to, I'm going to say 1 into, so this is the with mask count, so I'm going to say 3725, and then I'm going to say without mask labels is equal to 0 into this number. Okay, so or what you can do is, you instead of 3725, you can also put length of with mask files. In this case, you can put a length of without mask files. So that also works. So basically, I'm creating a list which has only one element, which is 1. And when I multiply this with 3725, this will create a list that has 3725 values, and all these values will be 1. Similarly, this list will contain 0 as the value for this many numbers. So I'll run this, and then I'll print the first five values or values of this list and this list. So let's do that. So print with mask labels 0 is to 5, and I'll copy this and put without mask labels 0 is to 5. So let's run this. As you can see, first it says all the values as 1, and this is for 0. So this is what we are printing here. So this 1, and then we have this without mask labels as 0. So now what we have to do is just like make sure the count is same, and then we just like combine these two lists. So I'll call print length of this and the length of without mask labels. So we have 3725 with mask and 3828 without mask. So which is like the same number that we have here. So all the things have happened correctly. Now I just want to, combine these two sets. So I'll create a new list called as labels, and I'm going to say with mask labels plus without mask labels. So when I use plus, the values won't be added. If it is a numpy array, that is what happens there. But when you add two lists, what happens is two lists will be combined. So I'll use this. So I'm basically like combining the two lists that we have, and then we'll print the length of labels, and also let's print the first five values of this list, which is called as labels, and the last five values as well. I'm going to say -5 colon. So totally we have 7,553 labels. So first set of labels will be ones, and the last set of labels will be zero. So I'm just like printing the first five labels and the last five labels. So no issues as of now. So the creating the labels part is done. So the next step that we are going to do is understand how the images are looking like, whether all these images are of same shape. When I say shape, I mean the width and height of these images. And then we just have to do this pre-processing of image. So all these are like standard steps. So I'll create a Excel, and I'll call this as displaying the images, and for this purpose we will be using our matplotlib library. So you can also use cv2 underscore I'm sure, but in this case I'm going to use matplotlib. So let's create a command and say displaying with mask image. So let's display one with mask image and one without mask image, and let me create a variable as image. So image is equal to mpimg. So mpimg is nothing but matplotlib dot image, which we have imported as mpimg. So that is like the abbreviated form that we have imported. So I'm going to say mpimg dot imread. So this function reads your image in the form of a numpy array, and here I need to give the path. So I know that all the images with mask is present in this folder, so I'm going to copy the path. So please don't click this sign, because it basically contains more than 3000 files, so it will take a lot of time to process. So let's copy the path and paste it here, and then we need to give a file name. So here we have also printed the name of this file names. So I'll just like copy some number in this. Let's take this one, 2590, and I'll paste this here. Dot, is it jpg or png? Okay, so it's jpg, and I'll create another variable as plot image plot is equal to plt dot imshow img. So we are first reading the images as image as numpy array, and then displaying it in a matplotlib plot. So that's why we are using this plt, which is matplotlib dot pie plot, and then we have to mention this plt dot show. Let's run this. So this is the image that we have where a person is like kind of wearing a mask. So you can also like copy a different file name. So I'll copy this and paste it here. So all these images will probably have people wearing masks. So similarly, you can try for different images in this particular folder. So let's see. Yeah, so we can see here it basically shows people who are wearing a mask. And also note that the image dimensions are not uniform throughout. So I'll copy this, and now let's check this for without mask image. So here I'll go and copy the without mask folder path, and let's paste it here. And then in this files that we have printed above, I'll copy this path, sorry, this image name, and I'll put it here, without mask 2925, and let's run this. We can see here there is a person who is not wearing a mask, and the main thing that we have to note here is the sizes are a bit different. So this is like more than, like, the height is above, just about 200, here it's like about 250. Like here also you can see the size, the width and the width in this case. So all these images are of different shape. So that is like one thing we have to remember. So while processing these images, we have to resize these images in an appropriate way. So these are the other things, and the next step will be to do those image processing that I've been talking about. So I'll create a text cell and I'll name this as image processing. So let's run this. So there are two main things that we have to do here. One is resize the images, and the next one is convert the images to numpy arrays. So these are the two things that we have to do. And I'll create a command as convert images to numpy arrays. Here I'll create a variable as with mask path. So this is the path of the folder that contains all the images where people are wearing mask. So let's copy this path from here and let's paste it. Now there is a very important thing here. So at this end we have to put a forward slash. So I'll tell you why this is important. Just a moment. I'll create a empty list and I'll name this as data. So next thing is creating a for loop. So I'll say for image file in with mask files. So this is not this variable. So this variable is with mask path, but this is like with mask files. So this is the first list that we have created, right? So you can see here, yeah. So with mask files. So this is the list that we are accessing. So we know that this list contains the name of the files that is present in this particular folder. So this is what I'm using for this for loop, and I'm going to say image is equal to image dot open with mask path plus image file. So let's try to understand what happens there. So using a for loop, I want to read all these images. So the image file names that are mentioned here. So I want to read all these images. So totally there are about 3,700 images. So at each iteration, I want to take one image and read it. So for reading this, I'm using a function called as open. So image.open. So this image is nothing but the one that we have imported from Pillow library. So this image again is used for processing the images, and this open is for reading those images, and the parameter it takes is nothing but the path of that image file. So this is how we are giving this with mask path, which is this content plus image file. okay, plus image file. So what happens is when this for loop runs for the first time, this image file will take the value as with mask 193.jpg. Okay, so that is the value that this variable contains now. And when I say with mask path plus image file, it is nothing but content data with mask forward slash and the name of that jpg file name that I've showed you. So this is why we need to add a forward slash here. So if we don't add a forward slash, so this will just like concatenate this image file directly to this, so it will just give you a directory error. So make sure you are including a forward slash after this, and this is the code for this. Okay, so at each step we have to read a image. After reading this, we need to convert this to a standard size. So I'll say image is equal to image dot resize. So this image dot open, which we are using from pillow library, won't convert your image to numpy array but to a different pillow object. So that pillow object has a property of resizing. So I'll say image dot resize, and here we have to put this parenthesis, and within this parenthesis create a tuple and mention the shape that you want to resize to. So I wanted to reshape this to the shape of 128 comma 128. So these are some of the standard shapes that we have. So in some pre-trained models, you need the images to be in the shape of 224 comma 224, all those things. But for me, I'm going to create a custom convolutional neural network, and I want my images to be of the shape 128 comma 128. You can also try different shape, but make sure that is like in par with these shapes. Okay, so don't create or don't resize this to a very larger image, so that won't work properly. So here I'm going with 128 comma 128, where this number is the height of the image and this number is the width of the image. So now what happens is we have seen that all these images are of different shapes, and by using this particular code snippet, so using this for loop, we are reading all these images and we are resizing it. Once we resize this, we will convert it to the numpy arrays. And the next step I'll use is image is equal to image dot convert RGB. Again, this is a very interesting step. So this is not actually needed in all the cases, but in this case, this is needed because some of these files are being read as black and white image. This particular data set basically contains your image as colored images, but like very few images are in the form of black and white images. So if I don't include this, I'm getting this issue where the images are being like the black and white image, and you cannot train a neural network where some images are colored image and some images are a grayscale image. Okay, so that is why we need to include this, which basically converts your image into RGB color channel. Okay, so this is the next step. So, and in the next part, we are going to convert this object to a numpy array. So we are going to say image is equal to np.array. So it's okay if you don't understand some of the steps. I'll also explain all these steps one by one once this code snippet is done. So np.array image, and I'm going to say data dot append, data.append image. Okay, so that is all. So let's try to understand what happens here. So first I have the path of the image, which is basically to give this entire path to this image.open. So nothing complex in it. And I'm creating a list called as data, which is a empty list. And I'm iterating this with mask files, which contains the name of the files of all the images where people are wearing masks. And I'm iterating this through this. In the first step, this image file is being read using the pillow library that we have, using this image module using open function, and then these images are being resized to 128 comma 128 shape. That is the next step. And later we are making sure all the images are being converted to RGB, or it is like staying in the same RGB format. And in the next is a very crucial step of converting these images into numpy arrays using this np.array function. And once this image has been converted, we are adding this numpy array to this data list. Okay, so what happens is once this for loop has been executed completely, all these 3700 images will be read, resized, converted to numpy array, and all these images will be stored in this list. So this data list will contain all these images which are converted in the form of numpy arrays. That is what happens. I hope you are clear with this. uh, like you will also like see this clearly, so I'll try to show you the elements of this data list, so that will make like more sense to you. But there is another step that we need to do. This we have done only for the folder that contains people who are wearing a mask. So we need to do the same thing for the without mask folder as well. So I'll copy this entire thing, but you shouldn't copy this data. So we are going to add this to the same list that we have created. So we shouldn't like include this line alone. So I'll paste this. So copying, and let's remove this. So if you do this, so you will have only like these set of images, just these 3800 images only, so that becomes a problem. So I'll rename this to without mask path, and let's copy the path. Here also make sure the forward slash is present at the end. So I'll close this and let's paste it here. And this with mask files should be replaced by without mask files, which is given here. All right. So I'll paste this here. Yeah. Now we need to replace this here as well. Okay, so we are doing the same thing. The only difference is that once all these with mask images are processed, we are giving the path of without mask images. So the same process will be carried out. Only this path is different, and then we are taking the file names from this without mask files, which contains around 3800 images. So these names. Okay, and once this resizing has been done, RGB conversion is done, and we are converting to this NumPy array, and then we are adding to the same list, which is nothing but our data that we have created initially. So let's run this. If you have like more number of images, this step will take some amount of time, but for us it won't take like that much time because the count is just like 7500, so it won't take like that much time. Okay, so let's wait for this to complete. Okay, so this is some warning while we are like converting these images to this RGB pattern, so it won't affect us as of now. So let this run. In the meantime, I'll write few other codes. Length of data. Okay, so this cell has been executed, so this took around 27 seconds. Now this data is a list that contains uh, all the images which have been converted to numpy arrays. So first I'll show you the data type of this data. So it will show that it is a list, right? And now I'll print the number of elements or number of basically elements in the list, which is 7553, which are individual numpy arrays of individual images. So here I'll print okay, so I'll show you this data, how this data 0 looks like. Data of 0, right? So all these are pixel values, so you can see the values range between 0 to 255. So when we convert it to a numpy array, we are just like talking about getting those pixel values like in three matrices. One is like red intensity value, a green intensity value, and blue intensity value, which corresponds to this RGB images that we were talking about. I'm assuming that you know all these things. If not, I've already made a video on how this image data is being processed, so you can like refer to that as well. And now I'll check the type of this data. So type of data of 0. So data is the list, and data of 0 is the first numpy array in that list, so which is the first image in that list. So we have this numpy array. Now let's also check the shape of this data of 0 dot shape. So this will give me the value as 128 comma 128 comma 3. So 128 is the height of the image, this 128 is the width of the image, and 3 is the color channel. If we are working on grayscale images, you won't have any values. That means actually the value is 1, which corresponds to one color channel. Here we have three color channels, which are red, green, and blue, so we have the number as 3. Okay, so the final data that we got is a list that contains 7553 images, which are in the form of numpy arrays. So I hope everything is clear as of now, and after this like things are like pretty simple. We just have to build our neural network. So we know that this data is in the form of a list now, and also the labels is also in the form of a list. Now I don't want this in the form of a list. I want to convert this again to a numpy array. So I want to convert this labels to a numpy array, and also this data list to a numpy array. So let's do that. So converting image list. So when I say image list, I mean the list data, and label list to numpy arrays. So it's better to do the processing and training when the data is in the form of numpy array. So that's why I'm going to say x is equal to np dot array. So this function will convert a list or a tuple or anything into an array. So I'm going to pass this data, and we are just going to do the same thing for labels. So I'll name this labels as y, and instead of data we need this as labels. Let's run this, and let's also check the type of x and y now. So the processing has been done. So previously the data was was a label, sorry, it was a list data type. Now we have converted it to a numpy array. Numpy nd array, it basically means numpy n dimensional array. Let's also check this for y to make sure it is working. And now, okay, so it should be uppercase y. I'll print the shape of this x and y as the next step, and also the shape of y. So let's try to understand this shape. So this is the shape of x. So this number means the first number is the number of numpy arrays that you have in your entire numpy array. So this x is the overall array that we have, and this array contains 7500 arrays. So that this number actually represents that, and this is like the height of each of these arrays, and this is the width of each of these arrays, and this is the color channel. So this is the number of images or number of numpy arrays, height, width, and your color channel. And this contains only one value. 7553 is nothing but your labels. So if you want, you can also try to print your x and y and z. So let's print y. So it contains like 1 0, all these things, which are your labels. So I hope everything is clear as of now. So the next is a pretty easier step of splitting your data into training data and testing data. So I'll create this as train test split. So let me make this bold. So I'll create four arrays: x train, y train. Sorry, it should be x train, x test, y train, and y test. So all my training images will be stored in x train, and the corresponding labels will be stored in y train. All my test images will be stored in x test, and my test labels will be stored in y test. And then for this we'll be using the train test bit function, which we have imported already from sklearn.model selection. So train test bit, and here we have to pass x, which is our image array, y, which is our labels array, and then the next thing that we can do is your mention the test size. So in this case I'm going to take like 20% of the data as my testing data. So I'll say test size is equal to 0.2, which means 20% of data. And next is random state. Random state is a pretty simple parameter. So I'll say random state is equal to 2. So so each time you perform this train test split, your data will be splitted randomly. And if you want to reproduce your code, if you want to make sure the data is splitted in the same way, you mention the same number as random state is equal to that particular number. So here I've given this 2. And if you want to split the data in the same way that I'm splitting, you should also mention the random state value as 2. So that is like the importance of it. It is not like that much necessary and all those things. So let's run this. So the splitting process will happen. Now let's print the shape of the original array, which is x train dot shape and x test dot shape. Let's run this. So this is the original array, which contains these many files, and 80% of that is 6042 and 20% is 1500. Okay, so we have done this, and the next part is again a crucial step of scaling your data. So let's do that. So I'll explain you what exactly happens here. So scaling the data, here I'll create a variable as xtrain scaled is equal to xtrain divided by 255, and then this is for x test scaled. So let's run this. So let's try to understand why we need to do this. So previously we have printed this data of 0, which is the numpy array of first image. So I have told you that all these are pixel values. If the value is 0, so somewhere the value will be 0, that means for that particular pixel your color is black. If the value is 255, that means color in that particular pixel is white, and you have this number. So this means like this is somewhat in the middle, like all these color ranges range between 0 to 255. Okay, so when it is like, as we have discussed before, this is a colored image. So each image contains three matrix. One is for what is the intensity of red color, and the second matrix is what is the intensity of green color, and what is the intensity of blue color. And for red matrix, if you have the value as 0, that means the color is black. If the value is 255, that means the color is red. So that is like the idea of it. So here the main thing that you need to know here is like all the values range between 0 and 255. Now in the scaling process, we kind of scale down the values so that all the values ranges between 0 and 255. Sorry, previously it lies between 0 and 255. Now we want to make sure the values range between 0 and 1. So what happens is, when I divide this x train by 255, all these 7500 images we have, right, and all these images will have this kind of a numpy array. All these values of all these images will be divided by 255. If the value is 0, if we divide 0 by 255, we will get 0. If the value is 255, the result is 255 divided by 255, which is 1. So all the values will lie between this. So the minimum value that we have is 1, sorry, the minimum value that we have is 0, and the maximum value that we have is 1. So white color will be represented as 1 and black color will be represented as 0. So this is the main idea. So all you need to understand is we just have to scale down the values. So previously the values are in the range of 0 to 255. Once we divide by 255, we get the values between 0 to 1. So that is like the concept, so nothing complicated in it. And in most of this neural network cases, your model performs way better once you scale your data. So that's like the other thing that you can remember. I'll also show you how these values have been changed. So I'll print this x train of 0, which is the first image of this x train. So this is before scaling. You can see the values as 109, 107, 118, and so on. Now let's do the same, but we are going to print the same image in x train scaled, where we have applied this scaling factor. X train scaled of 0. So the result of these two cells are basically the same image. The only difference is that now the scaling has been done. So that is what is mentioned here. So if the value is 0, that value will be 0. If the value is 255 here, and the value will be 1 year, so all the values will lie in between them. So that is like the concept behind it. And yeah, so the image processing part is done, and now let's move on to the part of building our neural network. So I'll create a text cell and I'll name this as building a convolutional neural network. So I may not be able to explain all the building blocks of this CNN as of now, because the purpose of this video is just to understand how this implementation comes together. I'm about to make this course on deep learning, so in that I'll clearly explain you the basics of neural networks, and what is the importance of convolutional neural networks, what is the importance of convolutional layers, max pooling layers, and all those things. But for now, let's focus on the implementation part alone. So being a convolutional neural network. And as I've told you, here we will be using two libraries. One is TensorFlow and the another one is Keras. So here import TensorFlow as TF, and let's also import from TensorFlow import Keras. Okay, so let's try to understand the importance of these two libraries. So TensorFlow and PyTorch are the widely used libraries in order to build neural networks. So TensorFlow is the library developed by Google, and PyTorch is the library that is developed by Facebook. And Keras is just a wrapper of these libraries. So Keras is not a standalone library. So we will, have this APIs of sequential, convolutional layers, all this from the Keras library. But it is just like a wrapper of these libraries. So Keras need either TensorFlow or PyTorch in its backend. Okay, so previously this Keras was, this library was present individually. So what you do is import this Keras, and you also install the TensorFlow libraries, and you mention that the backend of this Keras is TensorFlow, or it can be PyTorch. So later, once people have started using it, so what happened is like TensorFlow kind of included Keras in its library itself. So that is what we are doing. So we are only importing the TensorFlow library or installing it,
Keras kind of comes with it. So first we are importing this TensorFlow library as TF, and from this TensorFlow library we are importing this Keras module alone. So I hope this is clear. And in the next step we can build a neural network. So here I'll create a variable as number of classes. So here we should mention the total number of class that you have, class of images. Here we have two class of images. One is with mask and the another one is without mask. So here let's create a variable as model is equal to keras dot sequential. There are like multiple ways to do this. So one is like we create this model is equal to keras dot sequential, and then we create a list within this, and then like what I do is uh, like add more layers here. So I'll just say model dot add, or no, or just say that we won't say model dot add. So we will say like keras dot layers or something like that, and we put a command and add all the layers like that. So there is also another way of doing this, which is you create this model is equal to keras dot sequential, and you mention the parenthesis here, and you say model dot add. This is the other way of adding layers to your neural network. So sequential is like this is where we stack all the layers together. So this is the first thing that we need to do, and in this add we can add different types of layers. So the first layer that we add is keras dot layers dot convolutional layer. So con 2D. So 2D convolutional layer, and here we need to give some parameters. The first parameter is your filters, and I'm setting the filter number to 32 here. And we should also mention the kernel size, so you can like work around these different values. So I mean you can't use any number that you think. There are like standard numbers that you can use, so you can like refer to it. So here I'm going to use the kernel size as 3,3, and there is a activation function. So I'll explain about this activation function, convolutional layers, all these things in our deep learning course. For now let's see how to implement this. Okay, so relu is basically your rectified linear unit. So you also have other types of activation functions like your um, softmax, sigmoid, and all those things. So we are creating the sequential, and then we are adding this convolutional layer as the first layer with 32 as the filters, kernel size of 3,3, activation function of relu. And the next thing that we need to do is give the input shape. So this is very very important. So this input shape is equal to 128 comma 128. So if you are working on a different problem, if you have a different set of images, the other things can remain the same, but like this you should change depending upon what's the shape of your image. And this is why I mentioned you that if you want to train a neural network, make sure all these images are of the same shape or same dimension. So here we know that all the images are of 128 comma 128 comma 3 because we have resized all those things. And again, if you have RGB images, make sure you mention 3. If you have grayscale images, you shouldn't have any values here, so it should be like this. But in this case this is a colored image, so we are mentioning this as 128 comma 128 comma 3. The first is your keras.layers.convolutional 2D, your 32 kernel size of 3,3, activation of relu, input shape of 128, 128, and 3. And the next layer that we will add is our max pooling layer. So model, so this convolutional layers and max pooling layer are two most important part of convolutional layers. So normal artificial neural networks, we don't have this. We just have an input layer, we have some hidden layers, and we have output layers. So the only additional thing that we have in convolutional layer is like different number of convolutional layers and max pooling layers. Okay, so I'll add this model dot add keras dot layers dot max pooling 2D. So here M, P, and D should be in caps. And there is actually like you don't have to do this keras dot layers dot come 2D. Like if you see each layer we use this keras dot layers. So the other way to do this is you can import this conv 2D, max pooling 2D, all this from keras itself. So that will also work. But for now, let's stick to this particular syntax and code style. Again, you can try these things by importing this keras and layers before itself. So that things will become like much easier there. So here I'll say max pooling 2D, and here we have to mention the pool size as 2 comma 2. Okay, that is done, and this is the first convolutional layer and max pooling layer, and I'm going to add more convolutional layers to it. I'll just add like one more pair of convolutional layer and max pooling layer here.
So here we have to change, like let's change this filters to 64. Kernel says let it be 3 comma 3. Activation is also relu. Okay, I think the other things let it be the same. Okay, so we shouldn't include this input shape. So the input shape should be present only in your first layer. It's like telling the neural network like this is the shape of the image that you will get. So you need to mention that only at the start, so you don't need to mention that anywhere else. So that is like one thing that you can remember. So we have the only change that we have made is like filters are there, kernel size again, kernel size are I'm giving the same. The only difference is your filter size. So first it's 32, next we have 64. Now we can add like flattened layers and more dense layer to our model, which is model.add keras dot layers dot flatten. So this is a very important layer. So we use this in any neural network that we build. So this is basically while passing your data or image to your model. So this should be passed as a single dimensional data. So if you can see, this is in the form of a matrix, right? So we can't pass this directly, so we flatten this. Flatten, what happens is like this two-dimensional data which is in the form of a matrix will be converted to something kind of a vector, some kind of a vector where the data is in only one dimension. So that is the purpose of this flatten. So this is like again a standard thing that we do in any neural networks that we create. So flatten is the next layer, and then we are going to add more dense layer, which are dense layer means like all the neurons in this layer is connected to all the neurons of the previous layer. So we call this as dense layer or basically your hidden layers. So I'll say model dot add keras dot layers dot dense, and I'll say 128. Activation is equal to relu. So the difference, so this is like the total number of neurons that you have in your network. So what this means is like in this first hidden layer or this first dense layer, I want 128 neurons. So there are like standard numbers that we use. So the numbers can be 256, or it can be 128, or it can be 64 or 32. So if you notice, all these are powers of 2. This is just to basically that uh, regarding this like memory allocation, all these things, so things will be better, or it's like memory efficient if you use the values in powers of 2. So that's the idea. Again, nothing complicated in it. So make sure you start with a larger number and you reduce the number of neurons in the further layers. So in this case, I'll start with this 128 neurons, and in the next layer I will have like 64 neurons. Again, all these are like powers of 2, so make sure like you are using something similar to that. And after this, I'm going to add a dropout layer. So this is again done to make sure there is no overfitting issue that may arise. So keras dot layers dot dropout. So this is just like turning off some of the neurons in our neural network so that it reduces the risk of the model getting overfitted. So that's the thing. So again, this is like the magnitude of how much dropout you to add. I'll give the value of 0.5. So and then I'll again create another uh, dense layer. So I'll copy this code and I'll paste it here. And now, as I've told you, I'm going to use 64 neurons in this layer. I'll have the other things the same, dropout layer, and there is like relu, all these things. You can also build your code with without dropout as well, again, but there is a chance of your model getting overfitted. And yeah, I think finally we can build our output layer. So that is again an important thing that we need to note here. So it should be the same, keras.layers.dense, but here this number should be the total number of class that you have in your data. Here the class is 2, right? So this is why I've created a variable here. So you can also say 2, but sometimes it's not like easier to understand why we have used 2 here. So that's why it's always better to store this 2 in a variable and use this variable here. So always we mention the number of classes in this layer. Again, if you use a different class function, we don't have to, like sometimes like you don't need to have two neurons, one neuron is sufficient, because in that case we use a different loss function. But let's not go into all those details as of now. Let's discuss that at some other use case video. So in this case, just remember that the number of neurons should be the total number of class that you have, which is 2. Okay, so what happens is like if mask image is predicted, one neuron will give the value as it's just a probability. So two neurons are there, right? So one neuron will give a probability for an image being masked image, and the other neuron will give a probability of the image being without masked image, right? So from this, like, the model try to say which is the highest probability, and we get the prediction. So that is also, that is why we have these the value as 2 in this case. I hope this is fine. And here I'm going to set the activation function as sigmoid. So sigmoid is used mainly in the case of binary classification problem. And there is also another, again, there are several activation functions. The ReLU, sigmoid are like the often used ones. There is another activation function called a softmax. So that softmax is used when you have a multi-class classification problem where you have like more than 2 classes to predict. Okay. So I hope everything is clear as of now. So first we are creating this keras.sequential, in which we are going to stack all our layers, and then we are adding our convolutional layer, max pooling layer, with this set of kernel values, kernel size, and like, sorry, this is the filter value, kernel size, and all those things. Similarly, we are creating another set of convolutional layer and max pooling layer, and then there is a flattened layer and a two dense layer and a final output layer with a sigmoid activation function. So let's run this. So this is just like setting up the architecture for our neural network. So the training has not been done yet. So there is another thing that we have to do before training our neural network, which is compiling it. So this step is compile the neural network. So when I say compile, it means we have to set optimization algorithm and loss function metrics for a neural network. So I'll say model.compile optimizer is equal to Adam optimizer. Again, so there are like different optimizers that we have. So we will discuss all those things in our course, but let's use the standard ones in this case: sparse categorical cross entropy. So if you have one not encoded labels, you can go with categorical cross entropy. If you have numerical encoded label, you can go with sparse categorical cross entropy. So that's something you can remember. And here I'm going to set the metrics as, in this list we have to mention ACC. So ACC means accuracy. Again, these are like standard things. So in this compile, we need to have optimizer, loss function, and your metrics. So I'll run this. And the next step is training our neural network. Training the neural network. So here we have to say, I'll store this in a variable called as history. So this history is equal to model.fit. So all this training checkpoints will be stored here. Again, if you do this, it's better to build the plots. So that is why we are doing that. So model.fit. So make sure you are passing your x-train scaled, which is your scale data. So x-train scaled comma y-train and validation split. So I'll explain you what is meant by validation split while this training happens. I'm going to set this validation split as 10%, which is 0.1. And I'm going to set only lesser number of epochs because we just have a smaller data set. So I'm not going to give many epochs, so that may lead to overfitting and it might not give a significant increase in the accuracy. So I'm going to set the epochs as 5. So this is the model training part. So model.fit, x-train scaled, which is your scaled image data, y-trains are your labels, validation split, and epochs. Let's run this again. So this training happens really quickly if you enable GPU from this runtime. If you are working on CPU, this is going to take a very long time. So make sure you are on your GPU environment. So let's try to understand about this validation split. Validation split is just similar to your test split. It is just to understand how your model is performing on unknown data at each epoch. So if you see, we have this loss value and your accuracy value. So our main goal is that the accuracy value should increase and your loss value should decrease, right? And at each step we reserve 10% of data. At each epoch we reserve 10% data as our validation data. So your training will be done on the 90% of the data, and in the remaining 10% your validation will be carried out here. So if there is overfitting, you can see here itself your training accuracy will be high but your validation accuracy will be low, just for that purpose. So usually when we train, we kind of like do this. So okay, after 5 epochs we get a training accuracy of 93% and the validation accuracy of almost 91%. So there is, again, if you can see, there is not a significant increase in the accuracy values. So you can like again try with the different epochs, you can try with different optimizers. So I'm leaving that up to you. So yeah, again you can try all those things, but I'm just settling this for now. So the other thing, so this took 30 seconds. Again, you can experiment with training this on CPU, and maybe you can also find like how much time that it takes. But this, we are like fine with this as of now. The last thing that we are going to do is just do the model evaluation on our test data to make sure the model is
performing well on the unknown data set itself. So that is, so this validation split is splitted from the training data, but previously we have set aside some test data in this X test and the corresponding labels are in Y test, right? So you can test that using this particular thing. So I'll put this as model evaluation. Here I'll say loss comma accuracy is equal to model dot evaluate. I'll say X test scaled comma Y test. So I'm passing the test data, and again we won't pass the Y test here. Actually what happens is, like, only this data will be passed to the model, and once the prediction has been made, it will be compared with the original ground truth, which is your Y test. And loss is your test data loss, and accuracy is your test data accuracy. They'll also print this print test accuracy. So this test accuracy is equal to, let's say, accuracy. So let's run this. Right, so the accuracy is like almost 92 percentage. So the training accuracy is 93 percentage and test accuracy is 92 percentage. So it's, the model is like working well. So like no issues in that. Now let's just like visualize these plots. Plots of like how your loss has changed and how your your accuracy has changed, those things. So for that I'm going to, so this is why we have fitted this model with a variable called as history. So I'll say h is equal to your history, and here first we are going to plot the loss value. I'll say plt, which is our matplotlib library, plt.plot, and h.history, and in this square bracket we have to mention loss. So this loss is nothing but the values that is present here. So all this we can get from this history, h.history or history.history of loss. And here we have to give the label as training. So this is not that label, this is the label for our plots and graphs. So I'll say train loss, that means like training data loss. And just similar thing, this is for h dot history of val loss. So just loss is for training loss, this is for validation loss. Let's call this as validation loss. Okay, label is equal to validation loss. Okay, everything is fine. And then you can say plt dot legend. Again, these are all the characteristics of the plot that we are building. So you'll be sure about this. Again, you won't have any doubts if you have worked somewhat on this matplotlib library. And then we have plotted this loss value, and then let's print the accuracy value. This is just to visualize like how your accuracy and loss function has changed over the course of your training of 5 epochs. So usually we train with a larger number of epochs just because like the data is small, we are just settling with lesser number of epochs. So here instead of loss we have to mention ACC, which is your accuracy, training accuracy, and here val underscore ACC, your validation accuracy. So here I'll call this as accuracy. Yeah, so this should do the work. Let's run this and see how this plot is building. Right, so this is like the plot that we are getting. So again, there is like kind of a zigzag thing, but ideally how this should be is, when we start, the loss function value will be higher. So from a higher loss value we try to minimize that so that like it kind of reduces. So this blue color is for training data loss and orange color is for validation loss. And similarly this is for accuracy, like again it starts from a lower value and it kind of reaches a higher value if your data is good, if you have a good neural network and all those things. So I hope you know what is meant by this loss and accuracy. Loss is basically how much your, what's the difference between your true value and your predicted value, or you can think about as the distance or the difference between your true value and the predicted value given by your model. Accuracy is like how many correct predictions it's like making. So if your loss decreases, your accuracy increases. So that's what you can also see here. I hope so far it's clear. And finally let's build our predictive system where we can pass an image and that will give you a prediction. So I'll call this as predictive system. Again, so you won't get 100% correct results in this case because your model is trained on a data set. I wouldn't say that is like very qualitative. Again, if you want better prediction, you need to give it more
images to train on. So that is like something that I would say, again, this will perform well, but again it depends on the data that you are feeding it. So I won't expect like 100 percentage accuracy in this case because of the data that we have trained on. If you get data similar to the ones that we have trained on, if you get the data that is in this test data set, in that case it would perform well. But let's try this with some data that we have got from the internet. Let's see how it's performing. So I'll create a variable as input image path. So how this will work is, so when I run this cell, it should ask for the path of the image to be predicted. Once I give that path, this image should be displayed and it should give a prediction of whether that person is wearing a mask or not in that image. So this is the idea. So here first we need to give a path as input, right? So I'll create input function here. So input, so it should say path of the image to be predicted. Okay, so next step, input image is equal to, so we need to read this from this path. So the path will be given by the user. So from this we have to read the image and convert it to a numpy array. That is the first step, and for that we'll be using cv2.imread. Again, you can use pillow. The reason I'm using cv2.imread is I'm going to display it using google.collab.patches, that cv2imshow function. So you can't read it through pillow, right? So we have this, right? So if you want to display it through the cv2imshow, you need to read this as numpy array. But if you use image.open, it won't be read as a numpy array but a different pillow object. So that's why I'm reading this using cv2.imread. And here we need to pass the path of the image, which is this input image path, right? And we use a cv2 underscore imshow, and here we have to, so this is again a numpy array, and put this here. So this will basically display your image. And then the next step is, remember we have resized all the images, right? So the image, if the model is going to predict the image, that image should also be resized. So I'll say input image resize is equal to cv2 also has this resize thing. So I'll use the one in resize. The previous one that we use is with pillow library, so this one is with uh, cv2. So input image comma, so mention like what is the shape that you are expecting. So I want the images to be in 128 comma 128, so you don't need to mention 3, it will be in color. And then it should be scaled as well. So all the processing that we done before should also be done here. So input image scaled is equal to this one, input image resized divided by 255, and image. So the next thing is we have to reshape this. So input image reshape. So I'll explain you why this reshaping is done. mp dot reshape input image scaled and 1 comma 128 comma 128 comma 3. Then we have input prediction model dot predict. So I'll explain you why I've given this number, just a moment. So input prediction is equal to model dot predict input image reshaped. Let's also print this input prediction so that we are clear like what's the result is looking like. Now input prediction label is equal to np dot argmax max of input prediction, and let's print this label as well. If this input pred label is 1, we have to say, we have to print the person in the image is wearing a mask. Else, so else means the prediction is 0. We have to say the person in the image is not wearing a mask.
Okay, so let's try to understand this. So first let's run this and see if it's working. So I have this input image path. Okay, so here the user gives in the path of the image that should be predicted, and we have this input image. So we are reading this image from the path given by the user, and we are displaying this image as the first step. And then we are resizing the image to the shape that we have trained our model. And then we are scaling the image, and this is the reshape part. So this is what I need to explain you here. Previously, for test data, we have used this model.evaluate where all the images will be predicted of 0 or 1, right? In this case, we are just predicting for only one image. So we need to reshape this so that the model knows we are predicting the label for only one image. So we have this one. So this one just says that I'm predicting for only one image, and the height of the image is 128, width is this, and the color channel is this. This is why we have this reshape, and for this we are going to use this reshape np.reshape. I'll repeat this. We are doing this to tell the model that I'm making prediction for only one data point. So that's the case. And once you do this reshape, you feed this to the model. So this is the model that we build using this keras model.predict input image. And the thing is, machine learning models will give you the prediction as either 0 or 1, but that's not the case in the case in this like keras neural networks. So you will get the prediction as probability values. So as I've told you before, here we have like two neurons in the last layer. So each of this neuron will give you a probability score. So one neuron will give you a probability like what's the probability that the image being a person wearing a mask, and the other neuron tells you the probability of the person not wearing a mask. So like it's basically a list that contains two probability values, so we need to choose the one that has a higher probability. So if it will be like evident once I run this, because we will print this probability values as well. And np.argmax, if the first value is maximum, it will this np.argmax will return the value as 0. If the second value is maximum, it will return the value as 1. So that's why we have this. So basically this step is done to convert this probability values to our respective label values. So that is all. And then we are printing that label value as well. So if this label value is 1, we say that the person is wearing a mask. If the else means the value will be 0, so we say the person is not wearing a mask. So before this, we just like pass some test images. So I have downloaded few images from the internet, and I have like stored this somewhere in my desktop. So I'll see. So I have this as test.jpg and test.png. I'm not sure if this will work correctly, but let's see. So first I'll copy this test.png. I think this is the one where person is wearing a mask. I'll copy that, and yeah, so I'll run this. Now this will ask for us to give the path. So paste the path that you have copied, which is test.png. So this should display the image. Right, so it says the person is wearing a mask. So path of the image to be predicted, we give that, and this is the result. So we have this probability value, right? So this is nothing but the input prediction. If you see, this first value is the probability that the person is not wearing a mask, because it is 0, and the second value is the probability that the person is wearing a mask. So here the second value is maximum, so we get the value as 1. So this is what np.argmax will do. If the first value is maximum, it will give the value as 0. If the second value is maximum, it will give the value as 1. If it is 1, we say the person is wearing a mask using this if condition. If it is 0, we say the person is not wearing a mask. So that is all. I'll copy this. If you want, you can also put this in a function instead of copying and pasting this every time. So that also works. So that is like up to you. So this image is displayed using this cv2 underscore I am show. So this one that we are predicting is nothing but this. So in print input pred label, right? So that one. So I'll run this again. Now I'll paste the JPG. So let's see if this works properly. So I'll go to this JPG and I'll paste this. Let's see if it's predicting correctly. It should say the person is not wearing a mask. Okay, so it says the person is not wearing a mask. So here we are displaying this using this cv2 underscore I'm show, and we are predicting this like printing this prediction using this input prediction, and finding this label as either 0 or 1 using this argmax np.argmax. Here you can see the first value is maximum and the second value is less, so we get the value as 0. And it says, if the label is not 1, we say it's 0, that the person is not wearing a mask. So this is what we are printing, is not wearing a mask. But if you see here, the probability difference is not that much different. So I mean, the model is like just in a confusion of whether it is a
whether it is a class of 0 or 1, but 0 is slightly more, so the model tells the person is not wearing a mask. Again, this depends on the data set that we have trained on. The data that we have trained our model is different, and the ones that we are using to predict is different. That's why we're getting this. And if you generally, if you use a larger data set to train a model, often your neural network will give like amazing performances. So that is the one thing that I wanted to add. So I hope everyone is clear as of now. So I'll just give you a quick recap of all those things that we have done to just like wrap things up. So we have started with importing the Kaggle library. So we, for importing this data set from Kaggle through the API, make sure that you have this kaggle.json. So I have showed you how you can download this, and this code is like standard. So this is just configuring the path of your Kaggle file, and this is the API to get your Kaggle data. So use exclamatory mark here, and we know that the data set is loaded as a zip file. So we are using this snippet to extract this file, and this is to see like what are the files are there in this directory. So we are importing all the dependencies that we need, and we are creating like two list, one with the file names of all the images with label, sorry, with mask, and the another one is like for all those images where the person is not wearing a mask. So those two things, and we are printing like how many number of mask images are there and how many non images without mask are there. So that thing, and again we are creating the labels based on this number. So first this many ones and this many zeros, again these are like pretty obvious, and then we are displaying these images to see like how the images are looking like, and we see that the images are of different shape. So now we need to resize this images, convert it to numpy array, and that we are using this for loop to do that purpose for with mask images and without mask images. So until this like the image processing part are done, so we are just checking the shape and all those things, and then later we are converting this list where data, which is the list of images, and labels is the list of labels. So we are converting that to the numpy array using this line of code, and then we are splitting the data into training data and test data, and after that scaling is done to make sure all the pixel values are between 0 and 1. So after that is done, we are building our convolutional neural network. So this is the architecture of this convolutional neural network, and the compiling part where we add our Adam optimizer, loss function, metrics, and all those things, and we are just like sticking to a lower number of epochs as of now to just make sure like there is less chance of model getting overfitted, those things. And we are like evaluating the model with by passing the test scale data, and this is just like visualizing your loss changes and accuracy changes. And finally we have built a predictive system where you can give the path of the image, and it will like tell you whether that person is wearing a mask or not. So this is like in the development phase. If you want to deploy this in a UI or an API, is like what you do is like you store this neural network as a file, and you can like uh, uh, deploy this in the form of a API and create a post API basically. So in that post API, you post that image, and your API, sorry, your model is resetting in that API, so it will give you a response of whether a person is wearing a mask or not. Or the other thing that you can do is just create a simple streamlit UI. Once the user is uploading the image, so that should be fed to the model that we are building. Again, that can call the API of your model, or you can also have your model in the local and just like give a response, and you can just print in that streamlit UI that the person is wearing a mask or not. So that is like I'll give that up to you. You can like work on the deployment part. Okay, so I hope everyone is clear until this point, and I'll see you in the next upload. Thanks for watching.